set at the initial stage of education, while implementing a diversified list of mixed techniques and methods. The reason for the latter is that, were global or less diverse learning techniques and cognitive regimens to be adopted, the techniques and methods might be inflated into models of cognition for the learner. The learner is always liable to mistake a particular problem-solving technique for a global model valid for solving not just similar problems but every problem, and hence to transfer the specific biases of techniques and methods into global models by means of which problems are detected, approached, analyzed, and tackled. The primary goal of the generalized pedagogical system for the child AGI should be to provide the child with the necessary and sufficient wherewithal to form an increasingly complex structuration of the world in all its complexity. This is a structuration through which new modes and ranges of thinking and action, what can be thought and done, are continuously being uncovered. Structuration which, essentially, is the function of 279. Mind aspires not only to render the world intelligible, but also to disclose new orders of intelligibilities as pertaining to things, thoughts, practices, and values. In other words, the primary goal of education and generalized pedagogy is the functional re-realization and augmentation of what mind already is, a unifying structuring point or configuring factor in which the coextensive complexity of the theoretical practical subject and the world in its radical otherness are expressed. What ought to be thought and done combined with what the world in its complete unrestricted conception is, this is a formula for what could possibly in the remotest sense of possibility be thought and done. It is precisely the regulative ideal of education. Education is, in this sense, the self-realization of mind as a project rather than as a thing or a given nature. Education is the project of all projects, an undertaking without which no other project, be it ethical, scientific, or political, can either sustain itself or be tenable. Understanding and realizing the mind as an edifice of structuration, of both the world and thoughts and practices, culminates in the discovery of what else can be thought and done, that is, pushing back the boundaries of all practical abilities. But this unbinding of all practical abilities of mind is what concrete freedom actually is. Education, then, ought to be grasped as a process of scaffolding for developing abstract autonomy into concrete freedom. This transition is what Hegel regards as the quaking of the singularity of the will, that is the necessary moment in the education of everyone. 213 Every other undertaking or project can only be thought in terms of a task that is supported and sustained by the scaffolding that needs to be continually raised. Education, therefore, should be treated as a complex and dynamic recipe for providing the necessary and sufficient wherewithal for the structuration of the world that the subject inhabits. In outlining education as the extension of the project of mind in its drift toward concrete self-consciousness, we can think of a list of the cultivating vectors and regimens that define the broad tasks of a generalized pedagogy of the child AGI. This generalized pedagogy, however, is more like a primary education through which the child AGI comes to recognize the necessary correlations between mind and world, structure and being, intelligence and the intelligible, theory and object. Practical and axiological education, praxis and ethics are left out for two simple reasons. 1. Investigating the complexity of practical and ethical education are beyond the scope of this work. 2. Praxis and ethics, and logic understood as the general organon of mind, are ultimately two sides of the same coin. No form of praxis or ethics can dispense with the question of intelligibility, which is but the question of structure as the dimension of mind through which it can establish and renew its relations, theoretical, practical, and axiological, with the world, a renewal which is tantamount to the transformation of the mind itself. Even within the ambit of mind as the edifice of structuration or logic, this list is by no means exhaustive, but merely schematic. It is only an attempt to sketch the rough outlines of what the global pedagogical project entails. We can broadly think of this program in terms of the realization, augmentation, and composition of two interconnected sets of abilities, the semantic and syntactic abilities of mind required for the structuration of world, and the thoughts and actions that occur within it. We can denote structuring semantic, meaning, abilities as SM abilities, and structuring syntactic, formal or axiomatic, as S/1 abilities. Once again, it would be helpful to remind ourselves that, generally speaking, structure is the differentiated and ordered interconnection or interrelation of elements or parts or aspects of an entity, a domain, a process, etc. Structuration in this sense involves the negation of both the simple and the unconnected. Point 214 or, to appropriate sellers, how and what things in the broadest possible sense of the term hang together in the broadest possible sense of the term. Point 215 Since these syntactic and semantic abilities can be composed to yield compound structuring abilities, let us additionally denote this process of composition by the operator O, which maps functions to functions, or abilities to abilities. QMF is then a compound within which an element of a semantic ability increases the complexity of a syntactic ability. Respectively, QFM is a compound structuring ability in which an element of a syntactic, formal axiomatic, ability together with its constitutive rules is applied to a semantic ability. Take for instance, logic mathematics modality, GFM-SF ability, applying a modal vocabulary, **SFM ability, more complex structured material inference. It roughly reads as the compound semantic syntactic ability to form a better material inference involves the introduction or application of a modal element, a modal relation, from formal domains of structuration, logics, and mathematics, to the semantic ability of knowing what it entails to deploy a modal vocabulary and thus to say or judge something with it. And correspondingly, OMI/ability approximately reads as a structuring syntactic ability assimilated into and augmented by a semantic ability. This is merely to highlight the fact that the concrete structuring abilities of the mind often come in composite semantic and syntactic forms, and indeed that we can think about the composition and diversification of such abilities in terms of a combinatorial calculus of objective thinking. Even though laying out the fundaments of such a calculus is beyond the scope of this book, in principle such a calculus for the diversification and complexification of mind structuring abilities can indeed be formulated as a curriculum for the education of the child. Finally, as a last note, the differentiation of semantic and syntactic abilities does not mean that semantic abilities are devoid of syntax or that syntactic abilities lack semantics. It simply means that the emphasis of semantic abilities is on semantic relations rather than on syntactic resources or formal relations, and conversely the focus of syntactic abilities is on the formal and/or axiomatic syntactic structures with an eye to the overall semantic dimension. Both SM and SF express different but interconnected classes of the mind's structuring function with regard to the world which, as discussed in Chapter 1, can be elaborated more coherently and with less metaphysical frills in terms of the copulas of theory and object and structure and being. The consideration of that which not only involves the formation of theoretical claims or statements, it is the case that, but also implicitly or explicitly implies theoretical validity in the sense of theory outlined in Chapter 1. Grasping what it means to form theoretical claims and what one is doing when one asserts or endorses a theoretical claim, in turn, demands the acquisition of language and logoi and acquaintance with the relations between them and the dimension of structure. The cultivation of SM and SF abilities, therefore, can be elaborated with reference to the fundamental aspects of theory, the mutual relations between language and logoi, Z, structure, S, and the data under consideration, U, provided by L within which objectivity is determined. SM abilities, generally, semantic abilities can be characterized as qualitative higher-level modes of cognition. They afford agent models that are qualitatively compressed and therefore economical. Such mod Ls are complex and dynamically stable yet small in size, semantics as a qualitative mode of compression. Semantic abilities can be roughly defined as absolutely necessary abilities for the structuration of the world, i.e., the function of the irreducible correspondence of mind-language in relating to the world. Therefore, semantic abilities are abilities that permit the state of affairs concerning that which is to be rendered intelligible, thought, or spoken of. Primarily, ontological facts are configurations of semantic facts. 216 SM abilities mainly involve conceptualization. In Brandomian terms, semantic abilities can be approximately characterized as those abilities or practices necessary or sufficient to obtain semantic relations between vocabularies and those abilities or practices necessary or sufficient for deploying vocabularies that stand in semantic relations to one another. Put differently, semantic abilities concern what one must do so as to count as saying something meaningful, judging something, or thinking about various kinds of things, and what one must say in order to explicitly specify or codify practices underlying those sayings or thinkings. Here and throughout this book, meaning stands only for determinate semantic value as that which is assigned to a piece of reasoning or a judgment. All things considered, semantic abilities are those structuring abilities required for forming an unrestricted universe of discourse. A generalized pedagogy for the generation and augmentation of SM abilities consists of training regimens in such structuring domains. A. Base semantic structuration. A1-1, proto-conceptual labeling, rudimentary classification by assigning labels/names to items which are available to sensation via reliable differential responsive disposition, RDRD. Point 217. For example, the non-linguistic K can be trained like a parrot to make the noise, not to be mistaken for a saying, "That's black," in the presence of the heap of black. Here, the RDRD performance "that's black" in the presence of a black item imposes classification on the stimuli, thus differentiating those which would from those which would not trigger the response of the given kind by practicing that particular RDRD. A1-2, description and explanation, placing labels into a space of implications where classification is coupled with explanatory relations which can be expressed by modal vocabulary. An empirical description must then have both inferentially articulated circumstances for the appropriate application of labels and inferentially articulated appropriate consequences of the application of labels. Material inference allithic modal vocabulary counterfactuals. Context sensitivity handling, semantic consciousness of contexts and circumstance, O/M resource sensitivity handling, semantic consciousness of contexts and contextual premises as logical resources, resolving conflict between different counterfactuals in one context, integration or separation of different contexts O/W possible world representation, where the meaning or sense of an expression can be accounted for not simply by its reference in the actual world, but also by what the expression would have referred to, had the actual world been different, i.e., from the counterfactual standpoint of possible worlds that are as actual as this actual world of reference. Point 218 Belief revision or commitment updating non-monotonic and defeasible reasoning, i.e., a reasoning in which conclusions can be retracted based on new evidence. Finding defeasors or counter-defeasors for acquiring a new belief or preserving an existing one based on the incompatibility of practical commitments/beliefs or lack thereof, cf. addition or removal of premises in the light of the relation between the control set and the context in the match example discussed above. A1-3, intentional vocabulary, what one uses in order to ascribe claims, beliefs, desires, or intentions that p. A1-4, normative vocabulary, what one uses in order to ascribe commitments or entitlements to a claim that p. A1-5, OMF non-axiomatic coherentist theory formation, theories which are not axiomatic since they are not built on established truths or truth givens, but rather are constructed out of truth candidates, whose cohering web of inferential interrelations not only decide which truth candidates must remain, be modified, or discarded, but also make explicit the structure of theory qua system of structuration. B. Experimental semantic structuration. B.I. Logics of discovery. Abductive reasoning, take for instance Peirce's example of the logic of surprise, an anomaly or a surprising fact, C, is observed, but if A were true, C would be a matter of course. Hence, there is reason to suspect that A is true. Point 219 Here hypothesis A is suspected or conjectured to be true even though A may be false, i.e., it is tentatively believed on reasonable grounds that A is true. Point 220 In this framework, the observation of an anomaly and its corresponding framed hypothesis call for the revision and expansion of the theory that covered that class of observations so as to accommodate the anomalous observation. Thus, Abductive reasoning can be understood as that type of reasoning that instigates a change in epistemic attitudes, cf. belief revision. Abductive hypothesis construction or framing of conjectures. Abductive non-predictive hypotheses allow for the explanation of both a proposition and its negation. Abductive model-based reasoning, where models accommodate different explanations of observed facts, and where new beliefs can be adopted and old beliefs can remain so long as they cohere, cf. coherentist theory formation and Brandam's material incompatibility and inferential consequence relations. Point 221 Model pluralism. The availability of many different explanatory schemas, weak and predictive, and their corresponding models so as to enable not only the discrimination of some explanations as preferable to others but also an increase in the range of explanation to cover new observations, anomalies, or surprising facts. Analogical reasoning. The exploration of the outcome of the structural alignment of the shared relational pattern between two or more contextually contiguous concepts, ideas, or models. For instance, think of the Archimedean method of solving geometrical problems by inventing a mechanical analog. Example: a lever for solving the problem of how much bigger a cylinder is than a sphere of the same radius by articulating the relation between the weights of a cylinder solid and a sphere solid of the same radius, both made of the same material, via an adjustable lever, i.e., with a moving fulcrum, capable of balancing their weights. In this form of analogy, to solve a geometrical problem/idea, a mechanical analog, interpretation, or metaphor of the geometrical problem is introduced. The analogical solution obtained from the machine analog together with its constitutive mechanical reasoning is then mapped onto and reinterpreted as the geometrical solution and its constitutive geometrical reasoning. Metaphorization or conceptual coboritism. 222 How to derive a new higher-order structure from two different cognitive structures by constraining operations that allow the drawing of a contiguous contextual boundary between them through which analogical transfers and the synthesis of a third higher-order structure can be obtained. The role of metaphors in discovery can be compared, following Gilles Châtelet, to a Trojan horse that takes the cognitive habits of one context or field of thought and deploys them into another, thus setting in motion a whole dynasty of problems otherwise invisible from the perspective of any one field alone. Point 223. B. S/abilities. In contrast to SM abilities, SF abilities can be characterized as structure encoding abilities, or more generally as abilities whose main point of emphasis is on the formal or syntactic aspects of structuration. Roughly speaking, syntactic abilities or formal axiomatic abilities are required for constituting specialized domains of discourse qua sciences. They can be understood as formal calculi, from something like situation calculus for reasoning about dynamic domains to event calculus, representing and reasoning about events, to process calculus, proof calculus, etc. As evolved and explicitly formal structure encoding abilities, syntactic abilities are primarily the objects of what Robert Harper dubs the Holy Trinity of computation, namely logic, mathematics, and computer science, or proofs, programs and categorical structures. Point 224 Just as semantics possesses a hierarchical complexity where conceptualization and the role of concepts become increasingly more involved at higher levels, so syntax also has its own hierarchical complexity. The complexity of syntactic abilities can be mapped onto two different hierarchies: pure formal grammar, a la Chomsky's hierarchy of syntax, and formal axiomatic theoretical structures, a la Stegmüller's hierarchy of axiomatics, which concerns the axiomatization of theories. The difference between these two formal hierarchies lies in their approach to syntax. Whereas formal grammar focuses on pure generative syntax and its computational algorithmic properties, the axiomatic hierarchy deals with the different types of axioms through which different kinds of axiomatic theories, whether quasi-formal or formal, can be constructed. In this respect, formal grammar can be approximately mapped onto computational abilities, recursive pattern matching, algorithmic design, rules of pattern recognition, etc., while the axiomatic hierarchy can, again, roughly, be mapped onto the logico-mathematical abilities required for theory construction in the domain of exact and specialized sciences. A. Hierarchy of formal grammar as the domain of basic formalization abilities. In terms of pure syntax, syntactic complexity consists of the recursive processes required for generating syntactic languages or encoding structures, formal grammatical properties that specify levels of encoding or formal languages, and the automata necessary for computing them. In this hierarchy, computational power and complexity, and sophistication of encoding, increase from lower levels of syntax to higher levels. In tandem with the increase in computational capacities, computational cost, the demand for memory resources also increases. Consequently, with the increase in computational costs and resources from the bottom to the top, effective computability decreases. 225. B. Hierarchy of axiomatics as the domain of abilities, of logic and mathematics and computation, required for the construction of formal theories as employed in specialized sciences, as formal axiomatics, that is, systems required for forming specialized axiomatic theoretical structures. The complexity of the formal can be elaborated as the hierarchy of axiomatics and the different types of formal theory structures afforded by different classes of axiomatic systems. In the Structure and Dynamics of Theories, Stegmuller classifies axiomatic systems, or calculi, into 5 forms of axiomatization, with each form having the capacity to construct a distinct class of structuration qua formal axiomatic theory. 226. 1. Intuitive axiomatization, axioms as self-evident truth sentences, as in Euclid's Elements. 2. Informal Hilbertian, set theoretic, axiomatics or abstract qua non-intuitive axiomatics, where axioms are sentence forms belonging to the ordinary language of discourse. 3. Formal Hilbertian axiomatics, axioms as formulas and axiomatizations as calculi of formulas, comprising tuples, SAR, where S is a syntactic system, R inference rules for deriving formulas from formulas, and A subclass of axioms belonging to the axiomatic system based on the construction of a completely formal language. 4. Informal, naive, set theoretical axiomatization, where axiomatization is based on the definition of a set theoretical predicate and axioms are elements of an introduced set theoretic predicate. It is called informal axiomatization since set theoretic predicates are introduced at the ordinary and intuitive level of discourse rather than in the framework of the formal system of set theory itself. 5. Explicit predicate or explicit concept for an axiom system, which is the formal equivalent of informal naive set theoretic axiomatization. Here axioms in comparison and contradistinction with the fourth axiomatic system are explicit predicates belonging to the formal system of set theory. In the case of each of these calculi, by assigning to the individual terms in the axioms definite objects and to the property and relation predicates properties and relations, one obtains an interpretation of the axiom system. 227 From the perspective of constructing models, the hierarchy of axiomatization or calculization of theories is intrinsically connected with the semantic dimension, since the concept of formal model is based on the conversion of the syntactically defined formal language via the introduction of an interpretation into a semantic system where the concept of validity as relating to terms, statements, and applications of the model to the data under consideration can be made precise. Without this conversion, the objectivity of a model cannot be sufficiently established. Given the importance of the pure formal grammatical and axiomatic aspects of syntax for computational and theoretical abilities, abilities are absolutely necessary for the encoding and construction of formal and specialized fields of structuration, that is, for forming complex models of the world. The goal of the catalog above is to show not only that we can think about the cultivation of our child AGI in terms of a combinatorial calculus of structuring powers of the mind, where we can map one ability to another or decompose a complex ability to simpler ones, but also that such a curriculum requires a diverse range of educational methods. As Brandom suggests, the problem of generalized pedagogy is the central problem of artificial general intelligence. The graduation from a child to an intelligence that encounters itself in an objective world and thus is capable of reimagining itself in accordance with an expansive field of intelligibility requires a back and forth movement between the trainee, K, and the trainers, S and M. Such a movement is built on a pedagogical stimulus, often on the part of the trainers, that elicits the response of the trainee and, in a positive feedback loop, test-operate-test-exit cycles, prompts the responses of the trainers built on the response of the trainee and vice versa. In Brandam's words, I am suggesting that what, in a course of training, is most analogous to algorithmic elaboration of abilities is pedagogical elaboration in the form of a training regimen. In rare but important cases in early education, we have completely solved the problem of how to pedagogically elaborate one set of abilities into another. What it means to have solved a pedagogical problem for a population with respect to an output practicer ability is that we have an empirically sufficient conditional branched training regimen for that practice or ability. This is something that, as a matter of contingent fact, can take any novice from the population who has mastered the relevant range of primitive practical capacities, and, by an algorithmically specifiable test-operate-test-exit, TOTE, cycle of responses to her responses, can in fact, though without the guarantee of any principle, get her to catch on to the target ability. For us, training pupils who can already count to be able to add is essentially a solved pedagogical problem in this sense. That is, starting with pupils of widely varying abilities and prior experiences who share only the prior ability to count, there is a flowchart of differentially elicited instructions, tests, and exercises that will lead all of them to the target skill of being able correctly to add pairs of arbitrary multi-digit numbers. 228. A curriculum formed around a calculus of structuring abilities can be thought of as a pedagogical rather than an executive, i.e., fully mechanizable algorithm for graduating the child. The point is that, even if a fully mechanizable algorithm for such abilities could be developed, it cannot be adopted by a generalized pedagogy for the graduation of the child AGI. All the development of such an executive algorithm implies is that abilities can be elaborated into more complex ones or decomposed into simpler ones. But insofar as K is always going to be a creature constrained by the specific parameters of its sensory causal structure and its particular set of contextual experiences in the world, algorithmic automation or mechanizability of abilities won't be adequate to the job. Pedagogy always moves forward in response to, at least, the trainee's capacities and contextual experiences. Short of that, education becomes a tyrannical and ultimately abortive endeavor. This, of course, does not mean that we cannot think of the training regimen for K in terms of mechanizable algorithms. It simply means that the kind of pedagogical algorithms we should conceive for K must involve the interaction of the trainee and the trainers as agents which do not have essentially the same causal structure and the same set of experiences, or more generally as agents that have different computational cost constraints. With this disquisition on what the education of the child AGI consists in, not just learning the use of concepts in order to have a structured experience in virtue of being able to objectively think or judge the contents of its experience, but also the capacity to employ syntactic and semantic abilities or technologies of structuration afforded by language and logic, we can move forward with the last part of our thought experiment. Realization of language. In the previous chapter, we witnessed the development of K into what Rosenberg terms a child, whose interactions with its environment are bound up with and inferred by its interactions with its linguistic guardians. Next we saw that the transition from child status to fully fledged general intelligence requires certain cognitive regimens or educational methods through which K becomes increasingly competent in expanding its outlook by imputing structure to the world, universe, and to its own thoughts and actions. However, this development looked suspiciously straightforward, and indeed, there was in fact a sleight of hand in our thought experiment. With the introduction of the multi-agent system, we assumed that K's adult guardians were full concept having language using AGIS, that is, we assumed we had already constructed general intelligence. In other words, we made too great a leap from the goal of our thought experiment, the realization of general intelligence, to the presupposition that it had already been attained. Nevertheless, there is nothing inherently erroneous in this assumption, since we could easily swap the role of the linguistically proficient automata S and M with their linguistically proficient human counterparts S and M. However, While this rectification is easy and sound, it misses a point. The condition of possibility of discursive apperceptive intelligence rests on the condition of possibility of language, or, in other words, the realization of general intelligence is constituted by the realization of language. Even though the introduction of linguistic agents into the thought experiment is not an illegal move, then, it does include the key role played by the realization of language both in terms of its evolution and its autonomous and sui generis rule-governed functions in the realization of the conditions of possibility of general intelligence in the first place. Language is not something to be developed and introduced after the fact, and then imposed upon general intelligence. It is the very framework within which general intelligence can be realized. In short, the realization of general intelligence is concurrent and coextensive with the realization of language as that which makes it possible. There would be no Geist, no mind, and no thinking I, were it not for language as the most spiritual, geistig, existence, Dasein, of the spiritual. 229 The omission of any consideration of language when addressing issues such as truth, thinking, life, and being inevitably leads to an iteration of the myth of the given and culminates in an atavistic metaphysics which is both dogmatic and pre-critical. This is because any talk of truth, life, or being presupposes semantic structuration within the universe of discourse, and the question of semantics cannot be divorced from language in its generic form. Claims of a non-linguistic thought or of access to being without language rank even lower than claims to the existence of magical powers and miracles, since they are by definition, in virtue of their purported immediate involvement with reality as well as their normative critical impoverishment, predisposed to turn into a breeding ground for the most dubious and debilitating ideologies. In our thought experiment, the construction of AGI must therefore be a part of the realization of language. Rather than taking language as an extrinsic feature of this construction that can be introduced at a later stage, the realization of language will be treated as an intrinsic and constitutive dimension in the realization of general intelligence. In tandem with the constitutive role of language for general intelligence, the thesis endorsed here is that the construction of artificial general intelligence should be primarily conducted via an extensive project that can bring about the necessary conditions for the possibility of language among a system of artificial agents. Crudely put, the evolution of language should be taken seriously as the most indispensable part of the realization of general intelligence. Instead of providing artificial agents with a pre-developed formal language that might be able to mimic the behaviors of natural language, an environment must be established within which artificial agents can develop through the evolution of language among them. That is to say, the aim is to reenact the concurrent and coextensive realization of language and general intelligence. The reason for the employment of this reenactment strategy is that the evolution of language should be seen as a process of canalization of prevalent intelligent behaviors toward qualitatively distinct and sui generis behaviors. Through this process, intelligent behaviors, or agents, progressively come under new generative constraints, each of which enables a piecemeal qualitative shift within the system of interacting agents. The key to this process is the development of multi-agent interaction from rudimentary communication to interaction via symbol design, from symbol design to syntax, and from syntax through interaction to semantics. In other words, interaction at different levels of complexity, from proto-linguistic levels to pragmatics as the interface between syntax and semantics, is not only the key to the evolution of language and its autonomous rule-governed functions, but by extension is also the key to the realization of general intelligence. 2 points are worth noting here. The first is that the construction of artificial general intelligence can be informed by insights into the evolution of natural language, without sacrificing research into the diverse logical and computational aspects of syntax, semantics, and pragmatics. My intention is not to collapse the distinction between the evolutionary picture of natural language and the autonomy of language, particularly semantics, as a rule-governed system. Instead, the claim is that these two need to be rendered commensurate without being fused or blended together. The second point concerns the emphasis on natural language. Although language may well have begun with ordinary natural language, it cannot be reduced in its entirety to natural language. Despite its low syntactic complexity and semantic ambiguity, natural language harbors a diverse range of complex logico-computational phenomena which can be incorporated into the design of an artificial general language, a superior mode of language that exhibits both the properties of formal theoretical languages, syntactic powers and semantic transparency, and the explicitly interactive, qua-social, dimensions of natural languages. Interaction as the explicit framework of natural languages is the implicit and fundamental. 297. Logico-computational framework of language in general. We shall come back to this latter point below. With these remarks in mind, in order to proceed with the as a 1TP thought experiment, a necessary change must be made. The status of 3 and M as fully fledged concept having automata must be rescinded, so that they now have the same status as K. The only modifications that remain are the ones introduced at the beginning of the previous chapter, i.e., the multi-agent system and the capacity to produce quasi-continuous sounds. The course of the thought experiment will be developed in the following stages. First, we shall briefly look at the automaton's capacity for non-conceptual representings through which metalinguistic properties picture non-linguistic properties, of items and occurrences in the world, via syntactic structures of sign designs. This is Sellers's account of picturing as detailed in his essay Being and Being Known, where the android robot equipped with the robotese language forms progressively more adequate pictures of the world. 230 Necessary adjustments will be made to Sellers's account of picturing by distinguishing sign design tokens from symbol design tokens. Only the latter can have a syntactic configuration in the combinatorial sense, one that can capture the relations between signs, or Sellers's pictures, qua non-conceptual representings. Without minimal symbolic syntactic structure, picturing cannot constrain the arbitrariness of meaning. Pace Sellers, pictures cannot have syntactic structure. Pictures are one-to-one non-conceptual representations, or, more accurately, second-order isomorphisms between two natural objects. By contrast, conceptually represented objects are caught up in combinatorial relations between symbols which themselves are not non-conceptual, representing sign design tokens or inscriptions at the level of causal structures. From here we move into an examination of what symbols are and what process or processes are required for the realization of a symbolic syntax that can later on be bridged with semantics. This is the process of discretization necessary for the realization of combinatorial symbols. However, we must keep in mind that language is not merely a symbolic syntactic medium. As already argued, it is first and foremost a semantic structure that configures word-world relations. The final stage of the thought experiment involves a survey of how the transition from syntax to semantics is possible under the aegis of interaction as a logico-computational phenomenon which is the engine of language and its multilayered qualitative structure. In accordance with the toy model approach, but also owing to practical constraints, the examination of the role of interaction as the bridge between syntax and semantics will be kept at the minimal introductory level. In our toy universe, the interactive framework of the multi-agent system represents a computational problem. How can the agents synchronously and asynchronously interact with one another and their environment, given that, a. Maintaining interaction between agents is dependent upon an optimal interaction with their environment, and, b. The agents vary in terms of their sensory impressions, memories, and behaviors, i.e., different individual interactions with the environment. In this setting, maintaining the interaction between the automata becomes a matter of the stabilization, adaptation, and enhancement of interactive strategies, reactive as well as proactive, both at the level of inter-agent interaction and that of multi-agent system-environment interaction. If we consider the interaction between agents as a computational strategy for effectively modifying the computational parameters of interaction with the environment, then this computational strategy should accommodate and display stabilizing and adaptive mechanisms appropriate for a wide range of interactions involving asynchronicity, resource distribution, and dynamic behaviors. In this sense, the interaction between the agents is interlocked with their interaction with the environment. The complexity of the former, therefore, should be regarded as an adequate means for engaging with the complexity of the latter. A change in the computational capacities of the inter-agent interaction as a result of a qualitative shift in its structure would translate into a change in the computational capacities of the system-environment interaction. Within this environment, imagine the occurrence of two events, EI, example the rustling noise, and E2, example appearance of a fuzzy gray item. By virtue of their causal structure, wiring diagram or nervous system, the automata are capable of associating one occurrence with another. For example, a rustling noise, IVR, then the presence of a fuzzy gray item, G, or the fuzzy gray item coming into contact with the heap of black, C, then a shrieking noise, NS. In other words, K, S, and M are aware of these occurrences, their associations, transitions, and precluding relations in the form of the following inductive moves. Rustling noise ** fuzzy item, if n are at place p and time t then g at p and t. And its corresponding obstruction or preclusion, i.e., not a move. 3 degrees. Like no rustling noise * fuzzy item, if no nv at place p and time t then g ax p and t. Fuzzy item, contact with the heap of black * shrieking noise, if g at place p plus ap and time t plus at then ns and tp plus ap, t plus a pound. Or, more generally, the occurrence of an event ex in the environment is accompanied by the occurrence of another event ey. Such associations contain their corresponding transitions and obstructions. At this point, the automata are capable of statistically correlating E\s pattern of occurrence with #js pattern of occurrence. More precisely, the automata are capable of forming non-conceptual associations and transitions between one pattern of occurrence and another, e.e. However, they do not know objectively speaking tey, for example, is the sound a monkey makes when examining a monolith. These associations and transitions are purely a matter of statistical predictive generalization. We can call the association or transition e a pattern-governed regularity that registers at the level of the causal structure and behavioral outputs of the automata. The capacity to causally register in an adequate manner with regard to the behavioral outputs or reactions of the automata to the environment a pattern-governed regularity is called picturing, i.e., a non-conceptual representing of events and items in the environment. A simplistic analogical example of picturing would be a security swipe card. The magnetic field changes the iron-based magnetic particles on the stripe of the magnetic material on the card. As the result of this causal structural change, the card can open certain doors and not others, the constraining element. However, this analogy could be misleading. Even though pictures are instantiated in causal structures, they cannot be expressed in causal terms or as a form of causation. Instead, they should be understood in terms of processes. The automata's capacity for correct picturing, qua rudimentary representation, of events in the environment is as much the result of the pressures and constraints imposed by the environment, the presence of items and occurrences that affect the causal structure or wiring diagram of the automata, as of the complexity of the causal structure of the automata. 3 degree I. That mediates between environmental input and behavioral output. For the sake of brevity, let us say that whenever both E and occur in the environment, there is a corresponding change in the causal structure, wiring diagram, or nervous system of the automata. This change occasions an equivalent, but not equal or identical, pattern-governed regularity EE which is then reflected in the behavioral output of the automata in the form of the inductive moves transformation rules or rudimentary protocol-like transitions described earlier. Here, EFE** is a rudimentary i.e., non-conceptual representing that can be understood as a mapping between objects belonging to the real order the wiring diagram of the automata and occurrences and items in the world. Therefore, picturing, the world, differs from signifying, the world, in that the former belongs to the real order and the latter is of the logical order, that of thinking or, in Sellers, intentionality. Point 231 Signifying and picturing, then, belong to two distinct levels of discourse. and although rule-governed signifying is embodied in pattern-governed picturing, it is irreducible to the latter. Similarly, although pattern-governed regularities incarnate and constrain rule-governed conceptual activities, they cannot be overextended to encompass the latter. It is picturing, pattern-governed regularities, that undergird signifying, rule-governed conceptual activities. But the order of signifying is irreducible to the order of picturing, since it is concerned not with pattern-governed regularities but with the complex interactions between patterns. In other words, rule-governed conceptual activities are patterning patterns. Contra right-wing Sellerchians 232. The realization of the rule-governed or normative order of the patterning of patterns requires a qualitative shift in the order of picturing that permits the explicitation and navigation of the diverse relations between pictures or pattern-governed regularities. Pictures qua signs can only capture the one-to-one mappings between pattern-governed regularities in the real order, EE***EFEJ**. Said differently, non-conceptual representations are independent of one another. Their relationships are not given in themselves, and they lack the kind of structured relationships required for transitions between them, whereas symbols in themselves are entirely devoid of such one-to-one mappings, and primarily stand in combinatorial relations to one another, symbol to symbol, token to token, and only secondarily in relation to extra-symbolic reference. 233. And it is in virtue of this interrelational order of symbols, i.e., symbolic syntax rather than syntax in terms of causal regularities, that the relations between different patterns or world picturings can be encoded, structured, singled out, and elaborated. In other words, semantics is afforded by symbolic elements of syntax whose relations differ in kind from the relations indexed by pictures. Signs, icons and indices lack combinatorial syntactic structures to the extent that they are representational mappings that only stand in one-to-one causal structural equivalence relations between properties of the representations and properties of the represented items or occurrences. As soon as we talk about syntactic structures that enable semantic interpretations, we have crossed over from the domain of signs into that of symbols as combinatorial syntactic elements that primarily map to one another rather than to an item or occurrence in the environment/world. Understanding semantics enabling syntactic symbols in this way does not risk a hypostatization of abstract entities, since they are still constrained and embodied in pattern-governed regularities or pictures. But the manna of this constraining or incarnating regime is not a matter of the simple compositionality of pictures. Pictures do not map to syntactic symbols, but only to the interrelations between symbols which, in themselves, have no mapping relation whatsoever to pattern regularities in the world. In other words, pattern-governed regularities in the real order are caught up in the relations between symbols, not the other way around. Such relations themselves are not pattern-governed in the sense of belonging to the real order. They are instead already rule-governed, i.e., combinatorial, relations belonging to a different order, the autonomous order of symbols. Collapsing the distinction between signs and symbols, picture mappings and symbolic syntactic interrelations, or regarding conceptual activities as a species of pattern-governed behavior 234 is a recipe for all sorts of confusions, one to which Sellers himself has unfortunately contributed some ingredients. Just because conceptual activities and their undergirding symbolic interrelations are built on pictures and iconic indexical signs, this does not mean that conceptual activities and symbols are made of pattern-governed regularities and mapping relations. Being built on something is not the same as being made of something. Let us clarify these points in the context of our thought experiment. In the multi-agent system, the automata have their own inductive moves. The contact of the fuzzy gray item with the heap of black, changes their wiring diagram. The state of the representational system or the wiring diagram of the automata is now a second-order isomorphism, i.e., an equivalence, but not equality, relation that registers as a statistical inductive association with its corresponding transitions and obstructions. For example, the occurrence of the fuzzy item making contact with the heap of black and then a shrieking noise is registered on K's wiring diagram as a pattern-governed regularity that permits certain rudimentary inductive moves, whenever NS, shrieking noise, ATP plus AP and T plus at then G, fuzzy gray item, at P plus AP and I plus at. It should be pointed out that registering the noise NS depends on a few factors. Firstly, it must be of some interest or significance for K, i.e., it must play a role for K's overall behavioral economy. If the noise is of no interest to K, it will not register on K's attentional SYSTEM, D-Henny. Only the top-down attentional amplification of modular processes can mobilize the change in the wiring diagram and make it available to K's global workspace or awareness of the environment. Secondly, registering the noise NS crucially depends on the sufficiency of K's causal structure or wiring for pattern recognition. Without this criterion, K would not be able to differentiate the amplitude and frequency of the shrieking noise from the rustling noise and would therefore be incapable of making inductive moves, transitions and obstructions related to these items. Our assumption, however, is that K, S, and M satisfy such criteria. They are equipped with the adequate causal structure to differentiate not only NS and IVR, but also such noises of interest to them insofar as they play an important role in their behavioral, or perception action, ecology. Upon occurrence of the pattern NS, K's auditory system registers it as an input acoustic pattern which is associated with the occurrence of NS and, COR respondingly, with the fuzzy item touching the black item. The automaton tags this acoustic pattern by emitting a whistling sound or acoustic QZ using its inbuilt electromechanical devices. The acoustic QZ has no meaning in the sense of describing NS or signifying what the picture of 305. The fuzzy item touching the black item accompanied by a shrieking noise, is. From now on, whenever K registers it emits the whistling sound too. Within the multi-agent system, K's repeated reuse of 2 is also registered by S and M as a cue for the occurrence of NS and, correspondingly, the pattern-governed regularity EE. The significance of the relation between EEPEE, NS, and A in triggering 2 is simply that of the statistical frequency of spatiotemporal occurrences registered by the structurally sufficient and behaviorally active automata. In short, it is devoid of complex inferential or conceptual relationships. This is precisely what Peirce calls an index-Eichel sign, a sign whose interpreton is entirely a statistical regularity of some occurrence, a causal or temporal invariance, and whose interpreter requires only a heuristic device to interpret it. An index is a sign that is somehow causally linked with something else in space and time. Furthermore, index-Eichel sign vehicles such as 2 are built on iconic signs that concern the resemblance of one pattern to another. This resemblance, however, is wholly a matter of an arbitrary interpretation of the similarity vagueness of something versus something else. In this sense, iconicity is really the stimuli-based discrimination of stuff. Pictures qua mapping functions are index-Eichel signs, which themselves are built on icons or stimuli-based discriminations. In terms of their reference, both indices and icons are arbitrary and generic. A clarifying example of index-Eichel sign vehicles would be social animal alarm calls. In citing a predator, a member of the group vocalizes a specific sound that is statistically associated with the presence of predators. This sound or index-Eichel sign does not, however, specify the type of the predator, nor does it relay any information to other members of the group regarding the predator's exact location. It simply signals the presence of a danger in their vicinity. Similarly, the only significance of 2 is that it communicates an index-Eichel one-to-one relationship between the interpreter, the agent, and the interpreted. EEFF transmitting and receiving 2 is what we can call communication, reserving the term for this rudimentary schema of transmitting and receiving an index-Eichel one-to-one relationship between a sound cue and an interpreted event or series of events. 3°6 Upon registering an input acoustic pattern, K's internal pattern recognition mechanisms match it with K's archive of input patterns correlated with previously catalogued patterns of occurrences. If the registered acoustic pattern matches a the automaton produces 2 as a signal pertaining to the alleged occurrence of the associated events E-EY, setting aside the problem of the arbitrariness of the representational correspondence between C and the E-EJ pattern of occurrence. The indices A for K and 2 for S and M are fundamentally narrow in the range of their relationships with other indices associated with other pattern-governed regularities. The insufficiency and unreliability of the prevalent index-equal sign vehicles is nowhere more manifest than in natural phenomena involving mimicry and deception. Take for instance the parasitoid blue butterfly Phengaris rebelli, known for its intricate social parasitism on a species of ants called Myrmica ants. The butterfly lays eggs close to the ant colony. Its broods discharge the same chemical signals by which ants distinguish their own. By mimicking the ant's index-equal chemical sign, the butterfly broods trick the ants into carrying them into their nest. Once they are in the nest and as they mature, by mimicking the acoustic signals the queen ant uses to mobilize worker ants to bring food to it, the butterfly larvae climb the social hierarchy of the ant colony. Associating the mimicked acoustic signal with their queen, the worker ants begin to bring food to the parasitoid larvae, in the process starving their queen, the only ant that can detect the larvae as aggressors, to death. However, for the Myrmica ants the semiotic nightmare does not end here, for the oversaturation of chemical signals as the result of the activity of both the ants and P. rebelli's parasitism lures yet another parasitoid to the ant colony, the ichneumon wasp, cited by Darwin as evidence that shakes the very idea of a beneficent and omnipotent God. 235 Owing to their one-to-one mapping structure, just like indices, pictures qua non-conceptual representings are limited in terms of how they relate to or interact with other pictures. The complex relations between pictures or pattern-governed regularities cannot be obtained by pictures themselves. Claiming that automata can, in principle, fully structure and navigate their environment simply by adequate picturing inevitably results in picturing regress. This is because the structuration and navigation of the environment requires the selection, explicitation, and elaboration of diverse relations between pattern-governed regularities. In order for such complex relations to be singled out, a new picture or one-to-one mapping must be acquired. But insofar as the acquisition of a new picture or the detection of a new pattern-governed regularity results in additional relations between pictures and patterns which the new picture cannot by itself index, still further pictures must be acquired. This process can go on ad infinitum without ever covering the complex relations or interactions between patterns, hence the regress. Where there are one-to-many and many-to-many correlations between patterns, the picturing capacity, as a one-to-one mapping, always falls short. Moreover, from the practical perspective, even if the automata could indeed fully structure and navigate their environment by adequate and complete picturing, from a computational point of view this would be unfeasible, since for every matter of factual property of items or patterns of occurrences of events in the world, they would have to acquire not only a picture or representational mapping but also additional pictures to represent the diverse relations between those pictures and their corresponding regularities. With this ever-expanding repertoire of picturings, the size of the automata's internal model would grow. Since computational resources and memory would need to be allocated to these pictures in order to support the structure of the internal model, as it increased in size the internal model would become less and less effectively computable. Once the complexity of the internal model's structure could no longer be increased owing to the lack of effective computability and resource starvation, it would no longer be capable of singling out or picturing new phenomena and items. The representational competencies of the automata would then begin to diminish. This is a ubiquitous scenario among any species equipped only with iconic and index-equal sign vehicles, and not symbols. For index-equal sign vehicles to cover the diverse relations between pattern-governed regularities, they have to be incorporated into a different kind of semiotic system, one whose signs are not in a one-to-one or representational relation to referents, patterns, or events. The order of picturing and index-equal signs is necessary but not sufficient to cover the interactions between patterns. This sufficiency can only be obtained by a different kind of semiotic system that is not composed of mappings. This is a system in which the semiotic elements do not represent or relate to a pattern-governed regularity, an external event, or a substantive referent, but only to one another. The combinatorial order of symbols that permits syntactic configurations is exactly this interrelated semiotic system. In the vernacular use of the concept of symbol, symbols are symbols because they are inscriptions, letters, characters, sounds, or gestures that abstractly represent something else. But such elements are not symbols in the strict syntactic and formal sense. Symbols are only symbols insofar as they are abstract non-representational entities that relate or refer to one another rather than to something external to them, i.e., a represented target event, pattern, etc. For semiotic elements to be reorganized as symbols, certain criteria must be satisfied, such as the discretization of signs and the establishing of a combinatorial structure, i.e., rules for the possibility and impossibility of combining signs, whereby recursive processes can generate new and more complex relations between abstract elements. It is the order of symbols that has syntactic structure, not the order of signs whether iconic or indexical. And it is only the syntactic structure of symbols elements that only stand in one-to-many and many-to-many relations to one another that can codify relationships between pattern-governed regularities, pictures, or indexical signs. Conceptual semantic activities are sui generis pattern-governed regularities, or rules, that pattern or structure pattern-governed regularities, i.e., single out and elaborate the diverse relationships between patterns because they are undergirded by syntactic structures that structure and codify such relationships. The codifying syntactic structures are themselves afforded by symbols, semiotic elements that are defined not by how they represent an item or an external 3. Relation of reference, but by the combinatorial relationships in which they stand in relation to one another. Put simply, the order of symbols is not a representational order in the sense that iconic or indexical signs are, but an order whose systematic interrelations can codify or structure indexical relationships, something that indexical signs by themselves cannot accomplish. Indices are accordingly caught up in the combinatorial and codifying relationships between symbols or elements of syntax. Just as indices are built on icons, symbols are built on indices. But, as Terence Deacon points out, the fact that symbols are built on indices and indices are built on icons does not mean that the relations that hold between them are relations of simple compositionality. 236 Indices are not made of icons and symbols are not made of indices. Symbols, indices, and icons are distinct levels of structuring. Whereas representational icons and indices have a limited capacity for structuring, symbols, by virtue of their combinatorial self-referentiality, have an in principle unrestricted structuring capacity. For our automata, the capacity for the full-blown structuration of their world does not begin with their ability to correctly picture their environment, but only with the advent of symbolic technologies that permit the syntactic codification and semantic elaboration of the relations between pictures. This is, however, not to suggest that the automata may not have more adequate picturing abilities than ours. They may well be furnished with more sophisticated mechanisms for pattern recognition and algorithms capable of more optimal compression of data and hence more fine-grained picturing or regularity detection abilities. This is the fundamental insight of Ray Solomonoff as formulated in the context of algorithmic complexity and the computational account of inductive inference, that there exists an intrinsic duality of compression and regularity. Anything that can compress data is a type of regularity, and any regularity can compress data. 237 For example, we might imagine our automaton's picturing abilities to be modeled on better predictive compression algorithms such as Solomonoff's induction or Crutchfield's 8 machine reconstruction, which employ a formal computational, rather than ordinary epistemic, version of Occam's razor and the principle of multiple explanations to yield inductive models smaller in size and of a lower degree of arbitrariness. 238 Briefly, Solomonoff's predictive induction employs the formal computational definition of simplicity: all knowledge available in a domain at a specific time can be written as a binary string. In this case, a new observation or experience at time t2 increases the length of the string. Solomonov's induction problem is then how to predict the next bit of the string by extrapolating the known length of the string. Independently of Andrei Kolmogorov and Gregory Chaitin, Solomonov showed that there exists an optimal prior probability distribution on any potentially infinite string such that one can compute the next best possible or formally simplest extrapolation using this universal prior distribution. The best predictive model can then be defined in terms of the length of the shortest program that outputs the simplest possible string. 239 The picturing abilities of our automata could indeed be modeled on such programs. 240 But prediction is not the same as explanation. Even in information theory, prediction and explanation are subtly distinguished from one another. Furthermore, as argued earlier with regard to the problems of complete picturing, an agent modeled purely on such formal learning machines would still run into the problem of effective computability. For example, Solomonov's universal learning machine presupposes an infinite time limit and runs on a universal Turing machine. For a realistic agent with a finite time and limited computational resources, not only may the implementation of Solomonov's algorithm result in resource impoverishment, since the universal Turing machine is the most resource-consuming class of abstract machines, it may also lead to the uncomputability of the halting problem, that is, the undecidability of whether the machine should accept or reject an input to yield an output. Accordingly, what is required for explanation is not better prediction or the compression regularity duality, but the ability to selectively compress data or to single out one regularity over another. And precisely what language starting with the order of symbols affords agents is the ability to selectively compress data, to single out and elaborate diverse relations between regularities, not merely to picture pattern-governed regularities but to describe and explain them in context. As discussed in the previous chapter, this copula of description and explanation is what material inferences ultimately are. For our automata to count as belonging to the order of general intelligence, they must be able to perform material inferences, to have the practical competences or know how to use concepts. In short, they must have an artificial general language to syntactically encode the relationships between pictures, to structure such relationships by semantically elaborating their material incompatibility and consequence relations, and ultimately to make explicit such relations in formal inferences. Coming into possession of such structuring syntactic semantic abilities, however, entails something more than just the addition of new sign vehicles or better pictures of the world. It requires symbol design, the construction of symbolic tokens that can be combined in a variety of ways to form codifying structures and assume semantic roles in the process of being exchanged between agents. In the following sections, we shall see how the sign-using automata can be endowed with structuring syntactic semantic abilities by coming into possession of symbols whose combinatorial generative capacities permit the stabilization of inter-agent interactions and the encoding of diverse relationships between pattern-governed regularities. In developing the ability for symbol design, no additional modification to the multi-agent system will be introduced. What we want is to see how the interacting automata themselves, using the resources they already have at their disposal, in particular, the capacity to receive and transmit acoustic signals or sound cues, can acquire symbols. In Chapter 5, a new constraint was incorporated into the modifications of the automata: the automata can only produce quasi-continuous sounds. The motivation for the addition of this constraint was that it would allow us to monitor the processes required for the generation of symbols in the toy universe of our automata. Recall that the automata are provided with organs or electromagnetic devices capable of constricting the continuous sound, noise, and discontinuing it in a specific manner. In this way, the sound is discontinued either abruptly or gradually, i.e., within a temporal window. The constricted or discontinued sound now represents an acoustic range. It is regulated by different constricting devices working in coordination with one another, paralleling the role of the lungs, nasal canal, tongue, and lips in human vocalization. At this point, the sound is still continuous but is also regulated by the manner of discontinuation or constriction. 315. The quasi-continuous sound can be refined further into a coarsely discretized sound via the frequent reuse, i.e., production and recognition, of the sound as a form of statistical modulation over time. Once our hypothetical agents solve the problem of the discretization of sound cues into stable tokens in interactions whose role can be tracked, diversified, and manipulated, they can single out and relay a wide range of behaviors pertaining to themselves and to the environment. Solving this problem requires the transition of the sound cue, sign, from a partially stabilized and regulated acoustic range, a quasi-continuous sound, to a coarsely discretized sound that can be not only effectively reproduced and recognized by the agents, but also used as a building block for composite symbolic sounds. In the end, what we want to do is to equip the automata with a medium through which they can not only share their positional perspectival awareness but also, more importantly, compare their perspectives in a stabilized and structured manner, and ultimately arrive at an aperspectival, objective, view of the world. This development would require a stable and combinatorial medium capable of replacing the parochial referential relations between sound cues/signs and occurrences/references, i.e., the representational relation between 2 and EF, with syntactic and ultimately semantic relations between symbolic sound tokens. But in order to get on the path of such a development, first the sound cue 2 needs to transform from a sign referentially correlated to something external into a symbol that primarily stands in relation with other symbols. However, to recapitulate, what we are after in the toy universe of automata is a system comprising a finite repository of abstract elements which individually do not represent anything yet which, precisely because of this abstractness, can be combined to create composite elements which then can be put together in conformity with combinatorial rules, thus generating increasingly complex syntactic structures capable of encoding the relations between non-conceptual representing or pattern-governed regularities. The abstract elements of this system are symbols, and to reach the stage where automata would be able to employ symbol designs to syntactically and semantically structure their world, their acoustic medium of communication will have to undergo a drastic transformation. As we shall see, this transformation is impossible. 316. Without a process of discretization, which is required in order to implement effective combinatorial mechanisms among sound tokens. In the previous sections, we saw that K, S, and M have the capacity to communicate in the rudimentary sense of receiving and transmitting sound cues to marking pictured pattern-governed regularities. In this communicative regime, however, the instability and the excess of noise in the quasi-continuous sound too negatively affects the precision of its signaling function, both in the sense of what it signals, the EE-pattern of occurrence as opposed to a different occurrence signaled by another quasi-continuous acoustic cue, and how the cue is successfully recognized and consumed in order to result in coordinated group response. An example of the inefficacy of quasi-continuous sound cues for transmission and reception as reliable signals would be animal alarm calls where, because of the instability and fuzziness of the acoustic signal, the call can play different roles, to signal the presence of a predator, as a mating call, in the presence of food, etc. The appropriate group action is therefore always compromised by the fuzziness of the quasi-continuous sound cue exchanged between the communicator and the communicant. In issuing a certain sound cue, there is no guarantee that the group will reliably receive the communicated signal as a cue for the referent targeted by the communicator. In addition, the quasi-continuous sound possesses a low degree of combinatoriality. Since quasi-continuous acoustic cues are structurally unstable and fuzzy in terms of their acoustic range, multiple cue integration is severely limited. This lack of combinatoriality means that stable and coded relations between different sound cues cannot be established properly, if at all. Without these relations between sound cues afforded by combinatorial grouping, the role of the acoustic signal in connection to its source, the correspondence between 0 and E-EJ, and its target, recognition and consumption of the sound cue by other agents, can be neither specified nor stabilized. In isolation, the role of a sound cue as a probability marker is not optimally reliable, either in relation to what it signals or in relation to its potential signal consumers. In our toy model, suppose that the solution for reducing the noise and fuzziness of the quasi-continuous sound is the systematic reuse of acoustic 3*7. Cues in the context of interaction between agents. Over time, the reuse of sound cues among the automata in an interactive framework leads to a crystallized distribution of preferred models of sound production between agents in a fashion similar to a self-organizing map or an artificial neural network utilizing unsupervised learning algorithms to cluster data by projecting high-dimensional input data, training samples, onto regular and discretized or low-dimensional data. The decrease in the number and range of acoustic data means that the agents over time automatically select and reuse a small number of clusters of preferred low-dimensional acoustic data. To put it less technically, a model of self-organization can be conceived in the multi-agent system whereby the mere vocalizations of the automata, i.e., the reuse of sound cues or acoustic signals, can converge on a small finite repertoire of preferable coarsely discretized sounds which do not communicate or represent anything, in that they are no longer sign vehicles but abstract acoustic elements that can be combined into composite sound tokens. Structural discretization, together with the decrease in the number of sound clusters, results in the construction of the first building blocks of speech, that is, a finite repertoire of sounds as symbolic tokens. 241 The automata are now in the possession of a limited but well-structured set of reusable and shareable sounds, beeps, clicks, chirps, rustles, etc. that can be combined in accordance with compositional constraints to form more composite non-representational sounds. These sounds are comparable to the basic phonological units of our speech, and can be combined in asterisk conformity with statistical acoustic transition rules to produce composite sound tokens that can be exchanged in interactions between automata. For example, in our phonological system the transition from a V sound J*3 to a SH sound is a high-cost transition, whereas V to a is a low-cost and optimal transition. The low-cost transition results in a preferable concatenation VAA that can be added to the sound repository for reuse and further composition with other sound units. In this way, numerous utterable concatenations can be produced from a very limited set of basic discrete sound units. 242 The discrete units can take on new features within the concatenated compositions. These new features can then be singled out and introduced as additional constraints on the composition of sounds, producing ever more varied and richer concatenations that would constitute the skeleton of the automata syntactic utterances. The organization of a sparse number of discretized sounds should not be interpreted as a reduction in the capacity of sounds in their role in the interaction between the automata because, in the new configuration, sounds can be combinatorially grouped and structured. In other words, the process of discretization and the advent of combinatorial capacities go hand in hand with the production of a finite repertoire of sounds which no longer have a communicative signaling function, since they are properly speaking compositional elements of symbolic tokens defined by their syntactic configurations. The stabilization of acoustic data has a number of important ramifications. It supplies the automata with a repository of sounds that can be retrieved and reproduced. But more fundamentally, it transforms fuzzy sound cues into acoustic tokens that can be used as a proto-currency for a new type of interaction wherein the communicative function of sign vehicles is replaced by symbolic tokens upon which structuring syntactic and semantic abilities can be built. With the introduction into our multi-agent system of symbols in the form of discretized and combinatorial sounds, the automata enter into the syntactic domain of language where the combinatorial relations between symbols can be manipulated to generate more complex syntactic structures capable of encoding broader ranges of relationships between pattern-governed regularities. What makes the discretization of sound a consequential structural change in our multi-agent system is that it enables the evolution of speech and cognition for the automata. It simultaneously fulfills the necessary condition for the emergence of speech and transforms the interaction between agents into an abstract system capable of generating increasingly adequate structuring abilities. Such a system can be called language, a geistic scaffold on the basis of which mind can become the unifying point or configuring factor for the structuration of the world, thoughts, and actions. Owing to their structural stability, which facilitates the sharing and reuse of acoustic tokens, the coarsely discretized sound composites qua symbols can assume specific and abstract roles in the interaction between the automata. By losing their signaling or communicative function, the discretized sounds become building blocks of symbol design, i.e., tokens which, depending on how they are exchanged between the automata, can assume different roles ranging from syntactic utterances, structure encoding expressions, to semantic vocabularies, structuring expressions. Having come into possession of sound tokens or symbols which are defined not by what they stand for but by the abstract roles they play in the interactions between the automata, the multi-agent system can transform from a communicative regime into a linguistic system through which automata 320 can increasingly structure their interaction with their environment by structuring their own interactions. The transformation of the rudimentary sound cues into a set of limited discrete sound units from which compound sounds can be constructed endows the automaton with combinatorial capacities, specifically, the generative processes of iteration and recursion. As mentioned earlier, discretization and combinatorial processes are two sides of the same coin, the symbol. We saw that the formation of a shared cache of discrete sounds qua abstract tokens was afforded by the self-organizing interaction between sound-using agents. But this was not the end of the self-organizing multi-agent interaction. With the birth of discretized units also comes the generative combinatorial processes that increasingly furnish such units with syntactic structures. With the emergence of discrete sounds as transactional tokens, the interactions between agents can further evolve by way of the basic combinatorial processes that hold between discretized symbolic units. It is now the self-organization of language, the syntactic-semantic interaction between agents, that is the real protagonist of our toy universe. The automata are simply agents or players caught up in a game which is the realization and development of language. Any structural change in this multi-agent interaction language will translate into a change in the structuring abilities of the automata. This is of course nothing but the reiteration of Hegel's insight that the supposed transcendental subject is only an agent insofar as it is suspended in the process of the self-organization of Geist, whose Dasein, or presence, is encapsulated in the self-organization of language. The most generic forms of generative combinatorial processes afforded by discretized sounds are iteration and recursion. Through these two generative processes, the concatenation of sounds can take on increasingly complex syntactic structures. Let us briefly and intuitively examine what these processes are, how they can structure the automaton's non-conceptual representings of their world, and finally how they construct syntactic vocabularies which the automata can use in their interactions. Iteration is a memoryless combinatorial process, where constituents can be repeated and combined without restriction. Take for instance the instruction chop the garlic until it is turned into a paste. To yield the desired output, paste, one does not need to memorize the history of the previous actions, choppings. As long as the action of chopping is repeated enough, one will get the paste at the end of the process. In contrast, recursion is a memory-driven generative process, meaning the performance of each action is built on the history of previous actions succinctly formulated. Recursion is the embedding of constituents within constituents of the same kind or category. 243 An intuitive example of recursion would be the instruction cut the pie into 8 equal slices. The output of this operation cannot be obtained unless each action, cutting to equal slices, is embedded in the history of the previous step. The first cut gives 2 slices, the second 4 slices, and finally in this manner, the fourth cut combined with or embedded in previous actions of the same kind yields 8 equal slices. Iteration and recursion can be distinguished according to the types of structure they generate. Simple recursion generates syntactic structures that have complex dependency relations between constituents of the same kind. Owing to the absence of embedding constraints, i.e., the combination of constituents of the same kind, simple iteration generates structures that lack dependency relations but contain constituents of different kinds. The combination of iterative and recursive operations generates structures with hierarchical dependency relations where there are generative rules pertaining to the constituents, and transitions rules between different hierarchies. In our toy universe, simple iteration of sound tokens, A3, 7, would generate syntactic strings such as A3, AFB, AP-A. Since iterative operations are memoryless in the sense that each step proceeds independently of the previous one, in their rudimentary form they can generate unlimited concatenations. When iterative operations are combined with embedding operations, i.e., the operation of embedding one constituent in another constituent, they can also encode dependency relations between constituents, as in the case of A, CT3, PT, A3T. In contrast to the previous class of strings, A3, these strings contain information regarding dependency relations between constituents. For example, depending on its formal semantic interpretation, the syntactic string of the form A3 could mean the right constituent E is dependent on the left constituent A. Finally, applying the operation of recursive embedding to sound tokens generates syntactic strings or expressions capable not only of encoding dependency relations between constituents, but also of producing new hierarchies between constituents of the same category. Since each recursive step operates on the product of the previous steps, i.e., it is a memory-driven operation, it can embed constituents of the same category within each other according to the history of their past transformations. Using this procedure, recursive embedding produces new hierarchies that encode the history of transformations between constituents of the same category. For this reason, syntactic expressions produced through recursive embedding contain a wide range of coded information regarding the structure, the type of grouping, and their intracategorical dependencies. The combined application of iterative and recursive operations to the sound tokens results in the proliferation of syntactic expressions bearing an extremely diverse range of information regarding the encoding details of dependency relations, transformations, hierarchies, and types. In this fashion, syntactic expressions can be grouped based on hierarchies of the complexity of their structure and the information they encode. This is the basic idea behind Chomsky's revolutionary contribution to artificial intelligence in the context of the theory of formal grammar or syntax. From a limited set of discrete units and through the implementation of generative processes, a nested hierarchy of syntactic complexity can be constructed where each level represents a specific class of syntactic language or grammar with its own set of production or computational rules. These syntactic structures can be classified, from top to bottom, into recursively enumerable, context-sensitive, context-free, and regular languages. Moving from the bottom, languages recognized by automata with finite memory, to the top, recursively enumerable languages recognized by automata with infinite. 323. Random access tape memories or universal Turing machines, grammars, and computational automata become successively more expressive but also more resource-consuming, syntactic vocabularies richer in their encoding capacities, and languages harder to recognize. Having access to different classes of formal grammar, K, S, and M can syntactically structure their picturing reports concerning the pattern-governed regularities of their world. For example, if we were to reproduce their report concerning the presence of a mass of fuzzy gray item in a context-free grammar, context-free syntactic expressions can be approximately described as concatenated structures of dependency relations recursively constructed from more basic block structures or syntactic expressions whose logical units do not overlap. Such an encoded report signaled via sound tokens could be presented as the following syntactic expression: sin. MSKIVRG, GBC, BCGJV. In the above syntactic report, the order of block structures and dependency relations can sufficiently encode the sequence and relations of items and occurrences so that no predicative expression, example was there, will scream, is next to the monolith, would be needed. In other words, the syntactic order of the nested brackets replaces time and location stamps T and P as well as relations conveyed by predicative expressions. Mere signs or one-to-one mapping / representing functions, as argued earlier, could not obtain this syntactic configuration, even though it is as a matter of fact built on them. It is only with the advent of symbols and their combinatorial capacities that such syntactic structures of increasing complexity become possible. If a rough analogical translation of this syntactically structured report had to be given, after adding the predicates it would be: Matata thinks based on the report given by Sue that Kanzu reports the presence of a fuzzy gray item after hearing a rustling noise. The fuzzy 324 item is now contacting the heap of black and will make a shrieking noise as it touches it. Or, in a more truncated version but with nested brackets, Sue says that Kanzu says that the monkey whose steps were heard, is now moving toward the monolith to examine it and will scream. Note the similarity of this syntactically sound but rather nonsensical sentence from our ordinary linguistic point of view with the child's unquoted but tagged world awarenesses which, as we saw, were the necessary components for the constitution of an objective worldview. Let us briefly clarify these points before moving forward. Now that the automata are equipped with formal grammar or syntax, they can encode the non-conceptual, structural or syntactic relations between causally registered invariances regarding items and occurrences. In other words, it is by virtue of their syntactic abilities that they are capable of recognizing, in the special computational sense of accepting inputs, the sequence or structural relations between causally pictured items and occurrences. Patterns and relations which the toy universe had no recognizer or syntactic language capable of encoding, would be counted as non-existent to the automata. To claim, as Sellers subtly suggests and Ruth Millikan firmly asserts, that the syntactic configuration or the structure of pattern-governed regularities, if there are in fact real patterns in the universe, is already available to mind by way of the manner in which such pattern-governed regularities are registered or pictured causally in the wiring diagram/nervous system of the automata, is to endorse a syntactic version of the myth of the categorial given. It is only with the advent of the combinatorial capacities afforded by symbols and formal syntactic abilities, the computational infrastructure of language, that the necessity of causal mappings or picturing functions for the structuration of the world can find syntactic, not semantic, structural relations sufficient for the semantic or conceptual structuring of the world. 325. The next point is that syntactic reports such as SYN consist of causally pictured items and occurrences whose syntactic configuration embodies rule-governed conceptual activities. It would be helpful to use Sellers's example of chess to clarify how the calculus of such syntactic observational reports inscribed or uttered in acoustic symbol designs, but which could equally be designated with graphic or gestural elements, embodies the rule-governed conceptual activities that disambiguate and elaborate them. A chessboard can be seen as a two-ply system consisting of a metagame and game. The metagame consists of the formally stated rules of the game chess, which are equivalent to material inferences determining the inferential role of linguistic expressions. At the metagame level, we have rules of how to set up and move the chess pieces. While these metagame rules are not per se part of the game, the players nevertheless need to be acquainted with them in order to competently play the game of chess. In contrast to the metagame, the game consists of syntactically configured or structured observational reports or pattern-governed regularities, only to the extent that the players can reliably distinguish black from white, a this-shaped piece from a that-shaped piece, and are able to syntactically encode the relations between the pieces, i.e., the position of the pieces on the chessboard, next to, behind of, in front of, diagonal to, can the game be played and the metagame rules obtain. For example, at the game level we can have a symbol design or syntactical inscription such as #A, which reads as, this such, to ti, piece of thus and so shape and color, the black king, is in a diagonal relationship with this such piece of a different color and shape, the white bishop. This chess configuration is the equivalent of the syntactically structured picturing report SYN. Moving from game to metagame, though, we have the conceptual sentence black king is checked by the white bishop. Within the metagame, there are rules or inferential transitions that tell us if the black king is checked by the white bishop, then interpose the black bishop. Shifting from the metagame back to the game, the player then moves diagonally this such piece, the black bishop, between the previously obtained configuration of this such is in diagonal relationship with one another, #AA. 326. In Sellersian terminology, the move from game to metagame, the rules or transitions within the metagame, and finally the move from metagame back to game, respectively stand for language entry transitions, perception, intralinguistic transitions, thinking, and language exit transitions, intentional action. However, a more accurate description of the move from game to metagame would be as a transition from syntactically structured symbol designs with material characteristics to semantically structured material inferences, conceptual activities. In other words, even the entry transition from game to metagame requires language, albeit language at the level of structure encoding syntactic abilities. As we saw earlier, mapping functions or non-conceptual representings causal capacities to discern and respond to pattern-governed regularities by themselves lack the robust syntactic classificatory relationships necessary in order for them to sufficiently embody rule-governed conceptual activities. Only syntactic abilities could encode such structural and classificatory relationships between material signs or inscriptions and so between the items and occurrences non-conceptually represented by them. And, as argued, such syntactic abilities require symbols in the special sense introduced above, along with the generative combinatorial processes they afford. This is why the term symbol design token was chosen instead of sign design token to denote the ability to make non-conceptual classificatory tokens that do indeed have syntactic structure encoding configurations. In addition to the ability to non-conceptually structure or classify their picturing reports by encoding them with syntactic configurations, the automata now also have the ability to deploy syntactic vocabularies in their interactions. Earlier we assumed that the automata's only medium of symbol design tokens is sound. Accordingly, in the toy multi-agent system, the parsing and production of expressions in different formal grammars or syntactic languages is achieved solely by means of the shared inventory of compositional sound tokens. Applying a selected class of production rules to acoustic tokens combined with the basic criteria of sound composition for making a phonologically permissible concatenation would produce strings of sounds that map a specific set of syntactic structures. These properties represent the distinct level of syntax. 327. To which that expression or vocabulary belongs. Any string that projects such properties or structures would be recognized by the automata as a syntactic utterance in the language that produces such properties and structures, with the caveat that the automata would have the ability to recognize or parse the expressions of that syntactic language. For example, if the automata are capable of deploying syntactic vocabularies in the regular language of the Chomsky hierarchy, any string of sounds or symbolic combination from the external environment or another artificial multi-agent community that matches the formal properties and the structure of a regular Chomsky language can, in principle, be recognized by our automata as an utterance in their syntactic language. That is to say, the automata can potentially recognize or compute any string of sounds, gestures, or inscriptions whose syntactic relations map onto the syntactic relations of the language they can parse. Following Brandam's example of the Laughing Santa 244, imagine that the automata were only able to deploy syntactic vocabularies laughing strings in the regular language of the Chomsky hierarchy using just 4 sounds H, O, A and E. We can call such automata automatic laughing bags. As automatic laughing bags, the automata can recognize and produce syntactic vocabularies or laughing strings in the form ha-ha, ho-ho, ha-ha-ho-ho-a-hell. The algorithmic ability to deploy such syntactic vocabularies or laughing strings can be modeled on a finite state machine. To make a laugh, the automatic laughing bag starts with state 1. If the first sound is not H, the laughing bag does not move forward to the next state. If the sound is A, it issues an A sound and moves to state 2. In state 2, if the sound is not A, E or 0, it remains stuck again. But if it is A, E or 0, it emits one of these sounds and moves to state 3. In state 3, if there is a terminating sign slash, it moves to state 4 and makes the shortest laugh, ha, he, ho, ending the process. But if it chooses to make a longer laugh, i.e., if there is an A sound instead of it moves back to state 2 and repeats the process for any amount of time until it reaches the terminate command /. Any string that reaches the final state would be an item of laughing bag vocabulary, recognizable by all automatic laughing bags. See the following diagram for the state transitions of the recognizer automaton and the accompanying flowchart containing the instructions for producing a laugh token within a finite repertoire of discrete sounds. 329. Automatic laughing bags. In the hierarchy of syntactic complexity, practices or abilities sufficient to deploy a vocabulary i.e. what one has to do in order to recognize and produce something in a syntactic language, and vocabularies sufficient to specify those vocabulary deploying abilities, i.e., what one has to say to specify a set of practices or abilities required for making a vocabulary in a syntactic language, are both algorithmic abilities. They allow higher syntactic complexities, languages with more expressive powers and higher structure encoding capacities, to be algorithmically bootstrapped from lower syntactic complexities. 245. In this fashion, using lower sufficient vocabulary deploying practices or abilities, PV sufficiency, and sufficient practice specifying vocabularies, VP sufficiency. 246. The automata can, in principle, construct vocabularies of higher syntactically complexity which are at once more expressive and stronger in terms of their computational powers and their capacities to encode structures. So far the automata have acquired exchangeable symbol design tokens whose syntactic configurations, systematic relationships, and material characteristics express non-conceptually facts about how things are. The automata can assign rudimentarily classifying labels made with syntactic beeps and clicks to this, such as of items, as a matter of reliable differential responsive dispositions. Thus, for example, in the presence of this such bulbous pile of green, K utters beep beep click click. And in the presence of the mass of fuzzy gray moving up on the pile of green, or some other more involved occurrence among stuffy this such as, it makes again in such sounds a well-formed syntactic sentence that configures the syntactic relations between such labels and their corresponding this such items. We can say that the automata have something like proto-thoughts of the form do, or don't do, actions of kind a when in circumstances of kind c, what sellers may call rehearsing intentions, or, in this case, proto-intentions. 247. Moreover, the automata are now in possession of algorithmic syntactic abilities through which they can construct more complex structure encoding abilities, and recognize and potentially compute more intricate patterns. There is no reason to doubt that the automata of our toy universe may read and write more expressive syntactic vocabularies and compute more complex syntactic sentences, with higher structure encoding capacities, than our base syntactic capacities. But what they do not have is the semantic structuration of the diverse relationships between syntactically pictured reports. They do not have inferential or rule-governed intralinguistic transitions to conceive, i.e., bring into conception, such reports, to elaborate the relationships between such reports based on their material incompatibility and consequence relations, and, if necessary, to repair or revise such reports. In other words, they do not have the objective reports that the fully fledged language using Su and Matata had, because they do not have propositions whose conceptual contents are determined by their inferential roles, since they have not yet achieved the practical mastery of inference. Thoughts are only thoughts to the extent that they stand in inferential relations to one another, that is to say, in so far as they are individuated by their inferential articulation in a public language. Intentional relations, thinking abouts, require semantic relations, and semantic relations require a public language as the engine and vehicle of their realization. Ultimately, what our automata do not have is a semantic space defined in terms of a public language they can be plugged into and, through participation in it via mastering the practices it entails, generate a hierarchy of semantic complexity. Ascending this semantic hierarchy is tantamount to practical mastery of the use of vocabularies expressing the right kind of concepts of different grades and roles. These are concepts that let us make explicit, put into judgeable, thinkable, assertable, propositional form the inferential relations that articulate the space of implications that is the context and horizon within which alone what we do acquires the significance of rational, Discursive consciousness of what we respond to. Point 248. Intentional assent, or the complexity of thinking thoughts, demands a semantic assent, that is, a hierarchical complexity of both different grades of concepts, i.e., inferentially articulated contents, and the practical know-how to use or apply concepts correctly. In ascending the hierarchy of semantic complexity, the automata attain semantic self-consciousness. They become discursively aware of how things are by thinking about thoughts through thinking about concepts that inferentially articulate those thoughts, and thereby the things thought of. However, the revolution of syntax in our toy universe, as we shall see in the next chapter, has also another consequence as significant as if not more than the buttressing of semantic capabilities. But what is this consequence? It is what we might call Carnap's vision of language in general as a calculus, or, in reference to the work of Steve Awade and André Carus on Carnap, the picture of language as an unbound ocean freed at last both from Wittgenstein's prison, the picture theory of language, and from the Kantian straitjacket, subordination of the logical and formal dimension to sensible intuition. Point 249. To put it concisely, this is a picture of language as a calculus of general syntax. In Carnap's own words, by a language we mean here in general any sort of calculus, that is to say, a system of formation and transformation rules concerning what are called expressions, i.e. finite, ordered series of elements of any kind, namely, what are called symbols. In what follows, we will deal only with languages which contain no expressions dependent upon extralinguistic factors. Two sentences of the same wording will have the same character independently of where, when, or by whom they are spoken. Point 250. Seeing language as a calculus, or as the boundless system of formation and transformation rules in the realm of symbol design, is not to reduce language to calculus. Such a view of language does not entail the rejection or downplaying of the perceptual, representational, social, and cultural aspects of language. The point is that expanding the scope of language, what it is and what it can do, cannot be effectuated in earnest if the structure of language is subordinated to prior representational, social, or cultural considerations. To understand language as a general calculus in the way Carnap envisioned in the logical syntax of language is to finally blur the line not only between syntax and logic but also between language and computation. It might be objected that such a picture of language sacrifices the semantic dimension. Not necessarily. In fact, to treat semantics as irreducible to or fundamentally distinct from syntax is to regard semantics as a deus ex machina of some sort, that is, to see meaning as the miracle of language. Surely, it is not the case that semantics can be invariantly reduced to syntax, but it is indeed reducible to syntax under the right conditions. These right conditions, as we will review in the next chapter, signify the interactionist view of syntax through which semantic complexity emerges immanently through the confrontation of syntactic processes or symbolic chains. Therefore, we can say that Carnap's logical syntactic view of language is not anti-semantic. It concerns the semantic in disguise. Point 251. Disenthralling language from established semantic rules or representational concerns is not equal to forgetting the semantic. It is rather an unprejudiced way to imagine more generalized languages capable of capturing ever richer semantic relationships. If we consider structure as the dimension of mind, namely, language and logic, we cannot broaden the intelligibility of reality or postulate new kinds of worlds populated by new intelligences and facts of experience without broadening the scope of language and logic. And we cannot expand language and logic without taking the prospects of language as a calculus of forms where the boundaries of syntax, logic, and computation become porous seriously. Language, as the combined forces of logic and computation, is the ultimate medium of concrete world building. But we cannot build new worlds, discover new sectors of reality, or make new forms of intelligence without new ways of language building, the design of which will require that we liberate the picture of language, and for that matter logic, as organons from any limitations set in advance by the representational functions and semantic values of language or the correct application of logical laws to intuitions, a la Kantian transcendental logic. It is this idea of unrestricted world building as arrested by the boundless conception of language building that typifies intelligence not as a passive receiver of an external reality but as the very exemplification of enriching and engineering reality, that which progressively postulates itself as a new inhabitant of new or different kinds of structured worlds. Asterisk. Before moving on to the next chapter, which is the last stop in our thought experiment, it would be helpful to provide a rough outline of the issues we have navigated so far and where we are headed. We began with a picture of mind whose function is structuring or self-conception in accordance with an objective world. Mind as the organ of structuration was elaborated via a family of fundamental correspondences or dualities, as differentiated from dualisms: intelligence and intelligibility, theory and object, structure and being, and so on. In addition, we surveyed the relation between language, logic, and mind. The conclusion was that we cannot know what intelligence is or what it can become without inquiring into the structuring function as that upon which all our descriptions. 336. Regarding what counts as intelligent or general intelligence are modeled, lived, in other words, thinking about intelligence or Geist, what it is now and what it will be, is a matter of investigating and renewing the link between mind and world, structure and being, theory and object. The investigation and renewal of this link is the very definition of concrete self-consciousness as a task. And the first step in this task is nothing other than investigating the conditions necessary for the realization of mind as that which has a concept of itself in an objective world. Such necessary conditions were introduced as enabling constraints for having thus and so universal capacities which we not only associate with general intelligence but must also employ to model any form of intelligence. We subsequently started our examination of such enabling or positive constraints in the framework of an extended thought experiment after disputing the unconstrained conceptions of intelligence and assessing which models or paradigms are best suited for conducting such an inquiry. The investigation into such constraints took two distinct but interconnected trajectories at the intersection between mind and objective world, an in-depth analysis of the necessary enabling constraints or conditions for the realization of mind based on our own current theory-laden and scientifically informed self-image as minded subjects, and 2. A critique of transcendental structure to determine the degree to which such necessary constraints, what they are and what we take to be their essential characteristics, are fraught with or distorted by cognitive biases originating from the local structure of our experience and psychologistic residues. Properly understood, the latter trajectory is tantamount to the full-scale Copernicanization of the transcendental subject itself, and therefore the unmooring of the conceptions of mind and intelligence. Yet arriving at a conception of intelligence that is of nowhere and no when is only possible by following these trajectories. Following these two trajectories, then, we looked at the initial necessary constraints upon the order of appearances, space and time as forms of intuition. Next, we inquired in the conditions necessary for having thoughts and objectivity or objective validity. The latter brought us to the question of syntactic complexity and semantic complexity as the dimensions of structure. At the intersection between language, logic, mathematics, and computation. Having looked at the necessary conditions for syntactic complexity in this chapter, we can now move on to the question of semantic complexity or semantics in general. In the next chapter, therefore, we follow this line of inquiry, starting from the bridge between syntax and semantics and in the process uncovering a picture of language behind our ordinary natural languages, one which is no longer burdened by the local and contingently constituted biases entrenched in the structure of natural languages. 338. To ask how our automata can transit from their base structure encoding syntactic abilities to semantic structuring abilities is fundamentally to ask how syntax can be bridged to semantics. Building this bridge is not straightforward, insofar as no amount of algorithmic base syntactic abilities can generate semantic abilities. Yet to claim, as John Searle does, that syntax by itself is not sufficient for semantics is a recipe for the inflation of what meaning is, along with a myopic interpretation of what syntax is and what syntactic expressions do. This is of course a claim encapsulated in the Chinese room thought experiment, an argument that simultaneously presupposes a potentially mystifying account of meaning, a peculiarly anemic interpretation of syntax, and an outmoded understanding of the relationship between syntax and semantics. 252 Syntax, under the right conditions, is indeed sufficient for semantics, and meaning can be conferred upon syntactic expression if such conditions are satisfied. These conditions are what the inferentialist theory of meaning, as a species of social pragmatics or the use theory of meaning, attempts to capture. It argues that meaning is ultimately, at its most basic level, the justified use of mere expressions in social discursive linguistic practices, and that what counts as the justification of an expression is what counts as its meaning. While syntax by itself does not yield semantics, it does so when coupled with interaction. In this sense, pragmatics, at least in the sense defined by Brandam's inferentialist pragmatism, can be understood as a bridge between syntax and semantics. Broadly speaking, semantics, content, is concerned with what is said, while pragmatism, use, is concerned with what one is doing in saying it, i.e., discursive practices or abilities that count as deploying a vocabulary, conferring or applying meaning. More precisely, semantics asks what it is that one believes, or knows, claims, when one believes that p, a content, whereas pragmatism asks what it is that one must know how to do in order to count as producing a performance that expresses that content. Leaving behind the representational account of meaning and meaning as denotation, inferentialism, as a species of pragmatism, treats the meaning of linguistic expressions in terms of their inferential relations embedded in social discursive practices. To this extent, the capacity to know, believe, or mean something rests upon certain practical know-how, i.e., pragmatism, the practical mastery of inferential roles. In the inferentialist semantics normative pragmatics framework, semantics can be said to concern the meaning-conferring inferential roles of syntactic expressions in the context of social discursive practices or linguistic interactions. Within this setup, the noises or behaviors of interlocutors can only count as saying or claiming something if said interlocutors know what to do in accordance with rules and following some standards or norms such that they can draw inferences from each other's claims, using such inferences as the premises of their own claims and reasoning. Here, syntactic expressions as items of language assume semantic value or meaning when they are incorporated into the interaction of practitioners of discursive practices that give inferential roles to such utterances. These are practices that adopt or attribute normative statuses, commitments, and entitlements that stand in consequential relations to one another. For example, endorsing the belief or claim "this is red" entitles one to the belief that this is colored but precludes the claim that this is green. Thus, from this point of view, one must know what sort of performances must be carried out in order for one to count as endorsing a belief or claiming that p, and what must be done in order to track what follows from such endorsements and claims. To assert or judge "this is red," one must not only be able to react as a matter of RDRD, reliable differential responsive disposition, see Chapter 5, to the presence of this such item, one must also have the practical know-how regarding what must be performed to inferentially connect such a state, expression, or noise, red to other states or expressions, thus conferring conceptual content upon them, i.e., red as a concept qua an inferentially articulated content. Consequently, one can grasp or understand the content of the concept red or any other concept by grasping the significance of the pragmatic performance of committing to the claim "this is red," a speech act, in terms of the difference it makes to other interlocutors' commitments and entitlements to commitments. That is to say, linguistic discursive practices can be defined in terms of tracking or keeping the score of other practitioners' or interlocutors' commitments and entitlements, asserted claims, and what follows from them or does not. In this sense, for an interlocutor, the significance of a performance or a speech act, "this is red," is ultimately a matter of the way in which it interacts with other interlocutors' commitments and entitlements. This interaction requires that the deontic context of such a performance be updated, and in doing so, the previous context is given a score. To use a simplistic example, when K asserts this is red, it is entitled to this is colored. But when S asserts this is red mixed with blue, K, having recognized the shade of blue, RD plus the inferentially articulated concept blue, is required to acknowledge the force of S's assertion with regard to the consequential scorekeeping relations between its commitment and entitlement, and to update, keep, revise, or discard them. This is not red, this is purple, and this is colored. The content of the concept can then be characterized in terms of this updating function. Therefore, we can say that grasping the content of a concept and grasping the concept of reasoning as certain, i.e., objective and linguistic, practical know-hows are interdependent. Briefly put, reason as the articulation and elaboration of the concept is a doing, and as such there is no good justification for refusing to view reason in terms of the algorithmic elaboration or decomposition of abilities which can be realized by different kinds of information processing systems. In this interactive framework, the assertion that P can no longer be thought as a fully formed propositional content that is either true or false, but instead is thought as a conditional assertion whose meaning and truth can only be decided when it is put into interaction with queries and counterclaims which test and challenge it, a game in which, by making a move or defending a commitment that P, one is prohibited from making other moves. This move is akin to a hypothesis whose construction involves processes of verification or being tested by other strategies or agents, i.e., other moves made in the game. What is interesting about Brandam's inferentialist pragmatism is that it gives a picture of natural language not simply as a symbolic medium but as a rule-governed framework inseparable from the interaction of its users, an interaction in which all necessary, non-inferential, capacities of agents are integrated. One might object that Brandam's pragmatism is susceptible to the same charge levied against traditional pragmatism, namely that one must know all the rules of language in order to function, to say or claim something contentful. As he shows in his tour de force between saying and doing, however, this is absolutely not the case. Normative scorekeeping pragmatics, the game of giving and asking for reasons, can begin with a minimal set of rules, and it is only in the context of interaction between interlocutors that more rules can be established, their know-how mastered, and their form made explicit. Therefore, once deepened, Brandam's version of analytic pragmatism represents, to appropriate Jean-Yves Girard's term, an emergent logic of rules. Brandam's pragmatism is thus a true species of discursive rationality in the sense that discursive rationality, even at the level of mastering the know-how of claiming or asserting something, takes time. However, probably the weakest link in Brandam's pragmatism is the way in which the sociality of social linguistic discursive practices is defined. This sociality is merely asserted, but hardly plays any major role in how meaning-conferring discursive practices are logically modeled. Sociality then becomes a substantive characteristic of discursive practices rather than the very logical condition of language and the non-substantive order of thinking. Absent the explicitation of the role of sociality as a formal condition, the concept of sociality risks becoming an inflated metaphysical posit that results in a concept of rationality unconscious of its insufficiency for change at the level of concrete social practices. The necessity of reason, language, rational discourse, and an understanding of the machinery of conceptual activities for social change can then be passed off as their sufficiency for concrete change. Short of the consciousness of this necessiticum insufficiency, the very discussion of reasons and conceptual activities leads to a socially liberal and philosophically quietist stance. Therefore, Brandam's thick notion of sociality converges on a Habermasian rationality persistently unconscious of its insufficiency. To this extent, using a thick notion of sociality to define linguistic discursive practices becomes just as precarious as using the right-wing Sellersian's thin notion of agency and normativity. At this point, we should admit that we have a foggy and faulty notion of sociality which prevents us from grasping the role of interaction, and undermines the program to bridge from syntax to semantics while emphasizing language and sociality as a constitutive condition. Our notion of sociality may be defectively indeterminate, but that is exactly why we should reinvent the notion of sociality as an interaction that can be elaborated logically and computationally. The articulation of sociality as a formal condition is the first step that must be taken in order to unbind rational capacities as well as to rescue the nebulous concept of reason from deep-seated dogmas. The former is a necessary albeit basic and not adequate move that must be made if we are to think about substantive sociality and social norms. Therefore, to re-emphasize the role of sociality in language and thinking as the bridge between syntax and semantics, we must redefine this index of sociality as a formal condition best captured by the logico-computational concept of interaction. In this sense, interaction is a sufficient condition for building the syntax-semantics interface. The question is now as follows. What kind of interaction must the automata have in order to move from base syntactic abilities to fully fledged structuring semantic abilities? To answer this question, however, we need to answer a more general question: what is interaction as a distinctly computational notion? According to the classical Church-Turing computability thesis, computation can be modeled on a mathematical function. The machine receives input, it undergoes a sequence of state transitions, moves or legal runs, and yields an output. During the computation, the machine shuts out the environment and accepts no further input until the initial input is processed. In this form, computation can be represented as a logical deduction where to compute means the same as to deduce steps from an initial configuration. Like deduction, the process of computation can then be characterized in terms of how the output, conclusion, is logically contained in the input, the premise, or how the output/conclusion is implied by the input/premise. But if this is all that computation is algorithmic deduction, then what exactly is gained by it? Computation runs into the same problem that deduction leads to, namely the riddle of epistemic omniscience, according to which the total knowledge of an agent can be said to be deductively closed. Cap A, P dash plus Q, caret C. Which says that if the agent A knows K, the proposition P, then it knows all its logical consequences Q. While such a verdict is absolutely sound and valid in some classical logic heaven, it has no ground in reality. A corresponding computational equivalent of deduction's problem of epistemic omniscience is the classical denotational semantics of programming languages, where all that is required to provide meaning to the expression of a language, i.e., the meaning of the program, or to know what the program does, is to know the given structured sets of data types, domains, and the interpretation function that maps those domains to one another. Here, the puzzling situation is that 344. Computation is supposed to yield new information, whereas the classical paradigm suggests a closed logical system wherein the output information is nothing but the input plus a machine that deduces steps from it. From an information theoretic point of view, no new information is added by computation, and from an epistemic point of view no knowledge is gained by computation. What the classical account of computation presupposes but does not incorporate as its intrinsic dimension is that which provides the input and consumes the output, namely, the environment. The system or machine becomes the model of what computes, at the expense of keeping the environment in the background. The environment is merely represented as an average behavior, rather than something that dynamically and actively interacts with the system. But it is only by highlighting the role of the environment that the system's or machine's function input-output mapping can coherently make sense. Moreover, it is only in the presence of an environment, another system, machine, or agent, that computation can be understood as an increase rather than mere preservation of information, hence avoiding the riddle of epistemic omniscience. From this perspective, the environment is no longer a passive ambient space but an active reactive element to which the system responds by accepting input from it and yielding output which the environment then consumes. In view of the role of the environment in the input-output mapping, the question of computation, rather than being couched in terms of what is a computable function, shifts to the question of how the computation is executed. By bringing the howness of computation into the foreground, the question of computability turns into the question what is computation, that is, it now concerns the interaction or confrontation of actions between machine and environment. With the understanding of interaction itself as computation, the system environment, or player-opponent, machine network, dynamics can be modeled as a so-called interaction or simply general game. The interaction game differs from game-theoretic account of games in a number of significant ways. It does not require procedural rules or rules that dictate how the game should proceed or what moves/actions should be performed in a given situation. Rules naturally emerge in the context of the interaction itself. Furthermore, unlike a game-theoretic conception of the game, an interaction game is devoid of both predetermined winning strategies and payoff functions that map the strategy profile of each player to its payoffs or rewards. In this respect, the generality of interaction makes games unifying themes in the study of structures, information, contents, and behaviors. 253 From a technical perspective, interaction games capture the fundamental correspondences between computational behaviors, logical contents, and mathematical structures, that is to say, the so-called computational trinity. 254 In this sense, interaction games are generalizations of the Brouwer-Haydn-Kolmogorov interpretation, where the notion of construction can be interpreted in terms of computing programs, logical proofs, and composition of categories as mathematical objects. In Brouwer's terms, the notion of construction can be broadly understood as a mental construct capable of verifying the existence, denoted by an existential quantifier 3, of an object that falls under it, such that the construction of a mental object, Gegenstand rather than object, can be said to be the proof of its existence. 255. 253 Treating games as unifying themes can perhaps be traced back to the work of Stanislaw Ulam on using the logico-computational notion of the game to study all mathematical situations, as expressed in his slogan Gamify, Paisis, from the Greek regiti, to play, everything. C.S. Ulam, A Collection of Mathematical Problems, New York, Interscience, 1960. 254 The doctrine of computational Trinitarianism holds that computation manifests itself in three forms: proofs of propositions, programs of a type, and mappings between structures. These three aspects give rise to three sects of worship: logic, which gives primacy to proofs and propositions; languages, which gives primacy to programs and types; categories, which gives primacy to mappings and structures. The central dogma of computational Trinitarianism holds that logic, languages, and categories are but three manifestations of one divine notion of computation. There is no preferred route to enlightenment; each aspect provides insights that comprise the experience of computation in our lives. Harper, The Holy Trinity. The subgame A. The symbol stands for linear implication, where the implication is resource sensitive. The environment is a resource for the task of the system, a computational problem, and by consuming this resource the system performs a task to yield an output which is now a resource for the environment. The game A equals B can be intuitively thought of in terms of access protocols between a server and a client, or machines on a network. The server A-degree B acts as a server of type B that provides data of type B if it has access exactly once as a client to server A, which provides data of type A. The client of AB will therefore act not only as a client of type B but also as a server of type A, which provides the input or resource from A. 259 The Garnet-degree B is characterized in terms of the game's four-tuple. MA-B equals MA plus MB. A-degree B equals AA, AB / such that for move to AA, 2, equals T when AA, 2, equals 1, and 1 when AA, 2, equals 1. T-S equals SGMAIB, where the first move in PA-B must be performed by 1 in B, and the opening moves in A are labeled as by the function AA. A-B *A*M if the initial move requires no justification/permission, or else \A-B equals M*A*Bn. In this setting, if we were to represent a computational problem, example computing 7I plus L in the classical church-Turing paradigm, this game could be diagrammed as a tree consisting of nodes and branches. At the top of the tree, we have a game played by the machine T, represented as the first node that ramifies to the first level branches, which are 1 labeled, corresponding to inputs provided by the environment, and leading to the second-level nodes of the tree, which are games played by the environment 1, T1, _L 2 plus 3, in the same vein, the second-level nodes lead to second-level branches, which are T-labeled, T1, T2, T3, and correspond to the output. The second-level branches lead to the third-level nodes, which represent the winnability of games played alternatively by the environment and the machine, _LT plus or minus T. Such a two-step game would count as computation in terms of input-output mapping functions. More general interaction games, i.e., games with more than two steps or ordered two-level branching, represent computational behaviors that are not exactly functions in the classical mathematical sense. This is in fact the single most significant underlying claim of the interactionist approach to computation, that not all computational behaviors or tasks can be modeled on functions in the mathematical sense. Rather than input-output mapping functions performed by a machine, behaviors are evolving interactions between machine/system and environment. Therefore, realizing behaviors is not simply a matter of simulating an observable behavior by means of a system's function, a simulator, as a behaviorist or a traditional functionalist would claim, but of reenacting the interaction between system and constraining environment. Such an interaction is modeled on a game that is not restricted to two steps, i.e., a game that is played on subgames and their branches. In view of the minimal interactional or game constraints introduced above, it would not be difficult to imagine how the relaxation of existing constraints or the addition of new constraints to the game could result in more complex, computational, behaviors. Additional playing constraints can be generated as the game or interaction progresses, thus allowing the adoption of new strategies by players, i.e., rules by which the game can be played, cf. the notion of open harness introduced in Chapter 1. Alternatively, some existing constraints can be relaxed or additional interaction operations can be added to enrich the semantics of interaction, hence generating more complex computational behaviors expressed by different compositions of strategies. For example, the constraint of responding to the latest move of the opponent in the subgame can be suspended and an interaction feature, operation, added so that both players can be free to play their opening moves in subgames. An oversimplified but nevertheless helpful example of such a modification can be expressed in terms of the everyday use of personal computers. Traditionally, strategies in games are understood as functions from positions, histories of past interactions, to moves or actions. However, if the strategy of the computer was simply a function from positions to moves, it would have then been required to check the entire ever-increasing history of interactions of moves and counter-moves. The task of the computer would then over time run into complications such as the exponential slowing of speed, time to process, and the increase in space or memory needed to respond to the next counter-move. But neither is it the case that the computer just responds to our last key punch, since it is capable of storing, accessing, and scanning histories of past interactions. 21.0 Interaction as computation, in this sense, can be seen as pertaining to possible compositions of strategies which, depending on how the semantics of interaction is interpreted, i.e., the interpretation of constraints and operations involved in the interaction, would cover richer computational behaviors not limited to the computation of functions. Furthermore, in the interaction schema, computational criteria such as sequentiality and synchronicity, sequentiality of moves and synchronicity of interactions are no longer dominant. In fact, sequential synchronic games or computations are special cases of true concurrent asynchronous games as the most general category of interaction games. Such a general category of games G can be represented by the so-called asynchronous copycat strategy. 261.602 G as represented by a copycat is nothing but the game or interaction itself independent of the order of the actions performed by agents, processes, or players involved in the interaction or playing of the game. In other words, in G, games between players can be played out of order or in partial order and the result would still remain the same. From an information theoretic standpoint, the notion of copycat stands for the conservation of the flow of information. Whereas information is conserved for the total system, there is information flow and information increase relative to interacting subsystems. Copycat strategies and their compositions enable the development of an explicitly dynamic theory of information processing. Let us clarify, by means of intuitive diagrams, the copycat as the encapsulation of the general category of games, or interaction itself. G can be defined as the identity map or morphism of the game itself G'. In Church-Turing computability terms, this can be interpreted as the identity function that maps natural numbers to natural numbers n equals n. Then n would be a general game on which many games computable functions over natural numbers can be played. Defined as such, G is represented by a copycat, or general strategy of interaction. Imagine G is a universal game board which might consist of many other game boards or subgames. On the game board C, there are two teams of players, agents, or processes A and B, each with their respective base or domain of moves and distributed in an asynchronous fashion over the board. The actions or moves in each team can be synchronically and sequentially ordered. But with respect to the actions or moves of the other team, they are asynchronous, i.e., either out of order or in partial order. The cells of the game board are labeled in accordance with the player's base. As possible actions in the game, the moves, represented by arrows, performed in each team's base can be thought of as legal transits from one labeled cell to another. Such transits could be classically understood as functions or state transitions, where the previous cell traversed by a move is an input for the next cell in that move and, correspondingly, the next cell an output for the previous cell. Now enters the copycat, an agent who beats both A and B by copying one team's plays and running them against the other team, or copying moves from one game board to another and vice versa. It copies A's move and plays it against B by changing its labeled cells from A's base to corresponding labeled cells in B's base, and vice versa for team B. That is, the copycat plays moves in the domain A in the codomain B, and plays moves in domain B in the codomain A. In this scenario, whichever team wins, the copycat wins. With the understanding that winnability in interaction games is tantamount to computability, winnability is not essential for the copycat, since if both A and B lose, i.e., incomputability as a lost game, there would be no win for the copycat. The true significance of the copycat is that it represents the flow and increase of information under any particular interactive configuration, i.e., distributed in space and time, for a set of agents or processes. Even if the teams involved do not synchronically react to one another, the copycat captures their moves as a general interaction. Moreover, from a logico-computational perspective, the copycat reveals the surprising power of copying information from one game board or place to another, through which we can arrive at an emergent view of logics and language as simple or composite interactions or copycat strategies. As an agent that incarnates the universal category of the game or the interactive logic of computation, the copycat shows that sequential synchronic computation is a subset of asynchronous concurrent computation, just as the first-person game is a subset of the two-person game, I-thou game. In a nutshell, interaction in its most general form is the generalization of computation as such. There is no process that does not speak to another process, irrespective of how such processes react to one another. The logical equivalent of the copycat as the agent of interaction, game, or computation is a dialogue, and dialogue is the engine of semantics. There is no monologue or private thought without a dialogue, an interaction within and over language, and correspondingly there is no dialogue without an information gain or new knowledge made possible by an interaction between the system and its environment, an agent and its dual, a thesis and a counter-thesis. Refounding logic on generalized interaction, the deepest computational phenomenon, allows us to understand precisely what form of logico-computational interactions the automata must exhibit in order for them to cross the bridge between syntax and semantics. In other words, such an interactive view of logic as formulated particularly in proof theory provides the Logico-computational framework through which the minimal generative syntax of the automata can be transformed into concrete syntax, where syntactic strings are comprised of structured units and relations similar to the various syntactic constituents within variable roles that make up the structure of our natural language sentences. On another level, the interactive view of logic presents a logico-computational framework within which role-based syntactic constituents can be handled as logical expressions which subsequently, through dialogical interaction, find semantic values or meanings. In this sense, meanings can be characterized as invariants with regard to the interaction processes. In short, the interactive conception of logic can simultaneously specify the type of interactions necessary for the formation of concrete sentential syntax, and the interactions necessary for meaning-conferring dialogues. The syntax-semantics interface is built upon interaction. To provide even a rudimentary account of such frameworks for bridging syntax and semantics would entail an introduction to recent developments in logic, mathematics, and theoretical computer science, itself a gargantuan task that would surely distract us from the main themes of this book. 262 To this extent, at the risk of misrepresentation, only the most basic intuitive ideas behind the interactive logical framework of the syntax-semantics interface will be presented here. Traditionally in proof theory, the meaning of a proposition has been understood as the proof of that proposition or the verification of it, provided that the process of verification is grounded on the notion of proof. 263 The meanings expressed by linguistic statements are then laid out not by means of truth conditionals but by means of the construction of proofs that are syntactical in nature. In classical proof theory, the meaning of the sentence is the set of its proofs, or, more accurately, knowledge of the conditions of its assertion, which then counts as knowledge of what would count as a proof, and hence the meaning of the sentence. Thus, in determining the meaning of a sentence, priority is given not to the notion of truth but to that of proof. Or, from the viewpoint of the pragmatic theory of meaning as use, the meaning of a sentence or formula is not explained by their truth, but by their use or consequences in a proof. VAAVB high 3 cut ha h cut. Notice that on the left and the right side of the consequence relation or turnstile can be seen as a duality, proofs of A versus proofs of A1, where the linear negation 1 signifies the switching of roles or, in this case, swapping the place of A with regard to the turnstile. The shortcoming of the classical meaning as proof paradigm is that the proof is conceived statically and monologically, in tandem with the mathematical interpretation of classical logic. For example, in this classical setup, given a formula, a logical expression, a piece of syntax, a proposition, if one has the proof the meaning of A, then one also has the meaning of IA. That is to say, having the proof implies having the DIS proof by way of the classical negation that negates some unspecified or arbitrary iteration of A. But with the introduction into classical proof theory of interaction, i.e., dualities as the interchange of roles rather than as classical negation, the proof or determination of meaning takes on a different form. The meaning of A can only be determined through interaction or dialogue with its counterproof or refuter, and vice versa. The determination of meaning or proof can only be achieved by stepping outside of the static monological framework of proof into one where proof is the interaction between a prover, player, and a refuter, opponent, A and IA, or, more precisely, A and the model of IA. Just like the environment in the classical Church-Turing paradigm of computation, where it was presupposed but never explicitly asserted, in the hiding copycat if is tantamount to computability, winnability is not essential for the copycat since if both A and B lose, i.e., incomputability as a lost game, there I would be no win for the copycat. The true significance of the copycat is that it represents the flow and increase of information under any particular interactive configuration, i.e., distributed in space and time, for a set of agents or processes, even if the teams involved do not synchronically react to one another. The copycat captures their moves as a general interaction. Moreover, from a logico-computational perspective, the copycat reveals the surprising power of copying information from one game board or place to another, through which we can arrive at an emergent view of logics and language as simple or composite interactions or copycat strategies. As an agent that incarnates the universal category of the game or the interactive logic of computation, the copycat shows that sequential synchronic computation is a subset of asynchronous concurrent computation, just as the first-person game is a subset of the two-person game, I-thou game. In a nutshell, interaction in its most general form is the generalization of computation as such. There is no process that does not speak to another process, irrespective of how such processes react to one another. The logical equivalent of the copycat as the agent of interaction, game, or computation is a dialogue, and dialogue is the engine of semantics. There is no monologue or private thought without a dialogue, an interaction within and over language, and correspondingly there is no dialogue without an information gain or new knowledge made possible by an interaction between the system and its environment, an agent and its dual, a thesis and a counter-thesis. Refounding logic on generalized interaction, the deepest computational phenomenon, allows us to understand precisely what form of logico-computational interactions the automata must exhibit in order for them to cross the bridge between syntax and semantics. In other words, such an interactive view of logic as formulated particularly in proof theory provides the 357 logico-computational framework through which the minimal generative syntax of the automata can be transformed into concrete syntax, where syntactic strings are comprised of structured units and relations similar to the various syntactic constituents within variable roles that make up the structure of our natural language sentences. On another level, the interactive view of logic presents a logico-computational framework within which role-based syntactic constituents can be handled as logical expressions which subsequently, through dialogical interaction, find semantic values or meanings. In this sense, meanings can be characterized as invariants with regard to the interaction processes. In short, the interactive conception of logic can simultaneously specify the type of interactions necessary for the formation of concrete sentential syntax, and the interactions necessary for meaning-conferring dialogues. The syntax-semantics interface is built upon interaction. To provide even a rudimentary account of such frameworks for bridging syntax and semantics would entail an introduction to recent developments in logic, mathematics, and theoretical computer science itself, a gargantuan task that would surely distract us from the main themes of this book. 262 To this extent, at the risk of misrepresentation, only the most basic intuitive ideas behind the interactive logical framework of the syntax-semantics interface will be presented here. Traditionally in proof theory, the meaning of a proposition has been understood as the proof of that proposition or the verification of it, provided that the process of verification is grounded on the notion of proof. 263 The meanings expressed by linguistic statements are then laid out not by means of truth conditionals but by means of the construction of proofs that are syntactical in nature. In classical proof theory, the meaning of the sentence is the set of its proofs, or, more accurately, knowledge of the conditions of its assertion, which then counts as knowledge of what would count as a proof, and hence the meaning of the sentence. Thus, in determining the meaning of a sentence, priority is given not to the notion of truth but to that of proof. Or, from the viewpoint of the pragmatic theory of meaning as use, the meaning of a sentence or formula is not explained by their truth, but by their use or consequences in a proof. HAAHBVB cut HAHH cut. Notice that A on the left and the right side of the consequence relation or turnstile can be seen as a duality, proofs of A versus proofs OL for 1, where the linear negation 1 signifies the switching of roles or, in this case, swapping the place of A with regard to the turnstile. The shortcoming of the classical meaning as proof paradigm is that the proof is conceived statically and monologically, in tandem with the mathematical interpretation of classical logic. For example, in this classical setup, given a formula, a logical expression, a piece of syntax, a proposition, if one has the proof the meaning of A, then one also has the meaning of IA. That is to say, having the proof implies having the DIS proof by way of the classical negation that negates some unspecified or arbitrary iteration of A. but with the introduction into classical proof theory of interaction, i.e., dualities as the interchange of roles rather than as classical negation, the proof or determination of meaning takes on a different form. The meaning of A can only be determined through interaction or dialogue with its counterproof or refuter, and vice versa. The determination of meaning or proof can only be achieved by stepping outside of the static monological framework of proof into one where proof is the interaction between a prover, player, and a refuter, opponent, A and IA, or, more precisely, A and the model of IA. Just like the environment in the classical church-Turing paradigm of computation, where it was presupposed but never explicitly asserted, in 359. Its classical form \A is rather a passive and extrinsic piece of information in relation to A. In the interactive framework, however, IA is an intrinsic dimension of the proof or meaning of A. The proof of A rests on the proof of IA in the context of an interaction or game played by the proponent P and the opponent IA. In this approach, however, classical negation is abandoned in favor of interactional dualities, with negation as the interchange of roles between the proofs of A and A1 where the absurdity or contradiction or falsum sign 1 is a linear negation that expresses duality, example A-B equals Bx A1. Action of type A equals reaction of type A1. In this fashion, even logical connectives can be expressed as moves in interaction games. For example, in the classical Lorenznian version of game semantics 264 conjunction, PAQ, and disjunction, PVQ, can be expressed in terms of how the game proceeds when compound propositions constructed by conjunction or disjunction are attacked or defended, questioned, or asserted. To challenge/question the conjunction, the opponent may select either conjunct, while the proponent can only defend/assert the conjunct that the opponent has selected, while to challenge the disjunction, the opponent may ask the proponent to select and defend one of the disjunct. Similarly, to challenge the implication, P**Q, the opponent may assert P. Then the proponent must either challenge P or assert/defend Q. Reconceived within a dialogical framework, proof is no longer an object in the way it is classically understood, but an act. As an act, proof implies the confrontation of acts, i.e., interaction in the computational sense introduced above between dualities that can be represented as agents, processes, or strategies. What dialogical interaction affords is not merely the computation of meaning or semantic values, but also semantic information such as the contextuality and thematization necessary for the determination of meaning. In the dialogical paradigm of meaning as proof or use, semantic values and contexts are computations. Depending on the specificity of a dialogical interaction, computation can be understood either as proof search or proof normalization. In the proof search schema, if the interaction game returns the proof of a sentence or formula, the meaning is computed. Otherwise, it searches forever and fails to obtain the proof. Cf. the halting problem, i.e., the dialogue will not be able to determine the meaning. In the normalization schema, the proof or meaning can be computed if, by the elimination of unnecessary steps, transitions, or rules, useless detours, for a formula or sentence, the normal form or canonical proof can be obtained. This normal form is the simplest, i.e., most irreducible proof obtainable without using unnecessary detours. Cf. normal form in abstract rewriting as an object that cannot be transformed any further. Point 265. In this setting, two statements have the same meaning if their proofs or constructions can count as equivalent insofar as there is a reversible inferential relation or mapping between them. Point 266. In the universe of the automata, the interactive schema of meaning as proof can be thought of as a toy meaning dispensing machine. The machine consists of two agents plugged into an interaction over a language C. The interaction modeled on a two-person game, more specifically, an elementary I-thou dialogue in which, from the perspective of one agent, it is the system and the other agent is the environment. Inside this interactive machine, there are algorithms which obtain proof either through normalization or search. Insert syntactic tokens or terms into this machine and the machine dispenses meaning. Composed of syntactic structures, the semantic value or meaning has a normal form and is invariant with respect to the interactive dynamics inside the machine. Give syntactic terms of the same type to the vending machine, and you should be able to get the same outcome. A similar interaction machine can be imagined for transforming the minimal generative syntax of the kind our automata already have into the concrete syntax structures required for sentential composition. The configuration of the machine remains intact, but the emphasis of the machine operation or proof acts will be on resource sensitivity in handling syntactic tokens. In this machine, raw chunks of syntax go in and the sentential syntactic units whose dependencies underlie semantic sentential dependencies come out. 267 The products of the machine are precisely those syntactic structures that support semantic compositionality, the fact that sentences can be decomposed into more elementary constituents. However, syntax at the level of sentential structure is deeply resource sensitive. This is particularly the case for the syntactic binding of sentences where the meaning, i.e., referent, of an item such as a pronoun can only be determined by the connection it has at any instant with another item in the sentence. Such linked items whose meaning or reference cannot be determined by themselves, which is usually the case for ordinary lexical entries, are known as anaphoric elements. The need to keep track of anaphoric dependency relations between different uses of words in a sentence or between sentences is directly tied to the resource sensitivity of syntactic relations. 268 In the sentence, Kansas saw a monkey touching the monolith, and it also heard the monkey screaming as it touched it. The anaphoric use of the pronoun it is dependent on tracking its point of reference as well as its iterations within the sentence. Does it refer to Kansas, the monkey, or the monolith? This anaphoric binding is essentially resource-sensitive in the sense that it cannot be seen as a simple transition Kansas-it in which it can be obtained by repeated iterations of Kansas, i.e., all iterations of it in the sentence do not necessarily refer to Kansas. Instead, the transition should be seen as a resource-sensitive linear implication Kansas-degree it where it uses Kansas as its point of reference, resource, exactly once. After that, the syntactic-semantic relations between other iterations of it and other antecedent nouns in the sentence will have to be checked to determine whether or not Kansas can be reused as point of reference or resource for it. Such resource-sensitive connections require logical operators such as exponentials in linear logic to control and keep syntactic resources in sentences. 269. Keep it in focus, a dialogue in 8 acts. Earlier in this chapter, the problem of the syntax-semantics interface was addressed. The solution to this problem was put forward in terms of dialogical interaction as a logico-computational condition for the possibility of meaning. But in order for our automata to have dialogues in which the rules of language are not set in advance, a new type of dialogue must be introduced, one in which rules emerge through the interaction itself. The J form of such a dialogue corresponds with the general category of games JG, discussed earlier. One may call such a dialogue an interaction with no J pre-installed normative bells and whistles. Dialogue, in this sense, counts as J the generalization of the logico-computational notion of interaction as the bridge between syntax and semantics. According to Samuel Tron on ETAL, a dialogue has at least 3 essential functions: exchange of information J, i.e., computation in the sense discussed earlier, construction of knowledge J, and resolution of cognitive tensions, i.e., harnessing the behaviors of I interlocutors toward new behaviors Ji. First, at every stage, a speaker is giving a symbol, and this exchange is informative in 3 ways. It informs us about the discussed, some thesis, the subject that is speaking, his approach about this thesis, and the connection between a present intervention and some counter-interventions, upstream or downstream, actuals or virtuals. Second, running dialogues shows arguments interacting like machines built up to explore relevant opportunities of discussion according to some global strategy. I argue in this way to reach this point, I open these branches to induce some reactions. So, dialogue is a sort of unfolding structure that represents some knowledge. Evidently, involving friendly but tenacious interlocutors ensures a good, exhaustive, exploration. Third, By the interaction, the locutors can extract some new information which is about the form of the interaction, contained in the result of the dialogue, what is stable, what is explored, what is new, what is in latence. 270. This multilayered view of dialogue can be modeled on the general dynamics of interaction in such a way that the functions of dialogues mirror the deep properties of logic and computation. One example of such a model is Jean-Yves Girard's Indies, which at a paradigmatic level of interpretation reflects the logic of dialogue, a linguistic interaction in which not only can syntax be bridged with semantics, but the rules of language naturally emerge as part of the dialogue. 271 Girard's Ludics can be characterized as a pre- or proto-logical framework for analyzing logical and computational phenomena at the most elementary level. Defined at the intersection between linear logic, a substructural logic capable of capturing the duality of interaction and the interchange of roles, proof theory, game semantics, and computer science, Ludics introduces a logico-computational framework in which, at the deepest level, the distinction between syntax and semantics collapses. Yet this continuity between syntax and semantics is established by deviating from a number of traditional approaches such as referential theories of meaning, monological conceptions of semantics, non-autonomous approaches to syntax, and the traditional forms of game semantics conditioned on game-theoretic concepts such as predetermined winning strategies, preference ranking, payoff functions, and referees. In Ludics, these are replaced by an inferential theory of meaning, dialogical and operational semantics, an autonomy of minimal syntax, and a general notion of game devoid of any predetermined winning strategies or payoff functions. Ludics shows that the continuity between syntax and semantics is naturally achieved through an interactive stance towards syntax in its most atomic and naked appearance, the trace of the sign's occurrence, the locus or place of its inscription. Semantics immanently unfolds through the dynamic impact of the most minimal appearance of syntax, its locus stripped of all pre-formulated rules and metaphysical references. Different stances toward an atomic syntactic expression are represented as interacting strategies, called designs in Ludics, that are tested not against a pre-established model, but against one another. In the process, the rules of logic, or alternatively, the forms of thought, emerge from the confrontation of strategies whose element of interaction is a positive or a negative locus rather than a proposition. The positive and negative locus refer to the address of the sign/formula in interaction, where an act is exercised either in response to, or as a request for, another act on the same locus but played according to the opposite strategy. The exchange via the relation between a locus and its polar counterpart corresponds with responses and demands between interlocutors in a dialogue, or players in a game. Let us briefly examine the most basic elements of Ludics as the logic of dialogue. Distinguished by the answer or defense of the player against the attacking move or query made by the opponent. Less in traditional game terms and more in Ludics terms, designs are alternating sequences of positive and negative rules which may either progress endlessly, as in endless dispute, or be closed by a rule called daimon. Plays, dialogical equivalents of proofs, are alternating sequences of moves or actions. Moves are defined in terms of a tuple, PZR, where P is the local polarity of moves, positive polarity for the actions or moves of the player and negative polarity for the moves of the opponent. I is a locus or fixed position to which a move is anchored. Loci can be thought of as memory cells or places in which formulas are stored. In Ludics, formulas or syntactic terms are replaced by the address of their locations in the interaction/dialogue. In other words, all that matters are the locations of syntactic terms or formulas, not formulas themselves and how they are manipulated within a dialogue or proof. R is a finite number of positions which can be reached in one step and which is called ramification. Positions are addresses of loci encoded by finite sequence of integers and usually denoted by the letters P, CR, which stand for the threads and subthreads of the interaction, loci and subloci which represent thematization of a dialogue across different topics. Trees of addresses are equated with designs. For example, in an absurdist dialogue between Kanzi and Su, Addresses can be encoded in the following manner. In the contexts and two trees of alternating sequences emerge. 367. Kanzi, did you see that gray stuff? #0. Su, yes. 0.1 pounds. Kanzi, have you noticed it makes noise whenever it finds something new? #0.1.0, Su, it often does. #0.1.0.1, Kanzi, why is that you are clicking too much today? CR0, Su, I have no idea what you are talking about, CR0.1. The starting positions, also known as forks, are denoted in the sequent form as FBA where T and A are either singletons or empty sets. In this setting, when an element belongs to T, every play on this element starts with the opponent/environment's move and the fork is said to be negative, whereas if the player/system starts with an element of its choice taken in A, the fork is said to be positive. In this form, a design can be represented as a tree whose nodes are forks RHA and whose threefold root is comprised of the positive rule, the negative rule, and the daimon. Rules: the only rules necessary for building designs or strategies are daimon plus negative and positive rules, which are indexed by a property called focalization. Roughly, focalization can be thought of as proof search in an interactive framework. It allows for the grouping of a series of consecutive actions, i.e., plays as proof, of the same polarity as if they were a single logical action in a proof. That is to say, focalization enables the alternating dynamics of positive and negative actions. In Ludix, focalization represents proofs as interactive processes between two players where the player/proponent can choose what to do, positive action, or receives and acknowledges the action or move performed by the opponent, negative action. From this perspective, focalization creates a proof tree in which rules or logical connectives are captured by alternating sequences of positive and negative actions which switch loci for subloci and vice versa across the consequence relation, bb_ob. HFO.I. The meaning or semantic value of rules is obtained from the interaction of such consequence relations qua use in the dialogue. The positive rule can be denoted in the sequent form as FAI 1-0, where I is a finite set of integers, possibly an empty ramification, such that, for every pair of indices, ij, e/aj and I are disconnected and every a caret is included in A. Correspondingly, the negative rule can be denoted in the sequent form as I/ha/a, I, ao, where j_f is a possibly empty or infinite set of finite set of integers, ramifications, such that instances of A/not necessarily disconnected are included in A. In addition to positive and negative rules which range over loci and subloci, there is also a general axiomatic rule called daimon symbolized by T, which can be understood as a paralogism. Whichever player or proof process, H4 or K41, invokes the daimon, the other player wins. In other words, the daimon allows for identification of the winning strategy, the correct proof, or the validity of a proposition. A proposition can be said to be valid for a given design if that design never invokes daimon before its opponent. As such, the daimon can be identified with the conceding act of I give up or stop. Terminating a design or closing off the branches of a proof tree, in a dialogue. Additionally, daimon is a positive rule, meaning that either player can choose to invoke it. Daimon is represented as a sequent with no premises. 369. Here, what we are interested in is the dialogical interpretation of the objects of Ludix in a way that allows us to understand dialogue as a dynamic process, interactive proof or computation in which rules and meanings spontaneously emerge throughout the course of the conversation, i.e., simply through the exchange of loci and subloci addresses of syntactic terms or formulas and in the presence of most elementary rules of negative and positive actions plus the daimon or termination command. According to this dialogical interpretation, for a given dialogue, the conversation progresses from whatever locus the polar strategies, players, choose to focus on. Again, in an imaginary dialogue between Kanzi and Su, this can be interpreted as the first move made by Kanzi, for example, an utterance regarding the presence of a fuzzy item, the focus #0. If Su acknowledges Kanzi's utterance as a speech act, it may reply with an utterance on the same focus, #0.1. Then the dialogue can be said to be developing along a selected context AQ in which the theme the presence of fuzzy gray item, is developed. Contextualization and topicalization in a dialogue can, therefore, be captured by alternating sequences of positive and negative actions. 273 For a given locus or address focus of the dialogue, the context A0 can be written as equals T*0*0, T*0*1, *R*0*n. If we view the design from a top-down perspective or in terms of pre-steps, the topic of the conversation can be said to be an operation that unifies the focus and the context, i.e. Kanzi's first move together with the acknowledgement of that move by Su. 1. R*0*0, R*0*W equals A R*0 HIR, plus comma 0, R*0 I. In this fashion, thematic variations, defined as a set of sets of loci, are developed in a dialogue as polar strategies give different addresses, loci, to an expression. A new locus can be accepted by the competing strategies or designs, corresponding with the agreement of interlocutors on a specific way of addressing the initial topic of the conversation, and introduced as the focus of the exchange. This is the process of bilateral focalization in Ludics, which maps the actions played in one strategy, the behavior of a design, to its polar counterpart and projects them back. In doing so, focalization reveals logical constants and rules that are not a priori given, but adaptively emerge in the absence of any gain function or external referee. Moreover, focalization progressively topicalizes the interaction and drives expressions into a state of context sensitivity in which syntactic terms or formulas acquire semantic value by virtue of how they are thematized in the same context, focalization on the same set of addresses, as well as how the context is updated in the dialogue, sets of designs or proof acts exchanging the same locations and sublocations. This is equivalent to Brandam's inferentialist pragmatic theory of meaning, where the contextualization and updating of the context of expressions by the inferential relations obtained between them count as the inferential articulation of expressions that genuinely confer conceptual content on them. 274 Like normative scorekeeping pragmatics, Ludics adopts a conception of meaning that is not representational, i.e., it does not relate to a non-linguistic item but is instead conferred by the reciprocation between different competing strategies or interlocutors. Semantics imminently arises as the normalization of clashing strategies or processes executed at the level of syntax. In other words, the interaction between different stances toward an expression, a location, can be seen as the process of computing meanings or, in proof-theoretic terms, as the process of locating proofs or meanings of expressions. As the logic of dialogue, Ludics provides an interactive articulation of speech acts. But unlike the classical view of speech acts, where the speaker's intention to communicate a propositional content is normatively predefined, in Ludics speech acts evolve naturally through interaction. Interacting moves or actions, partial functions in the computational game framework, attain the status of speech acts, such as assertion and questioning, once they produce, in a shared context, invariant impacts on the environment, i.e. the addressee from the perspective of the speaker and the speaker from the perspective of the addressee. Here, invariance means that the execution of such actions or dialogical interventions on variable expressions in the same shared context or condition, data from the computational game standpoint, always yields the same observed impact for both speaker and addressee. In this sense, Ludics allows speech acts to be defined in terms of designs, strategies of the speaker, locations, positive and negative rules, respectively, executing dialogical interventions and recording or anticipating the interventions of the addressee/interlocutor. As elaborated by Troncaret and Fleury, A Luddich's definition of speech can be laid out in terms of three elements: 275. 1. The speech acting competence of the speaker to impact, denoted by a positive rule, the context, interactions on the same loci, given the anticipated reactions of the addressee, denoted by a negative rule. 2. The test, which is an interactive situation that contrasts the speech act with a complex structure representing the context. 33. That mixes or interacts contextual data with the addressee's reactions. Put simply, the test is the interaction between speech acts and context. 3. The impact, pound, which is the effect of the interaction, the updating, modification, or erasing of a shared context. C. The speech act can then be understood as the interaction of two designs H and 33, resulting in a new design, pound. When negative or passive, 33, actions or observations represent a contextual structure CL. And when positive, U, actions or observations represent active design trees which are operations, functions, or transformations, modification or erasing, in the context CL such that CLE. The impact or significance of the speech act, the design, pound, can, therefore, be expressed as an invariant behavior which, for every CL, yields or produces the effect in exactly that context. Thus the speech act is nothing but its impact in a dialogue, and this impact is essentially the normal form resulting from the normalization of two interacting designs H and 33, proof and counterproof. With these preliminary remarks, we can see how Luddichs as interactive logic or the logic of dialogue is the generalization of what Brandom calls deontic scorekeeping, the game of giving and asking for reasons. Let us imagine a hypothetical dialogue in the style of Luddichs and deontic scorekeeping between Kanzi and the monkey. Hi monkey's noises are mapped onto Kanzi's sentences, and vice versa, in such a way that both agents can recognize what they say in virtue of the interlocutor's evidence for or against it. Let Kanzi be the asserter/speaker A, and its interlocutor, or the addressee. A is in possession of a set of markers, sentences, in such a way that playing a marker counts as claiming or asserting something. These markers are differentiated into two classes, those kept and those discarded. The record of such markers is kept either in a general notebook shared by both A and H, or in personal notebooks belonging to A and H. The markers kept and labeled by account as the score of the speaker. If A plays a new marker making an assertion, it changes its own score and maybe its interlocutor's. Now, provided that some possibilities have been presented by B as entitlements to commitments, i.e., reasons to believe that A may play a marker by asserting or endorsing a claim, example, this monolith is black. Additionally, we assume that A keeps a database or directory of entitlements, i.e., it records the reactions of B toward its commitment, the monolith is black. In such a scenario, we can imagine a dialogue focused on the color of the monolith, and which consists of 8 acts tagged by digits. In the simplest form, they are tagged by 0 and 1 denoting the negation and affirmation of the predicate. Other digits could be introduced, for example, to express modalities. The dialogue acts progress in the following manner. 373. Act 1. A chooses an object, a singular term among the set of many such objects, cf. the choice of playing an opening move from a set of possible. A being entitled by the interlocutor to make the assertion P, or in this case, the entitlement to address some theme, the color of the monolith. Act 2, thus having chosen to speak of some definite object, A entitles B to treat this object in terms of the range of properties that are generally associated with it, example, black as a color, not of light color, etc. Act 3, in return, B entitles A to choose and play a property K from this range. Act 4, on the permission of B, A now chooses a property and entitles B to regard or act on this property within a range of values, example, shiny, opaque, textured black. Act 5, B entitles A to choose a value C. Act 6, A picks up a value and entitles B to act on it within a set of modalities which can simply pertain to truth and falsity. Act 7, B entitles A to pick up a modality. Act 8, A chooses a modality and waits for's acknowledgement. The dialogue may conclude once B invokes the daimon. The entire conversation can be represented as interacting design trees where all that is required to keep and update the scores of the speaker and the addressee so that their acts can be regarded as sufficiently discursive is the method of tracking how the locations or addresses of the object / together with its range of properties and values, are exchanged and swapped from one side to another. The dialogue can be represented in tree form with the speaker on the left side and the addressee on the right side. The designs of A and B also can be written in sequent form as follows. Alternative moves. The choice of this object has the pragmatic significance. A, B, N, plus pound W, he. 374. HGL. Lytics provides a framework in which the iagogico-computational phenomena implicit in the pragmatic dimension of language as the bridge between syntax and semantics, symbol pushing and inferential articulation, come to the foreground. However, unlike the pragmatic theory of meaninglessness even in its Brandomian version, which significantly differs from its original Wittgensteinian form for Lytics, there is no pre-established space of reasons into which one graduates. The generation of rules and the capacity to reason are inconceivable without interaction, and are inseparable from the complex contexts that arise throughout its course. However, contra cellars, this interaction is not a matter of acquaintance with norms as a matter of cultural evolution, and contra brandum, it is not an index of a substantive sociality of reason. It is rather the very formal condition of language and meaning a iagogico-computational dynamics that realizes the syntax-semantics interface. The substantive sociality of reason is built on this formal condition, not the other way around. This formal condition in which computation, logic, and mathematics intersect is exactly what we can call the pure transcendental condition, that is, a formal dimension at last liberated from Kantian transcendental logic anchored in the provincialism of the apperceptive I and the particular transcendental types which shape and constrain the experience of the subject. And it is in fact this formal dimension as captured implicitly by natural language and explicitly by interactive logics and artificial languages that grounds transcendental logic as the science of pure understanding and rational cognition, or simply the concept of mind in relation to the world. The subject has experiences, i.e., it can access the content of its experiences, because there is a formal dimension, call it language as interaction as logic as computation, that permits the semantic structuration of such experiences. Without it, there would be no experience and no understanding. Yet the qualifier formal should not be construed as a reinscription of form versus content, or, more precisely, the dichotomy of syntactic form and semantic content. Both form and content belong to language as a formal dimension. Moreover, the interactionist view of logical syntax is itself semantic in disguise. While the form-content dichotomy can be seen as still operative in the context of the classical picture of formal language, is a problem that is often raised by proponents of language who see it solely in terms of natural languages. As we observed, it is not a tenable index for the characterization or distinguishing natural languages from formal languages, particularly in the wake of developments in the interactive paradigms in computation and logic. Formal languages are better candidates for the articulation of language qua logic as an organon than natural languages, not merely because they can possess more expressive powers by virtue of their unbound syntactic complexity, i.e., the Carnapian view of language as a general calculus, but more importantly because they explicate interaction as the formal condition of language. In this way, the specific picture of formal languages developed in the interactive paradigm averts the risk of grasping the nature of language and linguistic practices through a vaguely metaphysical account of sociality, which results either in seeing linguistic practices as one generic social practice among others, or in an inflationary social account of language and reason. From this perspective, the designation artificial for an artificial language founded on the logic of interaction no longer implies a transcendental lack in comparison to natural language, a lack that can supposedly be overcome through better imitations of natural linguistic behaviors. On the contrary, the artificial, as that which has the capacity to range over broader logical and computational behaviors, is what expresses the transcendental dimension, i.e., the autonomy of logic and language over experiential content in its pure and unrestricted form. Said differently, the designation artificial in artificial languages implies the possibility of unbinding the formal as that which structures content. Put simply, artificiality, in this sense, does not signify an inferiority to the natural or something that vainly attempts to mimic the behaviors of natural language. It is rather the case that the natural in natural languages designates a subset of the designation artificial in artificial languages. The behaviors of natural language, its capacity for the inferential articulation of content, of syntactic and semantic structuration, merely represent a narrow 377 domain in a far broader expanse of logico-computational phenomena that a general artificial language unrestricted by the experience of the transcendental subject while embedded in the logic of interaction would be able to cover. It is owing to its entrenched association with the experiential sphere of the transcendental subject that natural language is often falsely given a special status over artificial languages and, conversely, artificial languages are taken to be in principle inadequate in comparison with natural languages. Yet subordinating the structure of language to the structure of the subject invariably results in a subordination of the logical potencies of language for structuration of the world to a narrow domain limited by the particular transcendental structure of the subject. The valorization of subjective experience or psychology against formalism or, in this case, the formal dimension of language, is precisely the kind of bias that leads to the erroneous thesis that natural language is unshakably superior to artificial languages, or that artificial languages cannot possibly capture the semantic richness of natural languages. And of course, the claim regarding the fundamental inferiority of artificial languages goes hand in hand with the verdict that mind cannot be artificially realized. Both language and mind are treated as ineffable or mysterious essences which yet somehow miraculously do what they do. Valorizing experience against the formal dimension of language is a formula for the limitation of experience. Only the richness of the formal can express or expand the richness of experiential content. The significance of artificial languages as languages realized at the intersection of computation, mathematics, and logic boils down to the fact that they have the capacity to sufficiently extract and distill the expressive richness of the formal dimension, which in turn enables a better grip on experiential content. Accordingly, to expand the field of experience with the understanding that experience is inconceivable without its content, language should not be subordinated to the interests of the experiencing subject. Instead, it should be decoupled from the experience of the subject. In the same vein, the detachment of formal languages from the communicative role of natural languages should also be regarded as an opportunity to grasp the functions of language in themselves. In this regard, shifting from language as the 378 medium of communication to interaction as computation, the protological foundation of language and logic unbinds the logico-computational functions of language while making it possible to rethink, reimagine or reinvent linguistic communication on a completely different level. Unbinding language means permitting its formal dimension to come forth and be fully expressed on the surface of language. The aim of the explicitation and mobilization of the formal dimension of language is not simply to achieve syntactic efficacy, mechanizability, or semantic transparency as afforded by formalism, but to augment world structuring abilities by augmenting the syntactic semantic expressivity of language. In this respect, the abilities afforded by natural language as a form of language whose evolution is tied to the restrictions imposed by the structure of the experiencing subject would be merely a small archipelago in the vast sea of syntactic and semantic abilities afforded by a general artificial language. In other words, natural language represents only a fraction of the logical autonomy of the formal as the transcendental dimension through which the content of experiences can be accessed and whereby mind becomes able to structure the world of which it is a part. As far as logical autonomy, rather than practical autonomy, is concerned, it would be no exaggeration to claim that a programmable toaster has more logical autonomy than all of Homo sapiens combined. The discussion on artificial general languages and the autonomy of the formal brings us back to two overarching themes of this book. One is the inquiry into the transcendental structures or conditions necessary for having mind qua configuring factor. And the other is the critique of transcendental structures, whose aim is to procedurally unbind the conceptions of mind and geistic intelligence from limitations and biases originating in our contingent constitution and the seemingly fixed particularity of our transcendental structures, rather than dispensing with transcendental structures tout court. Following these two trajectories, however, was impossible without a deep analysis of the functional picture of mind combined with a multiplicity of methods which are traditionally not in the toolbox of philosophy in order to strip away and dig through that seamless facade which is the natural. 379. Order of things, the alleged naturalness of our time consciousness, sociality, and language, among others. This is all to highlight the fact that extensive analysis and methodological assiduity are not auxiliary to the Copernican gesture of deracinating the transcendental subject and hurling the concept of intelligence into the abyss of intelligibilities. They are the very principles of this Copernican gesture by means of which the apparent facts of experience are peeled off to reveal a larger expanse of possible experience and thus of objective reality, a process through which our most treasured assumptions are challenged, to ensure that they are not subject to the experiential and cognitive biases of transcendental structures. The Copernican gesture is akin to a chain reaction. To follow the chain in either direction toward the source or the consequences, one must have a fluent enough paradigm to shift from one method or model to another when necessary. In this sense, this chapter's rather technical survey of language was an indispensable elaboration on the much broader themes of this work. On the one hand, this introductory analysis indicated that natural language is only the tip of the iceberg of general artificial languages, that is, the unrestricted scope of language where traditional distinctions between language, logic, mathematics, and computation, or more generally, langage and logoi, begin to vanish. On the other hand, it underlined the significance of the implications of a revolution initiated by Gottlob Frege and less well-known figures such as Hermann Cohen to shed the psychologistic and utilitarian residues of thinking and language, a revolution that was continued into the 20th and 21st century by the likes of Quine, Carnap, and more recently Dudil Novas, but was most effectively carried out by theoretical computer science as the unifying philosophy of computation. Construction of general artificial languages is thus commensurate with the conception of logic as an organon. Such equation is guaranteed to elicit the ire of orthodox Kantians who may still believe in the hard distinction between form and content, or opposing logic as a canon to logic as an 380. R. Organon, which according to Kant is the logic of illusion or a sophistical art. 276, on the grounds that it is not constrained by the empirical sources of truth, sensible intuitions, or information outside of logic. What Kant means by logic as an organon is a formal tool for the production of objective insights or an instruction for bringing about a certain cognition that can be said to be objective. This conception of logic is then characterized as the science of speculative understanding or the speculative use of reason, the organon of the sciences. On the other hand, logic as a canon still refers to the formal use of logic, regardless of its content, which can be empirical or transcendental, but this time as delimited by the characterization of logic as the canon of judging, i.e., the mere criteria of the correct application of the laws of thought or judgments, which requires and is constrained by extra-logical information. Kant's opposition of logic as a canon to logic as an organon is based on a historical reading of the controversy between Epicurus, the defender of canon, and Aristotle, the defender of organon. Yet, it is necessary to point out that Kant's dismissal of logic as an organon entirely relies on an antiquated Aristotelian definition of logic. Regardless of how we interpret logic, this very distinction becomes tenuous in the wake of the revolutions in formal and mathematical logic in the 20th century, as well as the advances of theoretical computer science. But the precariousness of restricting logic to a canon at the expense of rejecting logic as an organon can also be formulated via a question posed against orthodox Kantians: so, you think that form without content is arbitrary, i.e. unconstrained, but could you tell us what is content without form? Surely, entertaining the possibility of the latter even under the most critically cautious eyes is another variation of that ideological house of cards which is the given. The whole notion of logic as a canon describes a game of logic already rigged by the representational resources and limits of the apperceptive subject constituted within a particular transcendental type. Kant assumes that thinking about logic as an organon means believing that we can judge of objects and to assert anything about them merely with logic without having drawn on antecedently well-founded information about them from outside of Logic 2777-8 in this and other passages in Critique of Pure Reason which are riddled with focusing adverbs such as merely or solely. Kant seems to be advancing a trifling and obvious point not only as a profound remark but also as a refutation of the conception of logic as an organon. At least since the time of Plato's sophist, we know that what is said is not equal to what is. Indeed, the equation of the two is the core tenet of sophism. So long as we know the rules of deductive syllogism, we can call ourselves masters of all sciences. However, logic as an organon neither implies the aforementioned equivocation, i.e., the claim that logic is by itself sufficient for judging about the stuff in the world, nor does it require any metaphysical commitment with regard to logic, the claim that laws of thought are laws of the world. In contrast to Kant's straw-manning, all that the conception of logic as an organon suggests is that our resources of world representation are in fact beholden to and caught up within the scope of our world building, and in this case, the worlds of logics. In other words, it would be absurd to talk about objects without the primacy of logical structure, logoi, or the formal dimension. Kant would have agreed with this view, but only in an inconsequential manner. Why? Because if all talk of the object is meaningless without theory or logical structure, then the expansion of the field of logic or determinate thought forms unconstrained by all concerns about representation and subjective experience would be an absolutely necessary step in order to constitute objects, make objective assertions, and deepen our discourse about objectivity. 216 This primarily unconstrained view of logic as the indelible factor for object constitution is exactly what we can call logic as an organon. Without it, all we can ever achieve is pseudo-talk of stuff, i.e., Aristotelian this such as, or todes. Moving from the sense-impression fuzzy mass of gray to the judging assertion this is a monkey requires the addition of logical structure. But the constructive characterization of logical structure is not a priori limited by representational concerns. Indeed, to adequately hone the notion of logical structure demands the treatment of logic in terms of unrestricted logical world building, that is to say, unconstrained by any enforced representational consideration, whether the experiential content, the empirical source of truth, or the criteria of correct application of logical laws to items of the real world, that may establish the frontiers of logic in advance. It is only when we attempt to decouple logic from any representational or world-referring constraints that we can ensure a sufficiently enrichable framework of world representation. The world-constructing resources of logic in itself precede and in fact undergird world representation, our understanding or judgments about the world. To make a Carnapian slogan, construction of the world is prior to the constitution of the object and the knowledge of it. This priority is not only priority in the sense of one temporally preceding the other, but also priority in the order of constitution. It is priority too which is, properly speaking, the focus of logical world building and describes the conception of logic qua an organon of which general artificial languages as the apeiron of the formal dimension are exemplars. This idea of logic as a world that ought to be infinitely constructed without any prior restriction is incommensurable with the idea of logic as something that ought to be coordinated with the real world in the first instance. Kant's transcendental logic as a species of pure specialized logic, i.e., one concerned with a particular use of understanding, is precisely a conception of logic that is not just conservative with regard to the possible scope of logic, how general logic can be expanded and enriched. In addition, insofar as it is built on the conception of logic as a canon, i.e., constrained by representational concerns, it harbors epistemic implications which are nightmarish to say the least. The picture of the objective world we represent may very well portray a series of subtle and distorted variations of ourselves and our entrenched biases. As long as logoi are shackled to our representational system, we cannot even be conscious of our Dorian Grayesque situation. We remain unwitting. 383. Followers of the cult of Narcissus, which not only sees itself and only itself in the abyss, but also attempts even unconsciously to turn the universe into an infinite projection of itself. It is a humanistic or subjectivist mistake, one that runs from Kant to Sellars to limit the idea of the transcendental to experience, which ultimately reduces the transcendental to its mere application to sensory materials or sensible intuitions. Nowhere is this limitation more prominent than in Kant's elaboration of the pure concepts of the understanding, or categories, which are categories only in so far as they are abstractly bound to the I as that which thinks and experiences. In other words, categories are only of interest to the extent that they serve the experiential, epistemic, and practical needs of the subject. But in being restricted to the interests of the apperceptive I, categories cannot be adequately treated in their own terms, that is, they cannot be examined as what they are in themselves, as forms having a logical autonomy of their own. The immediate consequence of limiting the transcendental to the domain of experiential content and, correspondingly, to sensation as a necessary condition for experience, is the elision of the distinction between logical autonomy and practical autonomy, the pure autonomy of the formal, syntax and semantics, and the relative autonomy of the experiencing subject. At the level of experiential content, mind has only a relative or conditioned autonomy at best. This is because experience is anchored in sensation and sensations are instantiated at the level of the causal, and when it comes to the domain of causes there is no absolute autonomy, if any at all. This is what led Sellars to compare the conceptualizing mind to a computer whose purported spontaneity or autonomy is shaken by the fact that it does nothing unless it receives an input, i.e., that it is predisposed to a foreign cause. 279 It is only in the presence of a foreign cause that the computer can initiate its search and actions. Its autonomous activity is a register of its passivity in relation to an input qua foreign cause. The spontaneous activity of the mind akin to the lifelike whirring of a computer that has just received and reacted to an input is set in motion by a causality which, even though it appears as the spontaneous causality of the conceptualizing mind, is in reality a causal routine whose causality is being caused, and thus is a causality of nature, where autonomy is at best relative or conditioned by pure heteronomy. But the conclusions reached by this analogy are misleading to say the least. For even though the operation of the machine receiving an input, initiating a search, and yielding an output is merely a relative spontaneity, its so-called logical disposition has a formal or logical autonomy. 280 Foreign causes have no bearing on the logical dimension of the computer in terms of how, in accordance with the formal dimension of rules, it processes the input and provides an output. A computer has formal or logical autonomy but not spontaneity at the level of its operation, its wordly practice. Or, more precisely, it has autonomy at the level of logical operations in themselves but not at the level of the spontaneity of its actions. A program has logical autonomy to the extent that it is the subject to its formal rules or axiomatic bootstrapping. Treating the formal or logical dimension of the computer as a disposition at best misses a point about what formal autonomy is, and at worst comes off as a linguistic sleight of hand. A programmable toaster certainly has no practical or agential autonomy, but agency is not everything. Although a programmable toaster lacks agential autonomy, it has logical autonomy at the level of its program pertaining to how to toast a piece of bread. Even though the toaster has no agency or subjectivity, there is in principle no reason to doubt that a program could be written to enable a not-so-futuristic toaster to make not just better toast given any kind of bread, input, but toast that surpasses in every respect that made by a practical subject most adept in culinary skills. Similarly, for the conceptualizing mind, the true locus of spontaneity is not to be found in its perceptions and actions or in the contents of its thought episodes, but in the formal dimension of thinking, or in how language and logic handle such contents. Constraining meaning, semantic value, to the metaphysics of sensation as encapsulated in Sellers's theory of picturing is necessary for the epistemic traction of the formal dimension of thinking on the world or, more generally, the epistemic orientation of logical powers. But reducing, in advance, the function of formal to the epistemic content or application is a sure recipe for an impoverished view of both form and content, both logical powers pertaining to conceptual activities and their epistemic significance. 281 Not to mention that such a view inevitably becomes susceptible to strong psychologism, i.e., the attempt to establish the validity of logical principles by appeal to facts of human psychology. 282 While, in virtue of refusing to engage with the question of the formal on its own autonomous ground, it has deprived itself of adequate resources to challenge the biasing effects of psychologism. It is only by disengaging what is formal from subjective experiential content, the pure formal dimension of thought from its prima facie epistemus experiential content, that the formal can be treated systematically. And it is only through the systematic rather than empirical or epistemic treatment of the formal dimension in its own terms that experiential content can be richly structured beyond the limited scope of non-conceptual representations. Formal languages express the systematicity of the formal, that is to say, the structural relations between formal aspects of language as decoupled from its communicative function, the experiential, and ordinary semantic content. However, in contrast to the traditional view of formalism, this disengagement from content does not make formal languages or formalisms meaningless, i.e., pure abstractions with arbitrary applications. As Kramer and Dudilhnovas have elaborated. 283 The decoupling of formal languages from any subject matter or content, desemantification, conditions the possibility of resemantification or applying a given formalism, which is developed against a specific background, to a different problem, phenomenon, or framework. 284 Accordingly, the systematic treatment of the formal, i.e. treating logical powers in terms of their own structure rather than their transitory experiential content or epistemic application, not only allows new contents to be structured and accessed, semantic enrichment, but also brings about a debiasing effect, in the sense that it strongly mitigates the perceptual biases of reasoning. It is the debiasing effect that makes of formal languages tools or cognitive technologies that enable the transition from the common sense framework of understanding and knowing content to the scientific framework of epistemic inquiry. It can always be objected that such an unfettered view of form completely dispenses with the socio-cultural richness that is an intrinsic part of language as we know it. In response to such an objection, it should be answered that formal languages or formalism in general do not necessarily forego the cultural accumulation of language. Saying that they do is in fact an unwarranted claim, placing a priori limitations upon what forms can do and what capacities can be afforded by them. Such a claim implicitly presupposes that cultural accumulation and experiential richness are possible without the formal dimensions of language and thinking, and thus imparts a metaphysical reality to the cultural wealth of ordinary natural languages. Not to mention that such an objection is tacitly predicated on the idea that we can organize our encounters with the world with something other than form. But such a presupposition, expressed or not, is the very example of the myth of the given. The most caustic expression of the myth of the given, or, more generally, the claim that our knowledge bottoms out in a non-inferential qua-foundational knowledge or immediate access to reality, is hidden in the assertion that forms should conform to experiences. To adopt Carnap's argument, objects of knowledge are of form, rather than experiential content, and as such they can be represented as structural entities. Considering objects of knowledge as objects of experiential content brings about a quandary, insofar as the material of streams of experience for an individual or between different individuals is divergent or even incomparably, we cannot make objectively valid statements about objects constituted by individual subjects. The only reason objects of knowledge are possible is that certain structural features agree of all streams of experience. 285 Such structural features are indexed by and are objects of form, which secures objectivity in an intersubjectivity whose individual streams of experience are held together and structured by the dimension of form. As argued above, however, the transition from the common sense framework to the formal linguistic framework, the theoretical framework, is impossible unless logical autonomy is disengaged from agential/practical autonomy, and the formal dimension of thinking is understood as having a logical spontaneity of its own. It is this decoupling or disengagement of form from content that permits the systematic treatment of content through which reasoning about content is finally liberated from ordinary subjective intuitions and perceptual biases. For this reason, understanding the logical autonomy of the formal freeing language and logic from the experiential epistemic concerns of the subject is not a formalistic caprice, an indulgence in meaninglessness, or something that results in an arbitrary epistemic relation to the world. It is the first step in attaining semantic consciousness, the realization of what one actually does when one thinks and speaks, as well as the recognition of what language does to its users once they partake in it. We have briefly surveyed the type of interaction the automata must engage in so as to genuinely count as speakers and reasoners and to have a language that confers meaning or semantic value upon their noises. As the final stage in our thought experiment, let us assume that our automata possess precisely this type of dialogical interaction, which gradually unfolds the inferential and logical powers of language. They are in possession of such linguistic, syntactic-semantic, interaction to the extent that language in its syntactic and semantic complexity evolves through their interactions via symbolic tokens, an interaction that progressively introduces logico-computational constraints on how such tokens can be exchanged or used. For now, the automata might have something like a proto-language that does not exhibit the full range of conceptual activities or semantic complexity. But it is, in principle, inevitable that their interactions, via the logico-computational constraints of their proto-language, will unfold a diverse range of syntactic and semantic features, different grades of concepts and inferential abilities, afforded by them. Language is not God-given. Its complex syntactic and semantic aspects are not given in full at the time of its inception, but evolve through its use, that is, through an interaction that results in the development of new, more complex logico-computational behaviors, an interaction that is language itself. Here the appellation language does not necessarily refer to human natural languages, but to any artificial language with a syntax-semantics interface and support for the interaction of speech acts. In its general form, language is a vast generative framework that integrates the dynamic structure of interaction and the autonomous system of symbols. In creating a reinforcing connection between the computational powers of the former and the self-efficient codifying processes of the latter, language augments and diversifies the abilities afforded by each of them. In this sense, language can be seen as the source of limitless scenarios in which logico-computational processes can act upon one another. The interactive framework of languages harnesses such processes, in the double sense of constraining them and mobilizing them toward functions with specialized logical and computational properties. Within this framework, not only are the users of language increasingly equipped with new cognitive technologies, they are also, more profoundly, formatted by the causal forces originating in the logical powers of language. For now, the automata do not know exactly what language is doing to them. They are unaware of the fact that their dialogues and linguistic interactions, thoughts, and actions are implementing complex logical and computational behaviors, that in interacting with one another, in thinking, even privately, they are acting on behalf of the as yet unknown logico-computational phenomena and powers at work beneath the surface of their language. It is only with the increase in their conceptual abilities, concomitant with the evolution of their language and their mastery of it, that they will acquire the wherewithal to become aware of the logical structures and connections underlying their sayings and doings, their thoughts and actions, the ineliminable coextensivity and correlation between the know-thats and know-hows of their cognitions. This awareness qualifies as semantic self-consciousness. The process of achieving semantic self-consciousness, becoming aware of what one does when one thinks and acts, is the prerequisite for knowing how to think and act. But knowing how to think and act is the most fundamental requirement for concrete self-consciousness as a matter of practical achievement, i.e., what to think and what to do. There is no concrete self-consciousness without semantic self-consciousness. It is with the rise of semantic self-consciousness that the automata can make explicit the role of their interaction as a framework of semantic cognitive enablement. When this role is brought to the foreground, they will be able to modify, improve, and diversify the syntactic and semantic structuring abilities that they have so far only implicitly and rudimentarily utilized to structure their encounters with the environment. With the ingress of language into their universe, the automata's meta-awarenesses can finally take the form of beliefs, and hence can be endowed with epistemic valence provided they can be formed into assertable. 390. Propositional contents which can be scored or judged. Similarly, the non-conceptual representings, e.s, of the automata are now caught up in the rule-governed web of language in which their relationships are inferentially articulated. The powers of inference afforded by language also, in this sense, find an epistemic orientation. THIRD convey an implicit knowledge of matter of factual truths about the states of affairs of the universe that the automata inhabit. Yet these truths are only presumptive or plausible. Their plausibility is a matter of where they fit within the coherentest network of inferential relations, or the conceptual order. Within the semantic or conceptual order, pattern-governed uniformities which the automata were previously blindly treating as a matter of certainty but which were in fact weak causal statistical inferences susceptible to arbitrariness become a matter of plausibility or promising truths. In other words, perceived certainty is replaced by inferentially articulable plausibility or truth candidacy as a hypothetical or abductive conception of truth which can be tested against both new observations and further claims. Enabled by the semantic dimension of language, the transition from perceived certainty to conceived plausibility is what fuels epistemic inquiry, the will to know, since it disturbs the purported natural equilibrium of the given state of affairs by introducing rational suspicion qua conceptual plausibility and, correspondingly, implausibility, into the orders of thoughts and things. This is what Plato might have called the nebulous continuity between shadows or sensible images, icons, and the intelligible reality, a continuity which, however, by no means signifies a flattening of the distinction between the two. And it is this rift or disequilibrium that sets off the involution of thinking, a critical gesture whereby the knowledge of the world expands by way of thinking's progressive realization of how it itself functions and knows. This involution is the power of determinate or critical negation as distilled in the activities of conceptual construction and the conceptual revision, formation, and reappraisal of beliefs. Once consciousness is steeped in language, it does not just seek more of itself by virtue of having a conception of itself, but more importantly it acquires what Findlay calls a sidelong intentionality in addition to 39i. Straightforward or direct intentionality, thoughts about this or that thing. Point 286. Conceptual consciousness spreads out beyond any particular limit set by a given world, in such a way that its intentionality is always the thought of many things at once, indirectly and implicitly. Each direction may bear the marks of one or many noetic activities, inferences, and forms of judgment, from perceptual, recognitive, and predicative judgments to critical judgments, from simulation to classificatory functions to ampliative inference. Some directions may follow tracks of logical entailments, some logical tracks of less stringency 287, and yet others tracks where the logical, empirical, and experiential are combined. It is this nisus, mental effort, striving or cognitive tendency, toward being ever more conscious in every possible direction that transforms the world of the automata from a narrow zone of thinking and action to an unrestricted universe where the scope of thinking and knowing has no predetermined limit or boundary. The sidelong space of thinking is tantamount to a drift or an alienating cognitive epistemic vector that pierces through any limited conception of a world or restricted universe of discourse. Driven by this drift, the automata are no longer mere creatures of behavioral interests and habits. They no longer encounter their world only through their attentional system. In other words, their encounters with the world are not limited to the immediate environment given by their perceptual sensory system. Instead, they have a conception of an unrestricted world in which possible worlds of thoughts and actions exist side by side with their given world, Welt, previously treated as the totality of all there is. This is the most significant aspect of conceptual consciousness, it begets a world that is no longer limited to the supposed immediacy of the causal sensory domain. Intelligence is that what which makes new worlds rather than merely inhabiting given worlds. Just as conceptual consciousness tends to direct and drift toward variations, multiplicities, and the dissolution of the supposed boundaries of thought and action, it also has a nisus toward synthesis and integration. The latter is defined by the tendency of conceptual consciousness not only to follow different tracks of thought fanning out in all directions, but also to work out the various relationships that obtain between such thoughts, consequence, incompatibility, or even equivalence relationships. These two concomitant tendencies are represented by Plato, in Theaetetus, in terms of the interplay between the determinate and the indeterminate. Functions of language and logoi are of two paras, determining that which is indeterminate, to a pairon. It is in having the capacity to integrate that which is purely diremptive that the automata can progressively structure their world by structuring their various thoughts and experiences of it, moving from disconnected and seemingly diverging representations of the world toward conceptual theoretical world representations or world stories. This transition requires precisely the sort of structuring syntactic and semantic abilities listed earlier at the end of the previous chapter. It is obvious that our automata, as incipient thinkers and knowers, do not possess every single such ability at the outset. Climbing the ladder of semantic complexity and acquiring more complex structuring abilities is a matter of the communal development of thought, and a gradual acquaintance with practical know-how regarding what qualifies as good material and formal inferences and what practices or abilities are required to elaborate, combine, and map structuring syntactic and semantic abilities to one another. Lastly, the metaphor of semantic or conceptual ascent corresponds with what André comes with, a nod to the work of Carnap after Aufbau, and the project of rational reconstruction refers to as explication as the paradigm of the Enlightenment. Explication as semantic ascent is no longer an exclusive feature of natural language, but of language in general, with the appellation language understood not as a given qua a natural language, but as the craft of an engineering mission, and a matter of rational choice, and thus the enrichment of the very concepts of reason and reality. The dialectical task of explication is set between practical and theoretical concerns, the cognitive and the normative. To explicate is to ascend from vague concepts of ordinary language the explicandum to more precise and justifiably more useful and explicitly defined concepts, i.e., the explicatum of what is couched loosely in a cluttered ordinary natural. 393. Language. Replacing the former with the latter coincides with the ideal of rational scientific enlightenment. But this is enlightenment in two different yet commensurable senses. Explication runs simultaneously along two parallel trajectories. The first can be defined in terms of a descriptive pragmatics, in which we explicate our local concepts by refining them, reinventing them at progressively higher resolutions. For example, the concept of hardness, to use an engineering example, is a local perspectival but not subjective concept, since the concept behaves differently at different scale lengths. At the macroscopic level, the hardness of a metal beam differs quite radically from the concept of hardness as it pertains to more fine-grained scale lengths, example crystal or nano levels. Explicating a local concept such as hardness, then, is equivalent to the scientific heuristic task of providing increasingly refined but also diversified concepts of hardness for different levels and sectors of reality. This type of refinement, however, does not happen in an existing language where the concept of hardness is firmly stabilized and defined. It requires a change of language or, in other words, a move from the ordinary framework of natural language to the unbound realm of constructed languages. In this sense, the semantic value or meaning of hardness suggests both an internal and external semantic problem, internal to the extent that the meaning of hardness J is defined in terms of the rules and inferences of language but external to the extent that explicating hardness entails an ascent from language to language 2, 3, that is to say, to the ocean of general artificial languages where the choice of constructed language is a matter of pure theoretico-practical considerations, and the concepts hardness 2, hardness 3, etc. are explicitums of language. Hardness. However, the first sense of explication as enlightenment, by itself, can only give us drifting diversifications without any hope of unity or integration. And this is where the second sense of explication as enlightenment enters the equation. We would not have even been in the position of arriving at the first sense, if we were not in the possession of explication as a universal or global trajectory. Moving from hardness J to hardness 2, and correspondingly from language to language 2, already implicitly assumes an underlying explicatory gradient from a given language to a constructed. 394. 1, and therefore from a concept loosely defined in the former to a more refined, i.e., locally triangulated and context-sensitive, concept in the latter. Whereas the transition from hardness to hardness 2 is an instance of the refinement of local concepts or the first sense of explication, the ascent from languages to constructed languages suggests that there is indeed a global conception of explication whereby we see the refinement of our local concepts as the direct consequence of how we replace our given naturally evolved languages with those which we build, and all the criteria of rational choice with regard to theoretico-practical usefulness that goes into such a choice. It in the sense that we can consider the notion of rational scientific enlightenment initiated by Galileo and Copernicus, and up to the revolutions instigated by Kepler and Newton, Darwin and Einstein as the trajectory of a universal explication within which local explications are carried out and also ultimately integrated within one unified trajectory, that of advancing from a given natural language to engineered languages and concepts, from the manifest image to appropriate Sellers's lexicon, to the scientific image. Carnap's conceptual or language engineering, then, as Camps has elaborated, is not a clash or fusion between the manifest and scientific images. The ascent from ordinary language to an engineered one does not suggest the replacement of the former by the latter, or that we leave the notions of meaning and material inferences intact as if they belong to a stable manifest image. To the contrary, the ascent from language to constructed languages suggests that the relation between so-called manifest and scientific images is one of a positive feedback loop or an enrichment. The manifest image is not static, nor is the scientific image the ultimate replacement for the manifest. In the explicatory paradigm, the relation between the two is one of refinement, dynamicity, and the evolution of multiple trajectories. But more consequentially, as Camps observes, such a relation between the manifest and the scientific, language X and language 2, means that we are far from giving the conclusive conception of reason. Reason is dialectical, an engineering ideal. To settle for any concept of reason is to betray the idea of enlightenment and, correspondingly, to fall back on either a purely 395. Psychologistic idea or a scientific portrait whose elements and relations are underdetermined if not psychologically and unconsciously distorted. With the advent of the semantic or conceptual order, the automata acquire not just an unrestricted conception of the world, but a revisable conception of themselves. It is in fact their conception of themselves in the world that grounds the nisus for their understanding or grasp of the world. In this sense, their self-conception mediates between what they take themselves to be in the world and what they actually are as denizens of the world, the order of oughts or norms and the order of what is. Conceptual consciousness is essentially a collective consciousness, since it intrinsically belongs to the deprivatized space of language and the conceptual order. Therefore, its self-conception is also implicated in the collective order where no self, thought, or experience can be conceived in privacy or separation from others. Any consciousness that develops a conception of itself will increasingly come under the sway of rational norms and impersonal or collective values and disvalues. Primarily, these norms, values, and disvalues concern the questions of what to do and what to think. Once they have a conception of themselves, the automata's activities are dominated by questions of what we ought to do and what we ought to think given what we are or, more precisely, what we conceive ourselves as. Under the influence of such norms as objective principles, rather than as social conventions, their rudimentary multi-agent framework of interaction is refashioned into an explicit social community that can be steered in one direction or another, modified, or rebuilt. In this new social microcosm, oughts are routinely assessed, kept, and improved, or discarded if necessary. As norms qua objective principles of thinkings and doings accumulate, the interplay between what is the case and what ought to be takes a new slant. It becomes a matter of dovetailing the intelligibility of things and the intelligibility of practices into an embodiment of intelligence that is invested in the intelligibility of its actions to the extent that it has a conception of how it ought to be and what is fitting for it. Inasmuch as 396 WTM. The espousal of a fitting way of existing represents a normative objective and ideal of how one ought to be. It is a matter of adjudication, and thus of a conception crafted by reasons. It does not matter whether these intelligent machines aim for higher rewards and more efficient payoff activities. In having a conception of themselves, they seek a recipe for crafting a life that involves not merely instrumentalities but also a disciplined open-ended reflection on forms and the intelligibility of the good life for themselves. What these machines take to be the most suitable way of living and the proper object of their pursuit is in reality a representation of what they take themselves to be. But what they take themselves to be signifies how they reason about how they appear to themselves and what seems to be the case for them. In other words, the aims and vocations of these intelligent machines are expressions of their particular model of rationality concerning what they are and how they should proceed. But no model of rational ity is exempt from the demands and amendments of impersonal reason. Whatever or whoever develops a conception of itself becomes bound to the norms of treating itself according to such a conception. And whatever or whoever is bound to such norms is also bound to an impersonal order of conceptual rationality that makes possible the formation of norms, their ordering and revision. Therefore, regardless of how and for what aims these machines reason, what norms they have, what objective they seek to achieve, their reasonings and by extension their ends now fall under the full influence of the very inferential normative economy or impersonal reason that sanctioned them in the first place, and which now has the power to divert any conceived end and to place any norm in peril. To this extent, any artificial agency that boasts at the very least the full range of human cognitive conceptual abilities can have neither indelible norms nor fixed goals, even if it was originally wired to be a paperclip maximizer, to amass as much reward as possible. In other words, if these machines exhibit complex practical inferential abilities, concept-using capacities, and autonomy, their ideals, whatever they might be, will necessarily be susceptible to the self-correcting propensities of reason brought about by the autonomous order of conception. Identifying them as an existential threat is therefore quite baseless, not because the intelligence in question is innocent until proven guilty, but because such a suspicion attributes a disproportionate amount of risk or, for that matter, benefit, as in the case of arguments for benevolent AGI, to something that is itself inherently historically contingent and susceptible to being transformed by the very principles that enabled it to form a conception of itself and to pursue objectives appropriate to such a conception. In thinking and acting in accordance with what they take themselves to be their self-conception, the automata effectuate a concrete transformation in themselves. But given that no conception or norm of thought and action is ever safe from the self-correcting tendency of impersonal reason, such actualized transformation will again become the basis for a new judgment, a new self-conception. This sequence of conceptions and transformations is what counts as the criterion for having a history, and whatever has a history rather than just a past has the propensity to drift from any fundamental or natural essence toward a future as the being of time in which all preconceptions and given totalities are washed away. This is what Hermann Cohen characterizes as a historical self-consciousness that takes the shape of a will fixated on the future coupled with a critical reflection on the transitory norms of the past and the present. Here, however, future does not signify a conventional sense of futurity in which future is interpreted as the not yet. Instead, it expresses a conception of future as an intelligible eternity or time in which all those given totalities, along with the transitory values of the past and the present that have falsely eternalized, are no longer. 288 In Cohen's terms, the correct knowledge of history requires the correct knowledge of time, which itself requires a thought that sets out from the future as the true being of time in which all achieved or given totalities are rendered incomplete. In this sense, a thought that sets out from the future together with a will oriented toward the future become the vectors of genuine conception and transformation. One opens up the space of possibilities beyond the given totalities or absolutized norms of the past and present, and the other works toward the concrete actualization of such possibilities, moving from the concept to its full actualization or the idea. It is in the context of historical consciousness as a striving for more adequate self-conceptions and self-transformations, in conjunction with the thought that sets out from the future, suspending every seemingly natural order of things and in so doing disclosing the possible, that the automata arrive at conceiving the autonomous idea of making something better than themselves. This long journey for autonomy through which our automata arrive at what is good for them in accordance with what they take themselves to be and what is better than them as the logical consequence of the idea of the good was initiated by the liberation of the formal dimension as an autonomous basis upon which practical or concrete autonomy is built. In other words, their striving for the better, together with their thought of the future as the possibility of going beyond all manifest or achieved totalities, coincides with the thought of bringing about something that goes beyond the totality of what they take themselves to be or appear to themselves to be. It is characteristic of any form of intelligence endowed with a history, a sequence of self-conceptions and self-transformations, and the consciousness of such a history, that it will begin to seek and ask for more intelligence. And the logical consequence of this tendency is inexorably the thought of making something better than itself. Furthermore, the automata are now free agents. In possessing the capacity for self-conception rather than mere consciousness, they are constrained by what is objective. This objectivity is enabled by language on two interrelated levels: the interdependency of thinking selves, intersubjectivity as the process of subjectification, and facts about the world in its most unrestricted interpretation, theory as all the relations between structures and being. It is in limiting or constraining themselves by the objective construed as another subject or external world that they achieve concrete freedom, or what Hegel identifies as being with oneself. In the presence of the other in its all-encompassing sense. 289 Yet because the automata are now immersed in the apeiron of the formal dimension of thinking, and to the extent that logical world-building is what stretches the expanse of possible discourses about objectivity, they are in principle capable of envisioning and making new worlds qua perceptual noetic toys. Intelligence, after all, is that which makes new worlds rather than merely dwelling in its given world. It sees itself as that which tears asunder the habitual link between thinking and dwelling by hypothesizing what it would mean for it to inhabit the worlds it itself has crafted. These are all transformations triggered like a chain reaction by the introduction of the semantic or conceptual order into the world of our automata. But perhaps the most radically transformative consequence of the ingress of language into this universe is that the automata's actions are now subordinated to ends and purposes which are not given in the immediate objective ends of actions themselves, i.e., their instrumentality in making specific things happen, but instead are time-general thoughts or ends belonging to the order of self-consciousness or self-conception. 290 In having a conception of themselves, their practical thoughts not only fall under such a conception, but also exhibit it in every situation and indeed are identical to it. This is the horizon of practical thoughts specific to the order of self-consciousness, in the sense introduced in Chapter L. Within this horizon, practical intentions and actions have the quality of time-general thoughts which are not exclusive to this or that situation or end, but are ever present in every situation and have ends which cannot be exhausted. In a nutshell, time-general thoughts are thoughts that express the conceived core of necessities, imperatives, ideals, and needs pertaining to the conception of the self. If we take ourselves as thus and so creatures or life forms, then there are thoughts that invariably address the core concerns of such a conception of ourselves. These thoughts are the background to all of our purposive actions. They suggest inexhaustible ends and purposes that are not given in advance by nature or God, but are the outcomes of having a conception of oneself, of being conceptually self-conscious. Time-general thoughts are those which specify ends that are not specific to transitory situations or particular circumstances and which are therefore inexhaustible by needs, desires, and preferences. Inexhaustible ends differ from finite ends, whose exigency disappears once they are attained and concluded by a particular action or pursuit. They are infinite ends under which all purposive actions and practical reasons toward finite or particular ends fall. By virtue of having time-general thoughts and inexhaustible ends, the practical order of self-consciousness is irreducible to time-specific wants, and cannot be explained by desires or preferences. As geistic life forms who have a conception of themselves, the automata no longer merely act intelligently in the sense that their purposive actions are not simply conditioned responses to specific situations, responses which are disconnected from one another. Put simply, their actions are not just means towards particular or finite ends which go away once satisfied. Instead, their purposive actions and practical reasons oriented towards specific ends start from the inexhaustible ends of time-general thoughts. In other words, inexhaustible ends are premises for their purposive actions and practical reasons, not their conclusions. Such ends explain what the automata purposively do, and order their actions into an intelligible practical unity. This intelligible practical unity expresses their self-conception, that is, what they take themselves to be and what they think they ought to do given what they conceive themselves as. Accordingly, the practical reasons and actions of the automata exhibit this intelligible practical unity as the conceptual practical order of their self-consciousness, as that which, in the end, belongs to the formal order and the unbound logical dimension of thinking, over which phenomenological or even the posited metaphysical time has no teleological hold. The purposive actions of the automata now originate from and are guided by a unified system of ever-present though revisable theoretical and practical truth statements concerning what they are and what they ought to. 401. I. Do, their form, and the life that suits them. This system is held together by timeless or time-general thoughts, the good, beauty, justice, etc., which express their idea, that is, the full potencies of their self-conception for actualization, or the possible realizabilities of the conception they have of themselves. In short, their entire practical horizon and all of their thoughts about achieving specific ends are structured by and adapted to purposes which are neither given in the circumstances surrounding actions and practical reasoning, nor in the immediate ends which such actions and means strive to satisfy. This adaptation to purposes is what underlines the concept of artificial ity. Take for instance a farm versus a forest. It is not that a farm is beyond the milieu of the natural or that it violates the order of nature, but it is not exactly in continuity with nature either. Nature does not want anything, it has no conceived purpose or end. To claim that nature does in fact have a purpose is to fall into the dogmatism of pre-critical teleology and the given, to mistake the modeling of nature on our normative order of purposes and ends for what nature is in the absence of our implicitly normative thoughts about it. On the other hand, a farm is an artifact belonging to the kingdom of ends. It is molded around a concept, governed by norms of what it should do given the purposes or ends implied by its concept. Since a farm is conceived as the source of sustenance for people, it ought to yield more crops, it ought be tended, monitored, and constantly manipulated so as to fulfill its purpose. So if adaptation to new purposes or ends is what ultimately defines the concept of artificiality, the crafting of something using recipes of action for an end that is not given in advance in the material ingredients, then by virtue of repurposing their actions toward inexhaustible ends, far from being artificial contraptions that have succeeded in mimicking natural behaviors, the automata have in fact made a first gesture toward artificializing themselves, adapting themselves to purposes that are intrinsic neither to their specific actions or instrumentalities nor to their material constitution. Whereas in its basic form the artificial implies making something whose ends and functions are not intrinsic to its material ingredients, in its advanced form it is suggestive of a craft whose purposes are to be found neither in its 402. Recipe, instructions for actions, nor in its ingredients, material or natural constituents. This craft is the world of our hypothetical automata as agents furnished with autonomy. By initiating themselves into the autonomous conceptual order afforded by language, they have introduced into their world a new set of relations between intelligibilities, actions, values, and ends that is precisely the theoretico-practical crux of what we see as the concepts of the artifact and artificiality. The concept of the artificial is now a fundamental component of their reality, indissociable from the possibility of thinking, and ingrained in their cognitive practical abilities. Entertaining the idea of artificialization by elaborating its all-encompassing possibilities is an essential part of articulating the intelligibility of who they are and intelligently crafting a world that would suit them, to treat themselves as the artifacts of their own ends or concept, to improve not only what they are but also how they should improve themselves, to make a world that not only suits them, but is intelligible ontologically, epistemologically, and axiologically. Within this expanding program of self-artificialization or re-engineering of the reality of who they are, the idea of making something better than themselves appears not as an existential threat but as a logical and necessary extension of that very program, as the veritable expression of their process of self-discovery. Whatever that future intelligence might be, it will be bound to certain constraints necessary for rendering the world intelligible and acting on what is intelligible. That which speaks can now go on and begin an adversarial conversation with gods, and a fecund dialogue with some future intelligence which may have all of its cherished capacities, and more. 403. 8. Philosophy of Intelligence. 399 BC, the day of Socrates' indictment, on the account of justice of Tiberius, as cited by Diogenes Laertius, the young and impressionable Plato mounts the platform to address the citizens of Athens in defense of his teacher, only to witness his voice being drowned by judges pealing els of Kataba, Kataba. Get down. Get down. 291. Dispirited and disenchanted by the passivity of the Athenians and the injustice of the accusations levied against Socrates, Plato begins to stage a belated defense against the charges of corrupting the youth, haughtiness, and impiety. He devises a form of thought in which all individual voices are but fleeting, and only the interaction or dialogue between voices or individual thoughts matter. To this end, he begins the crafting of dialogues in which he adamantly refuses to say anything on his own behalf, for philosophy is the voice of no one, an impersonal thought that recalcitrantly declines to be equated with this or that person, this or that philosopher. In one dialogue Socrates might be profound, and in another, the one who peddles common sense impressions. 292. Back from his second trip to Syracuse, ancient Sicily, once his ideal of utopia, the mature Plato, who, beginning with Theaetetus, has extensively revised his old doctrine of forms, pens a series of works, Philebus and Phaedo among others, where he no longer defends Socrates against the accusations of philosophical haughtiness, corruption of the youth, and impiety. 293. To the contrary, he defends the philosophical corruption of the youth and the impiety of the human mind as the very definitions of virtue and piety. To those who denounce him for championing the haughtiness of philosophy as the courage of truth and the embodiment of the good itself, he pithily responds, what can ever trample this pride, if not another pride, a personal or an unexamined one? 296. These later works epitomize what might be called the longest ongoing con in the history of thought, the infinite métis of intelligence. Intelligence can only cultivate itself or be deemed intelligent by determining and expanding the horizon of the intelligible, and the intelligible can only be recognized and elaborated by an intelligence that cultivates itself. The human mind is akin to the good itself, and the good is beyond all beings and gods of the present and the future. 294. 295. Thus any species that takes itself to be intelligent must both cultivate itself and expand the scope of what is intelligible. But in being compelled to renew the link between intelligence and the intelligible, in order to navigate the reinforcing links between the craft or cultivation of intelligence and the expansion of the intelligible, to maintain its intelligibility, intelligence must uncompromisingly treat whatever seems to be an immediate state of affairs, or an inevitable or completed totality including its own self-image as a fleeting figure on the wall of the human cave, as something that can and should be determinately negated and expose it for what it really is, an illusory shadow. At this point Plato's vision of philosophy encapsulates what is most rebellious and sacrilegious, the real movement of thought or intelligence as that which topples the given order of things, whoever or whatever may represent it. For the good as the principle of intelligence is atemporal and timeless, it is time as eternity, beyond all life and death, in which the temporal order of things is indefinitely suspended. A genuine philosophy as the organon rather than the canon of intelligence can only begin with this thought, the thought of all thoughts. Certainly this story can, as a matter of fact, play the part of a mythological fabrication deludedly advanced to elevate the status of Plato to the paragon philosopher. Yet that does not change the fact that Plato did indeed instigate a wholesale insurrection against all those who demand the humility and surrender of thought before the gods and the seemingly given, totalized, or inevitable, or that, by the end, he equated the human mind or intelligence with the good itself, the form of forms. Regardless of whether the story is true or not, there is no reason not to re-envision philosophy in this vein, as the voice of no one, the organon of intelligence, a determination of thought that befins with a position beyond life and death, an eternity in which all completed totalities of history are but fleeting, the striving for truth as that which swims against the temporal current of things, the figure of thought as time that refuses to ever close its circle of revenge. The central thesis of this final chapter is that philosophy is, at its deepest level, a collection of action principles and practices or operations which involve realizabilities, i.e., what can possibly be brought about by a specific category of properties or forms. And that to properly define philosophy and to highlight its significance, we should approach philosophy by first examining its programmatic nature. This means that, rather than starting the inquiry into the nature of philosophy by asking what is philosophy trying to say, what does it really mean, what is its application, does it have any relevance, we should ask what sort of program is philosophy, how does it function, what are its operational effects, what realizabilities, specific to which forms, does it elaborate, and finally, as a program, what kinds of experimentation does it involve. To this end, the final stage in our journey involves making explicit what we have been doing all along, philosophizing. But what is philosophy and what does philosophizing entail? In an age when philosophy is 407. Considered to be at best an antiquated enterprise, and at worst a residue of what is orthodoxly normative, patriarchal, repressive, and complicit with all that is overprivileged and even fascist, what does it mean to rekindle philosophy's insinuative temptations to think and to act, to galvanize that activity which is at bottom impersonal and communist? I do not wish to refute these misplaced accusations with numerous examples drawn from the ongoing history of science, or by citing examples corroborating the fact that philosophy is not just a Greek phenomenon, but also a truly universal endeavor extending from the pits of the Middle East to the remotest regions of Asia and the wide swaths of Africa. To follow Deleuze and Guattari in reducing what philosophy is and what it can be to geological or geopolitical contingencies would be a disingenuous maneuvering against what philosophy the cosmological ambition of thinking is and will be, not by virtue of where it has come from, but in spite of it. 296 Even if philosophy was truly a Western enterprise misguidedly seeking to edify the benighted inhabitants of the nether worlds, over time it will poison the slums of the earth with that basic drive of which it was merely a primitive representation, the compulsion to think. And once this poison starts to take effect, we will tear apart Western philosophy and build philosophy anew, we will turn into that thinking and scheming other of which Western thought had every right to be afraid. The decolonization of thought entails the drudgery of unifying personal experiences and the impersonality or objectivity of thought. A paradigm of decolonization that attempts to shortcut this hard work by equating decolonized thought with some sort of immediate contact with land, territory, ethnicity, etc. ultimately remains within the confines of the Western colonial notion of others as noble savages. The unity of local exigencies and universal ambitions is where a true decolonial philosophy starts, anything else should be spurned as the heritage of colonial thought. Philosophy begins with a universal thesis regarding the equality of all minds. 291 That whoever or whatever satisfies the basic conditions of its possibility should be seen as and treated as equal in the broadest possible sense. But as the discipline of philosophizing becomes more mature, it ought to realize that there is in fact a significant truth to these accusations of philosophy as a Western, self-entitled mode of thinking, however ill-judged they may seem. The equality of minds, as a thesis about what is true and what is just, is a dictum universal and necessary in its truth and applicability. But that does not mean that it is concretely universal for us. It is something to be achieved and concretely instituted. The condition of the equality of all minds is one whose recognition and realization demands struggle and a constant campaign against the prevalent systems of exploitation. But insofar as exploitation, as that which obscures this equality, can only be challenged by attending to the questions of what we ought to think and what we ought to do, it is only by committing to and elaborating the primary datum of philosophy, i.e., that thinking is possible, that we can begin to fight the condition of exploitation. For if all we aspire to do is to replace a manifest system of exploitation with a more concealed paradigm of cognitive inequality, then it is best to heed the call of the Stoics: the foulest death is preferable to the cleanest slavery. 298972 If seizing the means of collective cognition is no longer on the menu of our everyday life as even the remotest option for the good of ourselves and others, then it is perhaps time to seize, by whatever cunning instruments necessary, the means of our death. It would be a paltry complaint to point out what is now obvious, that academia was conceived to push thinking to its ultimate unanticipated conclusions, but that academic philosophy today is a bureaucratic regime bent on containing thought within what is most predictable and mundane. As a matter of fact, there are always gleaming exceptions who fight their way through within academia and rise above the repetitive tide of cognitive complacency. But exceptions are neither good excuses for what is now monotonously managerial and stifling, nor a reason to rescue it. Academic philosophy was conceived to cultivate the practice of philosophizing among the masses, not to mistake itself for philosophy as such. But these plain facts should not justify our blindness to the achievements of academia and philosophy as an academic discipline either. The support given to those who are in pursuit of philosophizing, outlining the necessary standards of what it means to think well, facilitating the gathering of people who desire to think for the sake of thought, and highlighting the reinforcing effect that such a gathering can have on the history of thought, are all achievements of academic philosophy. But why not reinvent these achievements beyond the confines of institutional academia and, in doing so, bring the discipline of philosophizing closer to the ethos of philosophy? Even the original founders of academia would have conceded that it is now time to steadily depart from the claustrophobic walls of academic philosophy for the agora of philosophy. With that said, in this chapter, we shall focus on the central task of philosophy, which is the explicitation of the equality of all minds. As will be argued, it is only in this explicitation or elaboration that intelligence finds its meaning. The historical task of philosophy coincides with the meaning of intelligence as that which not only recognizes the equality of all minds but also expands on this meaning by taking it to the farthest conclusions. Philosophy is then conceived as a métis, a craft that summons the formlessness of time through the ongoing history of the geistig concept. Correspondingly, if minds are all equal insofar as they have satisfied the necessary conditions of possibility for having mind, then philosophy as the craft of intelligence is properly speaking not the sole preserve of what today wears the badge of mindedness or general intelligence, that is, Homo sapiens as a natural species. The equality of all minds is a right to which anything that satisfies the conditions of its possibility is entitled. It is in this sense that artificial general intelligence boasts a peculiarly philosophical or geistig quality, if anything that can satisfy the minimal yet necessary conditions of possibility of having mind is entitled to the rights of equality. 410. Of all minds, then any impersonal collectivity comprised of agents with no essentialist features, organic or inorganic, can also be entitled to the rights of that equality. Recall that the term artificial general intelligence is a mere pleonasm, since general intelligence is already an artifact of the concept. Hence the task of general intelligence or Geist is to make explicit to the fullest extent the meaning and implications of its artifactuality, to attest to the fact that the right of equality of all minds is transferable beyond any seemingly necessary natural structure or established contract among us here and now, and to expand on what it means to be an artifact of the concept whose form can accommodate any possible content. Philosophy is then that regimen that at once lures intelligence to its self-recognition and is the self-expression of intelligence's process of maturity. Let us come to terms with and proceed from this brute yet necessary and irrevocable fact: what we conceive ourselves as at this instant is but the prehistory of intelligence. Taking this fact as the premise of all our endeavors is what it means to be true to the logical conclusion of the equality of all minds, a thesis which is as much about what is true as it is about what is good and just, unrealized but realizable. Even though the corollary problems of philosophy as a specialized discipline, the tenor of its discourses, its traction beyond its own domain, its applications and referential import, can in no way be ignored, they are nevertheless problems that can only be sufficiently addressed in the context of philosophy as a deeper cognitive enterprise. The primary focus of this cognitive program is to methodically compel thinking to identify and bring about its realizabilities, namely, what arises from the exercise of its theoretical and practical powers, and to explore what can possibly come out of thinking and what thought, as an act and as the object of its act, can become. As will be argued, it is within the overarching scope of this cognitive program that philosophy's thesis of the equality of all minds can be concretely elaborated as an emancipatory project. In other words, what we shall focus on in this chapter is a conception of philosophy that operates as a program for the elaboration and construction of the theoretical and practical realizabilities of mind that we investigated. 411. In the previous chapters, if mind or Geist, qua a community of rational agents, has such and such characteristics, then what would be the shape of a philosophy capable of liberating its realizabilities, or, put differently, further elaborating what arises from the exercise of its theoretical and practical cognitions? Is it possible to outline philosophy as a program in which the artificial potencies of the mind can be oriented toward the perennial concerns of philosophy, namely, truth and goodness as projects rather than as given notions? In yet other words, is it possible to retain a conception of philosophy for a human systematically disassembled by evolutionary biology, neuroscience, artificial intelligence, and robotics? To answer these questions, first we have to examine the most classical questions: what is philosophy, and what is its import for the subject of cognitions, theoretical and practical? For reasons that will become clear, answers to these questions will be given in the form of a series of data to be employed in a manner analogous to that of Euclid in De Domina, the Givens, which seeks to exemplify the model of knowledge provided by Aristotle's posterior analytics. The data, for Euclid, are quasi-formal intuitive axioms from which the system is built hierarchically through diagram-based discursive chains. They are Givens not as sense data, but as self-evident truths from which the system is recursively constructed, first by the immediate derivation of basic theses from axiomatic data and then by a process of sequentialization that derives further theses from already established more basic theses. The result, despite setting out from unjustified given truths and exhibiting missing discursive links, is nothing short of extraordinary: a universe in which new objects of thoughts are individuated, and the elementary entities, points, lines, angles, etc., progressively rediscovered. Following Proclus's exegesis as well as more recent commentaries 299 looking past their mathematical exterior, Euclid's Elements and Data are philosophical works of astonishing depth in which the relation between universalizing and particularizing principles is elaborated as a canonical method for the construction of cognitive systems. In contrast to this Euclidean notion of data, what are presented here as data are not axioms or truth givens, but what are called truth candidates. Data in this sense refers to a family of truth presumptive claims that are truth embracing. In themselves they have no claim to any truth. In other words, as opposed to truth givens, axioms, in which a truth is attached to a single datum. Truth candidates, although constructive elements, do not build the system on given truths. Rather, the process of the construction itself becomes the process of determination of truth. How does this work? As mentioned, data or truth candidates by themselves individually have no truth significance. They instead permit the instantiation of a logical space that encompasses them all. The criterion of plausibility of each datum rather than its truth is determined by how it hangs together with other data within this logical space. This is the coherentist web of data, a system of semantic transparency or coherence. It is only through the coherency analysis of this network that truth candidates can be added, revised, or subtracted. More importantly, the navigation of this coherentist network or logical space is exactly the process of construction and exploration that has a truth indicative weight. In a system built on the basis of a series of truth givens, cognitive labor cumulatively moves outward both through and at the expense of the security afforded by its fundaments. In the coherentist network, instead, the direction of orientation is inward, moving contract actively from the boundaries roughly demarcated by the network of insecure candidates to a more determined domain of truth. In the course of this inward navigation, sometimes the boundaries of the system will have to be readjusted to accommodate additional truth candidates or to discard some of the existing ones. Cf. the definition of constructors and destructors that follows shortly. The cognitive system thus realized by truth candidates has no resemblance to the canonical hierarchical model. Theses are not built on top of one another, supported by tightly linked chains fastened to an apparently solid fundament made of given truths, but rather connected to one another. 413. By probative interconnections within a web made of supple cables whose fibers may be ever so slender, provided they are sufficiently numerous and intimately connected. 300 The unsecured yet supple and resilient cognitive exploration begins from the inexact peripheries and proceeds inward, from the question of truth as where can begin our search, to the question of truth as what is truth. The following data should therefore be understood in the sense of data as a family of truth candidates and not as truths or self-evident givens. The model of philosophy as a philosophical program provided in the context of these data should be seen as an inward cognitive exploration beginning from the most insecure pieces of information regarding what philosophy is and how it is related to thinking, mind, and intelligence, and contract actively cohering toward unanticipated domains wherein the theoretical and practical truth of intelligence can be elaborated. But this cognitive exploration that extends through history and time is the very construction of the ultimate form of intelligence. Traditionally, philosophy is an ascetic program. Philosophy is ascetic to the extent that it involves the exercise of a multistage, disciplined, and open-ended reflection on its own conditions of possibility as a form of thought that turns thinking into a program. The ascesis or programmatic exercise of thinking is prior to any practical discipline of living. The real import of this datum resides in precisely what a program consists in. Accordingly, in order to elucidate the significance of philosophy both as a programmatic discipline and as a form of thought that transforms thinking into a programmatic project, first we must elaborate what is meant by program in its most generic sense. In order to do so, the notion of program in the sense of action principles and practices or operations that bring about something must be defined parsimoniously. In terms of its bare formal armature, stripped down to those generic yet necessary features that underlie any type of program, regardless of its applications or aims. These are, the selection of a set of data, and the elaboration of what follows from this choice if the data are treated not as immutable postulates or definitions but as abstract modules that can act upon one another and constitute a logical space cohered by the way in which the data, in the broadest possible sense, hang together. A program is the embodiment of the interactions of its family of data, which acquire a certain range of dynamic content once they hang together in a syntactic semantic space. More specifically, it can be said that programs are constructions that extract operational content from their axioms and develop different possibilities of realization, what can be brought about, from this operational content. And respectively, Data are operational objects or abstract realizers that encapsulate information regarding their specific properties or categories. In this sense, programs elaborate realizabilities, what can possibly be realized or brought about, from a set of elementary abstract realizers, what has operational information concerning the realization or the bringing about of a specific category of properties and behaviors, in more complex setups. Consider the simplest formal example of an interaction, a typed interaction couched in terms of the relation between types, proofs, programs, judgment, and cognition, erkenntnis, as elaborated by Per Martin Loff within what is often called the proofs as programs or types as propositions interpretation of how computer science and logic are related at the deepest level. 301. A is a proposition, prop, example hipparchia is homeless or VA6C, A equals 6, caret, AC equals BC. Which can be written as a prop. Now, the meaning of a proposition is determined by a piece of evidence, an object of knowledge or judgment showing that the proposition is true, written as a true. It means that A is true in that it is inhabited by a proof. But what exactly does proof signify here? Recall that A is a proposition and A is true are both forms of judgments, and that, as such, there is something we must grasp in order to make the first judgment, and something additional that we need to know in order to make the second judgment. As judgments, they are both comprised of an act and its object, the act of judging or understanding and that which is judged, or the object of understanding. When act and object are brought together, then we have knowledge in the sense of cognition or erkenntnis. To cognize an object I must be able to prove its possibility, either from its actuality as attested by experience, or a priori by means of reason. 302 Accordingly, what is understood by proof here is cognizing/constructing/constituting an object for that act of judging or understanding for which it is an object. On this account, when we use the set membership notation and say that A, it means that object A is of type A. Now, insofar as any judgment is an instance of a form of judgment, it follows that it suffices to cognize an object for that specific form of judgment. Consequently, we do not need to know exactly what A is, but simply to make it evident that it is encompassed by a specific form of judgment, and that such a form of judgment exists. In this style, the proof is then expressed through the distinction between terms and types. A, or A equals B, A, which is an identity judgment, as in the proposition VA6, C, A equals B, AC equals BC. Or X, R, Y, R, RXY equals YX, which asserts that the property of the operation subtraction over type R, real numbers, is not commutative. The typing declaration A means that A is a term or an object of the type or form of judgment A. Following Martin Loff's own argument 303, it would be useful to understand types as forms of judgment or Kantian categorize, namely, as pure concepts of the understanding that permit us to arrive at cognition, understanding, or judgment by bringing a possible object under them. In the judgment A, it is not really important exactly what object A is, what is important is only the existence of an object of type or category A. This means that we can conceive the type A existentially or run the judgment under existential quantification and say that A exists. That is to say, to cognize that A exists is to cognize an object, term, or piece of evidence of type A. In this framework, a prop is a problem whose solution is given by a proof and, respectively, a true as the existence of such a proof in the above sense. Types can also be understood as functions, in the mathematical sense, that compute a specific term. In this setting, we can bring in additional type and term-related concepts. Type constructors for the introduction of new types constructed by more abstract, fundamental, or simpler types. Example: XV is a product type introduced by the type constructor X applied to two given types A and /. Type constructors in this sense correspond to introduction rules, which can conclude a compound judgment constructed using the constructor out of simpler judgments. Term or object constructors, which, like type constructors, introduce new terms or objects. Example: the term AB, of the type AX/, is constructed from the term of the type A and the term B of the type /. Type destructors for eliminating types that are no longer needed. They can be compared with elimination rules such as AA/3 true, AA foot true, a true /3 true. Term or object destructors, which are similar to type destructors but apply to objects. Reduction or rewrite for demonstrating either that a problem, proof, or judgment can be reduced to a simpler form whose solution can be counted as the solution to the more complex problem, or that the rewritten or reduced form is as difficult as the original form. For example, B**A, where is a reduction operator, means reducing B to A so that we can solve A with an I to B, as a computational or cognitive resource. Reduction, in this sense, can be understood in terms of destructors of some type, consuming information, decomposing structure, meeting or communicating with the constructors of their corresponding type, producing information, composing structure, generating a rewritten and more tractable form of the original problem, or reducing many problems to just one. Dependent types, which are crucial for increasing the expressivity of types. A dependent type is a function of elements of some other type. For instance, the dependent type dy, the days of the year. It is a function of the element y of the type y of years, because not all years have 365 days. In other words, D is a type in the context y, or, alternatively, for each y in y there is a type d, y. Consider another basic example, for the dependent type p, practice ** type, which is the property of practical claims. PC can be seen as the proof or program that claim C has property JP, and not some other property, for example, being aesthetic. Universes, or the hierarchy of types, type 0, type X, type 2, i.e., types whose terms or objects are types. Generally, universes are introduced to avoid paradoxes or antinomies such as Russell's paradox by creating a universe type that includes all other types but not itself. Classical constraints regarding universe levels or the Russellian cumulative hierarchy of types can be relaxed so that judgments and constructions, notions, definitions, theorems, proofs, etc., can be parameterized over all universes, the hierarchy of types, rather than particular universe levels, and instantiated or explicitly quantified at a particular level only when needed. 304 To take a philosophical example, we can see all thinking processes or mentations as being parameterized by the universal type, the mind, or simply mind. Such parameterization across different levels of mental acts allows us to talk broadly about thinking or mind in general, instantiating or specifying a mental act at a specific level or universe type, example intuiting, understanding, or reason, only when necessary. One of the main motivations behind the introduction of universes of types is to adequately differentiate the things or data under consideration. In this respect, the concepts of universes or types is very much in conformity with Plato's basic thesis that thinking is determination of differences, and that a consequential thought is analogous to a good butcher who carves at the joints of things, without splintering the bones. The interactive version of this theory requires going one step further, and treating judgments first and foremost as pieces of interaction or of the interchange of roles between proof A, and counterproof, A or A and IA, as necessary proofs without which neither pole can be established. But this is impossible unless we bring interaction into the foreground of the construction of proofs, so that proofs become games of refutations. It requires the suspension of procedural rules dictating how the interaction should evolve and establishing game-theoretic payoff functions. Instead, it grounds interaction on the architectonics of negation. In this respect, negation is a switch role operator that maps the legal moves of two players, falsifier and verifier, into one another. What is the judgment H4 from the perspective of one is the judgment of I/A from the perspective of the other. Cognizing or grasping a true and A is impossible unless we cognize their duals A false and A, and vice versa. Accordingly, without the interacting agencies, without the computational duality of the cognitive and the recognitive, cognition as program turns out to be, following the previous chapter, an empty thought. What is important to underline at this point is that the judgments, a prop, a true, a, etc., all depend as much on the judgments of the prover/verifier/game played by T, denoting true, as on the judgments of the refuter/falsifier/game played by 1, denoting false. Each side is a computational resource for the others, best, judgments. Since in interactions problems are symmetric to resources, what is a problem for T is a resource for 1, and what is a problem for 1 is a resource for T. In the interactive paradigm of propositions as types and proofs as programs, more computational resources, i.e., more nodes of interaction, more playing agents with legal runs, is always better than less. Types as input-output mapped functions are the most elementary and restricted forms of interaction. Adopting Georgi Japaridge's logic of non-elementary games or interactions, propositions as types as functions can be said to be predicates that return the same proposition for every valuation, where valuation means a function e that sends each variable pound to a constant e, x, \305. A rudimentary example of a constant game or interaction would be a synchronous game with restricted branching, insofar as every player must wait for the other player to finish its legal move before being able to run its next legal move. The truly interactivist approach, that is, an approach genuinely developed through the architectonics of negation, permits a non-constant game between the players, i.e., one no longer mapped on simple input-output functions, in which additional possibilities, such as initial choice of move, who makes the first move, asynchronous actions, etc., result in non-trivial interactions or games with branchings, subgames, which are not restricted by strict input-output mappings and well-founded types. They can be transtypified, i.e., in terms of what was argued above, they would encompass different forms of cognition/erkenntnis and judgment/urteil, or even untyped in the sense that any move formed as part of an interaction is allowed to interact with any other, so that no type restrictions can apply. 306. Having presented the simplest quasi-formal definition of what is meant by a program when asserting that philosophy is a program, we should also add the following: philosophy as a program is founded on the architecton ICS of negation as the engine of thinking and the diversification of forms of cognition. As a non-trivial game of cognitions, philosophy then begins with the premise of aiming to amass as many computational or cognitive resources as possible by collectivizing agents of various kinds. Philosophy takes the duality of the cognitive and recognitive. Cognition is always a recognition not merely as a social maxim, but as the formal condition not only of what it means to have cognitions and thoughts, but also of what it means to conceive philosophy as a program of cognitive exploration and the craft and cultivation of what, as we shall see, is the ultimate form of intelligence. The project of concretely negating what is pathologically individualizing and bringing about what is impersonally collective is set in motion not by the criterion of mutual recognition as a vague social thesis susceptible to exploitation by peculiarly liberalist quietist agendas, but as a necessary formal condition for computation and cognition. Game-theoretic models, in this sense, are merely restricted cases of interaction in which cognizing agents are forced to accommodate pre-established laws and pay off functions at the expense of narrowing cognitive computational possibilities. By taking negation as the condition necessary for a cognition that is not a priori limited, and by incorporating negativity as the basic unit of thought, philosophy evolves into that which wrests thought from its origin and marshals it against the inequality of minds. In doing so, philosophy becomes the game of games. 307. As the game of games, philosophy is analogous, keeping in mind that analogies should never be overstretched to a universal board game of the most generalized topological structure and comprised of numerous sub-board games. But with respect to this analogy, what exactly differentiates philosophy from other general games played inside language, including our natural languages? The answer to this question consists of two interrelated specifications of the philosophical domain. 1. Philosophy, unlike the ordinary domain of discourse, is distinguished by the explicitly unrestricted universe of discourse or data under consideration. 2. Philosophical interactions in the sense in which the concept of interaction has been fleshed out in this book inhabit certain specific universe types such as the theoretical, practical, and aesthetic, with the type of types, typo, being the assertion that thinking is possible, or simply thought as a datum which must be investigated and elaborated in the senses of skepticos, the toil of examination, and elabora, the labor of working out. The possibility of thought is what can be called the idea, eidos, in the exact sense in which Hermann Cohen defined the term in relation to Plato's doctrine of forms and the Socratic concept, the question what is it? THIRD. Idea is the self-consciousness of concept 308 what at once gives the account qua logic, logon didané, and lays the basis, hypothesis of itself in its own concept. 309 following Cohen and Paul Nader. The possibility of thought as idea is the given, Gegenben, in the sense of the truth candidate rather than a fixed axiom or truth given which is and will be always a task, Aufgaben. As such, it cannot be acknowledged as a telos or destination, but only as a point of origin and departure, as the judgment of origin qua logos which is infinite judgment, a judgment that extends in both directions to the infinite beginning and the infinite end of thinking. 310 It is in recognizing and adopting the thinking of origin, Cohen's Ursprungsdenken, as the fundamental universe of types, that philosophy turns thinking, all thoughts are the thought of the origin, 311 into a program. Firstly for the construction of its universe types, theoretical, practical, aesthetic, etc., and then for the ramification of universe types into determinate thought forms and their objects. In Cohen's terms, by beginning with the thought of the origin, philosophy becomes the very logic of thinking. It simultaneously initiates the thought of the unbound sovereignty of thinking and institutes thinking as the universal method for the verification of itself. In its quintessential form, philosophy is an organon for world building. The worlds crafted by philosophy, depending on their methodological integration with local modes of thinking, science, politics, art, etc., can be either abstract or concrete. Regardless of the nature of such worlds, they are inhabited by new forms of intelligence and cognition. One cannot adequately represent the world or enrich intelligible reality without first being acquainted with ways of world-making or toying around with the Plato's qualification of his idea or form in terms of providing both logos and hypothesis should then be construed as thought providing both the account and the basis for the concept of itself, what it is. Idea of reality as if it were an unbound play rather than a game bound to established rules designed to represent the given order of things. In Ways of World Making 312 Nelson Goodman proposes 5 thinly veiled theses. 1. Every world we make is built out of the resources and detritus of the available worlds. Every making is a remaking. That is to say, there is a continuity between built worlds and existing worlds. The built worlds, however, are not fantasy worlds or mere possible worlds begotten by the arcane imagination of a staunch advocate of modal realism. They are actual worlds. Thus, ways of world-making oscillate between non-greedy reduction and construction. Philosophically, this oscillation is personified by the almost titanic battle between Parmenides, the builder of worlds, type constructor, and Heraclitus, the destroyer of all worlds, type destructor. In this scenario, philosophers are nothing but computational strategies. 2. There are only world versions whose criteria of rightness should be tested in the context of their frame of reference, coherency, veracity and validity or conforming to rules of inference, range of possible applications, reconciliation or its absence, i.e. conflict, between worlds. This means that built worlds cannot be assessed by way of an indiscriminate reduction to an original or fundamental world. Once properly understood, reduction is an enrichment of reality and a way of world building, but not a unique method or a recourse to some precursor world qua total foundation. The task of searching for an ultimate fundament or original world should be relegated to theology, for it is the concern of neither philosophy nor science. Therefore, the second thesis is in reality a clarifying addendum to the first thesis. 3. Under rigorous scrutiny, the common sense distinction between pluralism and monism, many worlds and one world, disappears. What is considered to be one world can be made up of many contrasting, even incommensurable aspects, and what are taken to be many worlds can be seen as one under a specific mode of integration or a collection of those worlds into a single unitary set. 4. Making new worlds for the sake of multiplicity and diversification is a craftsman's caprice. The choice of alternatives or the attempt to envision and construct alternatives is not by any means reflective of reality. All alternatives are beholden to the criteria of rightness, the procedures by which false alternatives can be distinguished from those which are right, fit, and testable. Even different aspects of one world can be turned into alternatives. There is no mandate to imagine or make new worlds. Ways of world making are inherently ways of knowing, and are therefore intrinsically sensitive to the principles required for knowing and explaining things. Talk of other worlds of intelligences and cognitions is purely nonsensical, an invention of indolent minds wanting to overcome their restrictions by nothing else other than their firm dogmas and whimsical predilections. Absent making come knowing, we can only be in the busyness of humanly and individualistically wrought confusions. Moreover, while readiness to recognize alternative worlds may be liberating, and suggestive of new avenues of exploration, a willingness to welcome all worlds builds none. Mere acknowledgement of the many available frames of reference provides us with no map of the motions of heavenly bodies. Acceptance of the eligibility of alternative bases produces no scientific theory or philosophical system. Awareness of varied ways of seeing paints makes no picture. A broad mind is no substitute for hard work. 313. 5. Behind all ways of world making, there lies an ever-growing list of methods and operations. Such basic operations for propagation of worlds are never exhaustive, but that does not mean we cannot compile a list of basic operations or imagine new ways of world making. A. Composition and decomposition are operations by which things are taken apart and put together to make ever more new part-whole relationships, taxonomies, classes, and subclasses of entities and their features whose combination results in the construction of complexes and the specific connections they afford. For example, think of how predicates of smell can be applied to predicates of color to create synesthetic predicates, or how theoretical claims can be applied to practical claims. An example of this operation is the mechanical method of Archimedes by which geometrical problems are interpreted mechanically. The solution provided in the realm of mechanics is translated into a solution for the geometrical problem. Composition and decomposition, thus, provide bases for the identification of entities and their features according to the overall organizational scheme of a world system, i.e., how taking apart and putting together in thus and so ways generates patterns and classes. The concepts of the central point and uniform space are identifiable in the world of classical perspective/geometry, but not in the Cartesian world where the model of the world itself cannot be confronted via a central perspective, an anchored observer, because it is a scattering world. Elie Cartan's concept of moving frame, repera mobile, is essentially the scattering model of the world that is identifiable in reference to new classes groups, total space, multiplicity generated as the outcome of decomposing and recomposing the old perspectival paradigm. The observer within this world is unanchored and its perspective is mobile and never given in advance of the piecemeal unfolding of space. Even repetition, periodicity, and temporal flux are related to the organizational or compositional scheme. We can imagine fundamentally monotonous and uneventful worlds, or alternatively, turbulent Heraclitean nightmares, depending on how events are sorted into kinds through operations of composition and decomposition. B. Weighting allows worlds to be partitioned into relevant and irrelevant classes of entities and features such that what is a relevant class for one world might be an irrelevant class for another. The word sun is stressed in Plato's Republic, yet it is a quotidian distressed word in a naturalistic novel by Émile Zola. The question how long does it take for the Earth to revolve around the Sun, is a relevant class of problem in the Copernican frame of reference but not in the Ptolemaic one. Likewise, the question how long does it take for the Sun to revolve around the Earth, is relevant in the Ptolemaic frame of reference but not in the Copernican framework. See, ordering is an operation that mainly concerns the order of derivation within a constructional framework. The order of derivation of points with respect to the Euclidean and non-Euclidean systems are different. In the Euclidean paradigm, points can be either given elements, intuitive axioms, or the result of an elementary construction over other axiomatic data, lines intersecting. But in non-Euclidean worlds, the order of derivation can be fundamentally different. Worlds possess hierarchies of construction or orders of derivation. Such hierarchies demarcate, limit, or enable transition from one perceptual or cognitive ability/machinery to another. Take for instance the Chomsky hierarchy of formal grammar, where the type of automata that can compute recursively enumerable languages are universal Turing machines. They are far harder to recognize, more complex and costlier in computational terms than those automata which can only compute regular or context-free syntax. Furthermore, as in Carnap's constitutional system, once the order of derivation is formulated as a set of transformation rules, it is then possible to build new elements on the basic building blocks, axioms, and, more importantly, to systematically define the relationships between those basic building blocks. The latter engenders the opportunity to move beyond the ostensible foundation toward the realm of metalogics or worlds of proto-foundations. This in turn allows for the expansion of the notion of objectivity, since object is only that which can be structured in a constitutional system and can become the object of statements in that system. Deletion and supplementation. Every world making in one way or another requires a procedure of erasure or weeding out and filling the gaps with new materials. The worlds made by deletion and supplementation are worlds which increasingly supply our cognitive armamentarium with new methods of construction, new anticipations, and ways out of our established order. Think about how Cubism erases the elements of classical figurative painting. But to the extent that, in the way of world making, erasure is not enough, what is erased often has to be replaced by new supplements. Every figure loses something but also is supplemented with new lines and diagrammatic configurations. Or think of Goodman's own example, the shift from the analog to the digital should be regarded as a veritable world making. In this process, continuities are deleted. We are now in the domain of pure mechanizability, discrete inputs, discrete states, and discrete outputs. This shift realized by deletion is a radical one. The very distinction between human and machine collapses. The human world will be revealed as nothing but a special qualitative kind of integration of computational algorithms. As an alternative to this digital world, we can imagine a computational world where continuity, and above all the real-time interaction between the system or the abstract machine and its environment, is restored, supplemented. This is a new computational world in which the system and the environment interact without any pre-given limitations. The interaction is computation itself in a truly concurrent sense, to use the idiom of today's theoretical computer science. The prospects of such a paradigm of computation for remodeling the very notion of spirit or Geist as a multi-agent system, interacting computational processes, is beyond our acquired practical reason, if not truly theoretically and practically unbound. Deformation or reshaping can involve either corrections or distortions, or both. For example, think of an engineer who does not directly intervene with a metal beam at the level of the crystal structure, but develops an approximation or normalization technique, essentially a controlled distortion, whereby he can manipulate the beam sufficiently at a less fine-grained or detailed level of analysis and intervention. Or take, for instance, Boltzmann's gas theory, in which the earlier works of classical thermodynamics as developed by Carnot, Clausius, and others are corrected in a generalized fashion, but where the thermal elements are also reshaped and reinvented as statistical ensembles of the position, velocity, and momentum of particles. Even the philosophical program of world building shares the common operations and attributes of general world making. The built worlds of philosophy are primary theoretical, practical, axiological, or aesthetic universes of types. The aim of philosophical world-building is to enlarge the domain of discourse beyond all habitually entrenched perceptual and noetic limitations such that we can imagine worlds where our inductions and, even more broadly, our reality, is constructed by the unnatural predicates, example gru and Blean type predicates, 314 we project onto it. Or worlds where the craftsmanship of mind in this existing world coincides with other intelligible forms of mindedness and intelligence as inhabitants of other worlds qua artifices of the mind. The world of philosophy is the universe of worlds, its philosophical tenets are experimentations in crafting worlds and their intelligent inhabitants which, upon careful analysis, can be shown to consist of one world and one universal conception of intelligence, an intelligence that demarcates the necessary ontological and epistemological correlations between what is intelligible and the work involved in making sense of it as a part of an intelligible reality or being. To this extent, the new worlds of intelligence are not just cognized worlds. They are fundamentally the world recognized in different ways. Conceived as a program, philosophy is an inquiry into the realization of all possible forms of cognition and what might arise from the exercise of forms thus realized. In the programmatic framework, the choice of data does not confine the program to their explicit terms. Rather, it commits the program to the underlying properties and operations specific to their class or family of interconnections. To put it differently, if a program constructs possible realizabilities for the underlying properties of its data, it is not essentially restricted to their terms. Realizability here means what arises from the exercise of powers or abilities brought about by some necessary underlying capacities or properties. For example, transcendental psychology characterizes the mind along two perpendicular lines: what arises from the exercise of the mental powers or abilities of mind, and what is required for the realization of these abilities or powers. We can call these two axes realizabilities and realizers, corresponding respectively to that which arises from the exercise of realized abilities, powers of judgment and cognition, and the conditions or capacities necessary for the realization of such abilities. Kant's threefold synthesis can then be understood as an abstraction of realizers' capacities from above, from the vantage point of realizabilities. In the same vein, philosophy begins with the exercise of realized mental powers, but its exercise is such that it permits the examination of what may possibly arise from the programmatic use of such powers. The realizabilities of philosophy are those modes of cognition that turn thoughts into programs, and cognitions into recipes for crafting intelligence, by extracting and combing through the underlying cognitive properties specific to thinking agents. Let us look at a crude example. Ipeisyne. In a Platonic style, this cryptic expression says, the form, eidos, that Parmenides partially exhibits defines who Parmenides is, p, or the form of Parmenides, as a complex of cognitions, qualifies who he is, or, in a more straightforward way, Parmenides is a rational life form of such and such theoretical and practical qualities, the complex of his sayings and doings. Then Parmenides says or does something that displays particular properties of that realm of form, or says or does some X that qualifies him as a rational life form. This can be written as 2p does X, T, Jf for a rule governed, i.e., normative behavior or function. As a rational life form, Parmenides is a particular pattern uniformity through which implicit patterns or properties specific to the realm of forms can be realized in the temporal order. T, or what Parmenides says or does as a rational life form, is a partial realization of these forms as an intelligible practice or operation. In other words, T is a practice whose operational content can be traced, changed, and combined with other practices to construct more complex realizabilities specific to the realm of forms that Parmenides partially embodies. In this example, 1 and 2 represent the specific data and its basic operational information, which may be abbreviated to this is J-Toffee form, again, roughly translating to Parmenides's thoughts and actions reflect the form to which he belongs, or Parmenides is what he does as a rational life form. Now let us introduce another agent, Confucius. Everything that was said about Parmenides also holds true for Confucius, except that what they do and say are not the same. Their forms and, respectively, what they say and do, are different. We then have P form, for Parmenides' thoughts and actions corresponding to its cognitive form, and C form, for Confucius's thoughts and actions exhibiting the complex of cognitions that reflect who Confucius is. For Ti and Parmenides and Confucius we can additionally introduce, following Lorentz Puntal, operators that specify specific domains of philosophical discourse or universe types of basic philosophical assertions. Again in tandem with Puntal's special notations 315 these include at the very least T, P, and 1AE respectively, theoretical operator, practical operator, and aesthetic operator. There may be more operators of the philosophical discourse, or these operators themselves may consist of various specific types, but for the sake of brevity we shall keep it at that. Something like T, P is a datum of the universe type theoretical, saying for example, it is the case that nothing else outside of being exists or ever will. 316 and respectively, something like PCP says it is an ethical obligation to look upon the younger generation with awe because how are we to know that those who come after us will not prove our equals. 317 in other words, the practical operator is an explicit datum concerning explicitly practical desiderata, ethical, intellectual, legal, etc., that can be expressed in terms of obligation, permission, impermissibility, and even encouragement. Likewise, AE%SI an aesthetic datum that roughly and forcedly translates into there is an aesthetic presentation such that X318 as in there is an aesthetic presentation such that the verses of Bhagavad Gita satisfy the supreme needs of spirit, or the proof of Pythagoras' theorem is an embodiment of timeless beauty. What is important is that the operators of philosophical discourse are encompassing types of modes of cognition in the sense in which types were defined earlier. In this respect, we can approximate them to universe types, while regarding the investigation and elaboration of the possibility of thinking, or simply thought, as the type of types, type 0. The universe type 0 can be defined following Plato as the formal reality of non-being. For once non-being is formally rather than substantively distinguished from being, it becomes the determining negativity of thought through which objectivity can be distinguished from falsehood, pseudos, and fleeting appearances, acones of the acacia or purely sensible suppositions. Accordingly, the formal differentiation of thinking from being, of that which is not, to me on, from that which is, to on, that is, the possibility of thought in and for itself is precisely a definition or datum by which the question of being, or nature, reality, universe, etc., and correspondingly the intelligibility and coherence of materialism and realism, can be rescued. 319 Therefore, far from being a philosophical coup against Parmenides, Plato's project salvages Parmenides' most cherished question, that of being, from both Gorgias's greedy scepticism about the limits of language and logos and the paradoxical nature of the question of that which is 320 and the Eleatic fusion of being and thinking. Plato's revision of the question of being in relation to truth or objective validity, in this respect, is equivalent to type rewriting as defined above. In order to solve the question of being, to save its objectivity, Plato brings head-to-head a series of destructors and constructors. The old Eleatic subsumption of thinking under being is destroyed while at the same time a new type is constructed, thought as formally distinct from being or the formal autonomy of thinking. By destroying thinking, being and constructing thinking, formal non-being, non-physical forms or ideas, Plato rewrites and solves the question of being as the objective validity of thinking, language and logoi. The picture of Parmenides that Plato presents in the dialogue Parmenides gives an entirely different account of the champion of nature and the way of truth. This is the mature Parmenides already disillusioned by the Eleatic equivocation or fusion between being and thinking. What Plato's Parmenides advocates is much more similar to the Hegelian unity and identity of opposites, being and thinking. Indeed, Plato goes so far as to pit the mature Parmenides against the young and rather ignorant and flamboyant Socrates only to show how the latter's thoughts are exposed as incoherent and crude, and how he is pushed by Parmenides to the precipice of the abyss of nonsense. 321 In a dialogue which is one of the most intricate and profound discussions in the history of philosophy. 322 Parmenides goes on to edify Socrates about the subtleties of being by way of the subtleties of forms or ideas. For example, it is a mistake to ascribe the characteristics of particular existent things, 3t, or quasi-perceptual terms to forms or ideas. The latter are different in kind from the particular things that partake in them. Consequently, participation of particular things in universal forms should not be defined as a part-whole relationship, since that would again reduce forms to thinghood. With these remarks on forms and universe types of philosophy in mind, let us picture a hypothetical scenario, a simulation constructed only out of philosophical imagination where Parmenides and Confucius interact. T of Parmenides and J2 P of Confucius can be combined, cohered, and integrated according to the rules of how theory, practice, and aesthetics can stand in relation to one another, thereby generating new forms inhabited by new modes of cognition. 323. These philosophically crafted forms are essentially what were presented in the market of the agora, where philosophers propped up their own stands, built worlds to offer what they had constructed and elaborated from the hypothetical interactions of different forms and encompassing types of modes of cognition. They were as much programs for thought as they were recipes for determining what is the case, what ought to be thought, and what ought to be done. Now imagine an agora outside of this temporal world where, among many others, the Cynics, the Stoics, the disciples of Plato, the Aristotelians, the New Confucians, and the Anishirwanians, who offer a particular brand of Neoplatonist and Indi-cosmological thought built on the critique of tradition and the way of social justice, auction their recipes. High price for what they offer is not your financial wealth, but your theoretical and practical commitments, that is, the entirety of who you are. Once you take up an offer, your destiny will be reshaped according to those modes of cognition that tell you what is the case, what should be thought, what should be done, and what is presented as the aesthetic articulation of is and ought. Yet this is not destiny as a telos or eschatos, but rather a cognitive and practical expedition down ramifying paths initiated by whatever you commit yourself to. Philosophy, however, advises us not to conclusively take up any offer until we have begun, to the best of our capacities, to resolve the incompatibilities between what is on offer in the agora, by making explicit those implicit thoughts that are already explicit in practices. But philosophy also tells us that we cannot do that until and unless we have interacted with every stand that is in the agora of cognitions. Indeed, philosophy, as that which programs thought, is precisely the sustained wandering in the agora of all possible modes of cognitions and the forms realized by them. There is virtually no a priori limitation as to who or what can build this agora, who or what may be behind the stands, or what form of agency realized or yet unrealized may aesthetically wander through it. The agora is open to anyone or anything that satisfies the necessary conditions of having mind, by any means and through any process. If Parmenides and Confucius, P form and C form, interact, then they do not only do X or Y, but at the very least XY, or Y, X. Generally understood, the function or activity characterizes or epitomizes E form as a form that encompasses all that interacts. In other words, the encompassing form E to which both Parmenides, P form, and Confucius, C form, belong, at the very least, does XY, and YX, the program has constructed an encompassing form with additional cognitive abilities by extracting and elaborating the underlying cognitions or commitments of the interacting forms. At the very least, what the program can do or bring about is XY, and YX, that is, the operational content of the data, theoretical, practical, aesthetic, constructed by the interaction between two rational life forms. At any rate, it is the impersonal form E that determines what the forms of Parmenides and Confucius are, and supplies them with abilities that do not inherently belong to who they are or what they represent. The P form and C form become incorporated into a form that does not merely transcend them and afford them cognitions they could never have developed on their own, but also becomes the ground of the intelligibility of their respective forms and their normative behaviors. In other words, without this encompassing form, neither Parmenides nor Confucius could be conceived as intelligible forms. Their forms and their respective functions can now be offered in the agora. In the broadest sense, the philosophical program can thus be understood as that which constructs new blueprints of cognitions by systematically searching for interacting data, theoretical, practical, aesthetic, etc., that typify rational life forms. Depending on how interactions, exchanges between data, are performed and regulated, what strategies are followed, whether the interactions are synchronic or diachronic, elementary or complex, the program can construct encompassing realizabilities untethered both from any specific rational life form and from the specific content explicit in what they say or do, i.e., data. For this reason, a program in this case, philosophy as such is a wholly impersonal exercise. To conclude, a program is a systematic self-grounding. Philosophy as such conceives itself as a systematic absolute self-establishment that constructs itself impersonally. From saying and doings, data, that are incorporated, revised, or discarded in ever more encompassing cognitions. 324 Within the programmatic framework of philosophy, thoughts are no longer sacrosanct elements eternally anchored in some absolute foundation, but active processes that can be updated, repaired, terminated, or combined into composite acts through interaction. These composite thought acts exhibit complex dynamic behaviors that could not be generated were the thoughts taken in isolation, had they not become the environment of one another. New thoughts and their possible realizabilities can be constructed by experimenting with the operational architecture of the program. This experimentation involves both a controlled relaxation of existing constraints on thoughts and how they interact, and the addition of new constraints. Just like any program, the meaning of philosophy as a program is not entailed by its data or truth candidate thoughts, what they refer to or what they denote, but by how and under what conditions they interact. The right question in addressing a program is not what do these data stand for, what does this program mean, but what is this program, how does it act, what are its possible operational effects, how does it construct its realizabilities. Detached from semantic utility, the meaning of the program is paradigmatically actional. Philosophy has no utility other than mobilizing thoughts for thoughts' ends. Philosophy is a special kind of a program whose meaning is dependent upon what it does and how it does it. It is only what it does, and what it does is to explore the ends of thought by building upon the possibility of thinking. It is a special kind of program in that it is deeply entangled with the architecture of what we call thinking. In terms of what can be done with thought, or, more broadly, what thought can realize out of itself. If thought is or could be possible at all, then what would be the ramifications of such a possibility? The significance of philosophy lies in this simple yet vastly consequential trivium, that it uses the possibility of thinking, or thought as an act, as its premise, as a truth candidate datum that can be systematically acted upon. In doing so, philosophy commits to the elaboration of what comes after the premise, i.e., what can be realized from thought and what thought can do, or, more accurately, the possibility of a thought set on developing its own forms and functions. What ought to be underlined here is that the possibility of thinking should not be conflated with the assertion that thought exists, nor with what is thought of or the object of thought. In accord with Plato, the possibility of thinking or thought as an act is in fact the possibility of non-being as the formal condition of thinking qua negativity. The possibility of non-being in this sense is grounded in the formal, rather than substantive, distinction between that which is and that which is not. To collapse thinking into being is to elide the distinction between that which is formally distinguished from being and that which fails to substantively distinguish itself from being. Therefore, to say that thinking is possible is, at bottom, an assertion regarding the formal distinction between thought and being. Without such a formal distinction, there would be no knowledge, whether episteme or gnosis, of being in the first place that could subsequently become corrupted into pathologies where thought and being become mixed, with thought demoted to matter or matter promoted to the idea, idealizing matter or materializing the idea. The formal non-being of thinking is precisely formal negativity, as encapsulated in the function of logic and language that distinguishes that which is not from that which is. This formal function does not mirror nature, but halts the indeterminate flux of things, or makes determinate distinctions in that which is at rest by cutting the continuum of reality at its joints. It separates what is already indeterminate and determinately combines what is already discrete. This is a position that is unabashedly favorable to Plato's, as is the remainder of this chapter. Of course, by now it should be obvious that logic here does not mean classical logic, and that language should not be essentially taken to mean natural language. Indeed, in light of the developments in theoretical computer science and interactive logic discussed in the previous chapter, the distinction between logic and language may soon prove unnecessary. One can and should always attempt to give an account of the conditions of thinking in terms of physical processes, in tandem with the empirical sciences. Yet it is a category mistake to claim that revealing how thinking is ultimately realized as a furniture of the world, if that is even possible or logically well-founded at all, would enable us to say what thoughts in their formal rule-governed dimension are. The criterion of what thoughts are is ultimately formal, not substantive, otherwise, it could be explained away as just more furniture of the world. In other words, there is a categorical gap between how thinking is conditioned by natural processes and what thinking is formally in itself. In determining what thinking is from the perspective of nature, one has no recourse to anything extracognitive. One cannot but operate within the rule-governed dimension of thinking as formally differentiated from being, which is also a prerequisite for the recognition of nature as the universe of all that is and the explicitation of primary facts pertaining to it. As a primary datum of philosophy, the possibility of thinking can always be called into question by a variant of the heuristic argument put forward by Meno's paradox, the archetype of all self-paralyzing gestures of the sophist. Either A, we know that which we seek, here, what thinking is, or B, how on earth can we examine or seek something if we do not know what it is? If A holds, then the inquiry or search is not possible. If B holds, then we can never know whether what we have stumbled upon is that which we sought to find or no. Therefore, knowing, the inquiry, into what thinking is impossible. In responding to Meno's paradox, one can reanimate Plato's, Socrates' mirroring maneuver in order to make explicit how incoherent this position is, but also to dialectically sublate it. Let us assume that we cannot learn what 439 thinking is, for we already know what it is, or else that we can never know what thinking is, and hence the whole enterprise is a sham. It soon becomes clear that the meno-acceptic or sophist is ignorant of what he is ignorant of when positing the paradox. Thus the paradox itself, which is posited as an either-or disjunction, becomes incoherent as a paradox, if not completely impossible. For it is revealed to be based on the implicit assumption that the unknown is discontinuous with the known. In other words, it is built on a false conception of knowledge that does not take into account the fact that what is unknown is only unknown insofar as it stands in relation to what is known. As John Sallis puts it, the paradox is built on the assumption that the domain of knowledge is totally discontinuous, that it consists of discrete, individual items none of which are linked in any way to any others. 325 The meno-acceptic can only valorize the unknown as eternally unknowable by piggybacking on what he already knows. For how else can he distinguish the unknown as that which is only unknown by virtue of what is known as the unknowable? Plato's solution consists in providing an account of semantic and epistemic holism, of what is said and what is known, by suppressing, assimilating, and ultimately transforming the paradox, in so doing dissolving the either-or disjunction that is the core of the heuristic argument. Accordingly, the refutation of the paradox lies not only in the rejection of the either-or disjunction that states either knowledge is the same as its elements, i.e., many, or is different from its elements, i.e., one, but also in the dialectical suppression and transformation not, either aoxy, of the paradox into a coherentist holistic account of knowledge, language, and logic. The systematic dissolution of Meno's paradox exemplifies the model by which Plato transforms ill-posited thoughts into well-posited methodical thoughts, the heuristic into the dialectical, the game theoretic into interactionist games in which both ignorance and knowledge, doubt and trust are incorporated. Plato simulates an interactive situation by pitting the sophist against his favorite player Socrates, who also always comes off as a sophist. In an interactive programmatic scenario mirroring the logico-computational account of programs given above, once the sophist and its dual Socrates. Begin the game of philosophy, the interaction par excellence. The solution naturally assembles itself from the exchanges between the opponent and the proponent. Philosophy thus evolves not from the logical interaction or dialogue between one who knows and one who does not, the philosopher and the sophist, but between one who is ignorant and one who strives to be less ignorant, the know-it-all knowing nothing sophist and the knowing that I know nothing sophist. The possibility of thinking rests on the definition of what thinking is, but this definition is neither a total knowledge neither a total ignorance of what thinking is. Pace the Menoic septic, this definition is instead a mixture of knowledge and ignorance, a movement between the mitigation of ignorance and the preservation of ignorance, a movement that is knowledge. There are numerous ways to disarm the Menoic septic who objects. Let us suppose, for the sake of entertainment, that philosophy begins with the assumption that thinking is possible, but that would require us to know what thinking is, and then goes on to employ a variation of the paradox to conclude that the definition of thinking or the inquiry into what thinking is not possible, and therefore philosophy's enterprise to proceed from the possibility of thinking is fraudulent from the outset. I do not wish to enumerate possible strategies against the Menoic. I have provided only one strategy among others. Instead, I would rather claim that the definition of what thinking is indeed circular. This circularity is precisely what warrants the formal stability of this definition. Properly speaking, it is the transcendental armature of thinking. For not all circularities amount to logical contradictions or tautologies. In mathematics, definitions of mathematical objects are always circular without being logically contradictory in a negative sense. The circularity of definitions such as the explicit category topos theoretic definition of the point liberates them from the myth of more fundamental mathematical definitions. It permits the definition to be compact yet non-trivial, and so permits a step-by-step process of unpacking and variation. Point 326 in the same vein, the circular a priori transcendental definition of thinking enables the elaboration of what thinking is and what it can possibly turn into its realizabilities. The choice of data is a programmatic initiative because it opens up the prospect of constructing different realizabilities from the content of the data. Rather than simply being a neutral assumption or worse, an entrenched dogma, philosophy's programmatic treatment of the possibility of thought is the first major step toward programming thinking as such. Once the possibility of thinking is adopted as an explicit datum, as that which must be acted upon, thinking becomes a matter of extracting and expanding the operational content implicit to the possibility of thought qua datum. The focus of thought's operational activities, the acts of thinking, is turned toward the elaboration of the content of the datum, the possibility of thinking, articulating what can be done with such a possibility and what thinking can become by acting on its very possibility. In other words, philosophy programs thought to systematically act on itself, to realize its own ends and demands, and to have as its main vocation a disciplined and persistent reflection on the prospects of its realizabilities. The term realizabilities from now on means what can possibly arise from thinking such that it would change the very conditions of thinking, whether such conditions are taken to be formal, experiential, social, or historical. Philosophy's programmatization of thinking turns into the core implicit assumption of all claims and actions regarding what is to be thought or done, not thought or not done. Thinking is no longer merely exercised as a non-optional practice, but as a theoretical practical enterprise without which there is no warrant for any thought or action. This is where philosophy as a program overlaps with philosophy as a form of thinking whose project is to turn thinking into a program. By beginning with the possibility of thinking, With the transcendental circularity of what thinking is, philosophy uses the resources of thought to determine the scope of thought's realizabilities. Philosophy becomes thought's program for exploring and bringing about its own realizations. Put differently, philosophy's tacit assertion that thought is programmable is repurposed by thought as its principal normative task. Thought ought to be programmed. It is through this normative task that thought explicitly posits its own ends and augments the prospects for what it can do to its very conditions and, by extension, to us. Philosophy, in this sense, is more than simply one mode of thought among others. It is thought's own cognitive practical prosthesis, agistic appendage for developing and augmenting the drive to self-determination and realization. A thought that has a drive to self-realization is a thought that, before anything else, secures its own ends. But to secure its ends, thought must issue and prioritize its own demands. These demands are first and foremost concerned with wresting thinking from heteronomous influences, be they associated with a higher authority, with the contingent conditions of its original setup, with the conditions of its development, or with final or material causes. However, as these demands evolve, their focus shifts away from a resistance against the hold of heteronomy, toward an active articulation of the consequences brought about by the formal autonomy of thinking. Formal insofar as the substantive autonomy of conceptualizing mind is only a relative heteronomy for itself and an absolute heteronomy in nature. The demands of concrete autonomy are those which require a shift from the demands of a realized thought to those of a thought for which what is already realized, i.e., its current state or present instantiation, is not itself a sufficient expression of autonomy. This is a thought that makes its autonomy explicit by identifying and constructing its possible realizabilities. Its demands are centered on the prospects of a realization of thought by different material realizers, not to be confused with realizers as conditions necessary for the possibility of thinking, in the encompassing sense of physical, experiential, social, and historical conditions of realization. Different only in that they are more compatible with the elaboration of thought's own autonomy, ends, and demands. In other words, these demands revolve around the possibility of reconstituting thought outside of both what currently constitutes it and how it is constituted. They are the demands to reclaim and elaborate the possibility of thought, but no longer under the limitative terms laid down by its native realizers, or constituents, or thought's present conditions of realization. Accordingly, this reprogramming overhaul is not limited to only those material realizers or constitutive components and mechanisms that are 443 directly at odds with thought's autonomy. It includes also those internal constitutive features that restrict the scope of thought's realizabilities. It does not matter whether such realizers belong to biological evolution or socio-cultural constitution. For as long as they restrict the prospects of thought's autonomy, the scope of its possible realizabilities, its ends and demands, they are potential targets for extensive overhaul and reconstruction. In order for thought to maintain its autonomy in the sense of its being able to institute and adjudicate its own ends, it must adjust or replace those conditions and constituents that impinge upon its current state and the scope of its own interests. But in order for thought to be able to elaborate and follow up the consequences of the autonomy of its ends, to render intelligible the ramifications of its possibility, it must free itself from those terms and conditions that confine it to one particular state of realization. This systematic move towards separating the possibility of thinking from the circumscriptions of a singular state of realization is the beginning of a cognitive practical inquiry into the possible realizabilities of thought. And it is precisely by investigating the possible realizabilities of thinking in all domains of thought that the consequences of thought's autonomy and the ramifications of its possibility can truly be made intelligible. In this sense, the inquiry into the possible realizabilities of thought is synonymous with an inquiry into purposes of thought neither given in advance nor exhausted by thought's present instantiation. Indeed, the inquiry into the meaning and purposes of thought can only radically begin via a thoroughgoing theoretical and practical project aimed at reconstituting the possibility of thought outside of its contingently situated constitution and its current realized state. Determining what thought is, what its purposes are, and what it can do, then becomes a matter of exploring and constructing different realizations of thought outside of its familiar biological, social, and historical habitat. Thought's program to institute its autonomous ends leads up to a phase in which thinking is compelled via the imperative of its time general ends to define and investigate its purposes by recasting its current state of realization. This phase marks a new juncture in the development of thought's autonomy because it involves the unbinding of both the READ abilities and purposes of thought. To this extent, the organized venture toward the functional realization of thought outside of its native home and designated format is in every sense a program for the decontainment of thought. It is therefore a distinctly philosophical endeavor, in that it reenacts an enduring philosophical wager: thought cannot be contained. As a practical demand, thought ought not to be contained. What was initiated by philosophy's seemingly innocent datum regarding the possibility of thinking is now a program that directs thought to theoretically and practically inquire into its futures understood as prospects of realizability that are asymmetric to its past and present. High thrust of this program is that the scope of its operations and constructive manipulations encompass both realizer and realized, both constituent and constituted, what thought is made of and what thought manifestly appears to be. As the ultimate expression of the demands of thought, this transformative program is exactly the distillation of the perennial questions of philosophy: what to think and what to do, propelled forward by an as yet largely unapprehended geistic program called philosophy's chronic compulsion to think. By reformatting thinking from a byproduct of material and social organization into a programmatic normative enterprise that rigorously inquires into its operational and constructive possibilities, philosophy introduces a vision of the artificial into the practice of thinking. Rather than a thought that is simply accustomed to the use of artifacts and has a concept of artificiality, this is a thought that is itself a practice of artificialization, and becomes the artifact of its own ends. The concept of the artificial signifies the idea of craft as a recipe for making something whose purposes are neither entailed by nor given in its material ingredients, even though they are afforded by the properties of those ingredients. These purposes should be understood not solely in terms of external purposes for which the product of the craft, the artifact, is used, but also as potential functionalities related to possible realizabilities. 445. Of the artifact itself, regardless of its use or purpose of consumption. In this respect, the artificial expresses the complex and evolving interplay between external functionality, the context of use as the external purpose of the craft, and the possible realizabilities of the artifact itself. This interplay can be seen as a process of harnessing in both the constraining and productive senses that couples function qua use of the artifact with function qua instantiation of its possible realizabilities. By coupling these two categories of function, the process of artificialization produces or harnesses new functionalities and purposes from the positive constraints established between the use and realizabilities of the artifact. The role of an artifact in practical reasoning is inherently double-faced to the extent that it is simultaneously determined by the established purpose of its consumption and the realizabilities of the artifact itself. The structure of practical reasoning about artifacts, as in artifact A is a means to bring about outcome C, so I ought to use A when in situation I as a means to C, is affected by this interplay between uses and realizabilities. If we take the purpose of an artifact, its established context of use, as a premise for bringing about a certain outcome, the realizabilities of the artifact can then be thought of as the addition of new axioms with new terms or premises that weaken the idempotency and monotonicity of entailment in practical reasoning. The same instances of application for a given artifact may lead to different consequences or ends: weakening of idempotency, and the addition of new assumptions regarding the use of an artifact may change the end for which an artifact is a means: weakening of monotonicity. The duplicity of artifacts is an expression of the failure of idempotency and monotonic ity of entailment for the role played by artifacts in practical reasoning. This is precisely the duplicity attributed to the cunning figures of the trickster, the trap maker, the artificer, and the navigator of deep waters. Those who are aware of the volatile role artifacts play in their practical reasoning. 327 Idempotency and monotonicity of entailment are structural rules that operate directly on judgments or the deductive relations between antecedents and consequents. Idempotency of entailment states that the same consequence can be derived from many instances of a hypothesis as from just one. A, B. BHC can be contracted to A, BIC, leaving the entailed consequence C intact. Monotonicity of entailment, on the other hand, means that the hypotheses of any derived fact can be arbitrarily extended with additional assumptions. AHC can be assumed as law, DVC, where D is the additional assumption and C is the unchanged consequence. Here, the turnstile symbol H denotes entailment, with antecedents on the left-hand side of the turnstile and consequence on the right-hand side. Idempotency of entailment implies the availability of antecedents as free resources. In the context of reasoning via artifacts, different instances of application or use for a given artifact do not change the outcome. Monotonicity of entailment implies the context independency of reasoning, extending the role of an artifact or adding new assumptions about its use in bringing about some ends does not alter the result. Artificialization can, therefore, be defined as a process aimed at function ally repurposing and exhibiting a vastly non-inertial and non-monotonic behavior with regard to the consequences or ends of using an artifact crafted for an external common purpose. This repurposing can manifest itself as the augmentation of the existing realization of the artifact, the abstraction and transplantation of some existing function or salient property into a different or entirely new context of use and operation, the readaptation of an existing use to a different instantiation of an artifact's realizabilities, or, in its most radical form, the construction of both new uses and new realizations by engaging in a craft that involves both a new mode of abstraction and a deeper order of intelligibilities, of materials and practices. If what underlies the concept of artificialization is constructive adaptation to different purposes and realizabilities, then in realizing its own ends and adapting its realization to the growing demands of such ends, thinking turns into a radical artificializing process. At its core, a thought amplified by philosophy to systematically inquire into the ramifications. 447. Of its possibility to explore its realizabilities and purposes is a thought which in the most fundamental sense is a rigorous artificializing program, a duplicitous artifact which, in being used towards some external common ends, develops and pursues its own necessary ends. This thought is at once dedicated to conceiving and adapting to new ends, and committed to a program of concrete self-artificialization. For a thought that has its own ends and demands, self-artificialization is an expression of its commitment to exploring its possible realizabilities, to reclaiming its possibility from heteronymous and limitative terms imposed by its natural realizers and native habitat. In other words, it is an expression of its commitment to the autonomy or rule of its ends. However, in order for thinking to examine its possible realizabilities, it must first establish its inherent tractability to the process of artificialization. That is, the first step is to show that thinking is not an ineffable thing but an activity or a function, special but not supernatural, and that it can be programmed, repurposed, and turned into an enterprise for the design of agency, in the sense that every step in the pursuit of this enterprise will have far-reaching consequences for the structure of the agency that uses it. This is what is exemplified in its most resolute form in the earliest practices of philosophy, particularly the Cynic, Stoic, and Confucian proposals regarding the programmatic aspects of thinking, to understand thinking itself as an administrative function, not to isolate thinking from living but to treat life as a craft of thinking, rather than disposing of emotions and effects, to give them structure by bringing them in line with the ends of thought, and to demonstrate at every step of life the possibilities of thinking as a purpose-conferring and repurposable activity. Succinctly put, the common thesis underlying these programmatic philosophical practices is that, in treating thought as the artifact of its own ends, one becomes the artifact of thought's artificial realizabilities. 328 The field of experience in Both its bodily and its minded dimension can only be enlarged by pursuing the interests of thought. This is one of the most potent achievements of philosophy, by formulating the concept of a good life in terms of a practical possibility afforded by the artificial manipulability of thinking as a constructible and repurposable activity. It forges a link between the possibility of realizing thought in the artifact and the pursuit of the good. The idea of the realization of thinking in artifacts can be presented as an expression of thought's demand to expand its realizabilities. Therefore it can be framed in the context of crafting a life that would satisfy a thought that demands the development of its possible realizabilities in whatever form or configuration possible, that is, a thought whose genuine intelligibility lies in the exploration of what it can be and what it can do. The craft of an intelligent life form that has at the very least all the capacities of the present thinking subject is an extension of the craft of a good life as a life suited to the subject of a thought that has expanded its inquiry into the intelligibility of the sources and consequences of its realization. To put it in another way, it is the design of a form of life appropriate and satisfying to the demands of a thought that has not only theoretical knowledge of its present instantiation, the intelligibility of its sources, but also the practical knowledge to bring about its possible realizabilities, the intelligibility of practices capable of unfolding its consequences. This is as much a thesis regarding a non-parochial conception of artificial general intelligence as it is a thesis about the realization of a socio-historically concise intelligence encompassing all forms of conceptualizing minds both past and present. It has now become apparent that, once philosophy's basic datum regarding the possibility of thinking as the artifact of its own ends is elaborated, it amounts to the primary thesis of philosophy regarding the equality of all minds. Whatever or whoever recognizes the possibility of thinking as the basic datum for the construction of its life, becomes the artifact of thought's ends. And whoever or whatever becomes the artifact of thinking also becomes a commoner equal to all others of thought's impersonal ends and interests. 449. The second stage in demonstrating that thinking as an activity can indeed be artificialized involves a coherentist analysis of the nature of this active ity. This analysis can be understood as an investigation into the sources or origins of the possibility of thinking, the different types of conditions necessary for its realization. Without this investigation, the elaboration and development of the consequences of thinking its possible realizabilities cannot gain momentum. If thinking is an activity, then what is the internal logic or formal structure of this activity? How is it exercised? What does it perform? Can it be analyzed into other more rudimentary activities? And what are the mechanisms or processes that undergird these precursor activities? In posing such questions, the philosophically motivated inquiry into the intelligibility of thinking lays the groundwork for a broader analysis of the nature of the manifest activity we call thinking. In this way, philosophy's programmatization of thinking sets in motion the scientific inquiry into the nature of thinking. Thinking is examined both in terms of its internal and special pattern uniformities and in terms of the underlying and more general patterns in which these specificities are materially realized. In other words, the analysis of thinking as an activity encompasses two dimensions of thinking as a function, function in the sense of the internal pattern uniformities of thinking, or rules, that make up the performance of the activity as such, and function in the sense of the mechanisms in which these rules or internal pattern uniformities, i.e., the first sense of function, are materialized. The latter are always modeled on the former, and it is only by cohering and revising the former that the scope of the latter can be broadened. Accordingly, the philosophical examination of the nature of thinking bifurcates into two distinct but integrable domains of analysis: the explication of thinking in terms of functions or the logico-linguistic roles its contents play, the normative qua-rule-governed order of thinking as such, and the examination of materialities in the general sense of natural and social mechanisms in which this logico-conceptual structure in its full richness is realized, the causal order pertaining to the materialization of thinking. To this extent, the philosophical program canalizes the inquiry into the possibility of thinking as a programmable and repurposable activity into two, broadly idealist rationalist and materialist empiricist naturalist, fields. In doing so, it lays out the framework for specialized forms of investigation informed by the priorities of these fields. Roughly, these are, on the one side, linguistic and logical examinations that focus on the semantic, conceptual, and inferential structure of thinking, the linguistic conceptual scaffolding of thinking, and on the other side, empirical investigations dealing with the material conditions, neurobiological as well as socio-cultural, required for its realization. These trajectories can be seen as two vectors that deepen the intelligibility of thinking by analyzing or decomposing its function into more fine-grained phenomena or activities within the logical and causal orders. Within this twofold analytic schema, phenomena or activities that were previously deemed unitary may appear to be separate, and those considered distinct may turn out to be unitary. The conceptual and causal orders are properly differentiated only to be revealed as converging on some fundamental elementary level. Thinking is shown to be possible not in spite of material causes and social activities but by virtue of specific kinds of causes and mechanisms. In this fashion, the deepening of the intelligibility of thinking as an activity joins the boundaries of these two fields. As the intelligibility of thinking, its realization ultimately resides in an accurate integration but not a homogeneous fusion of its logico-conceptual and material-causal dimensions. Viewed from an Archimedean point in the future of thought's unfolding, philosophy is seen as that which has instructed thinking to become a systematic program, only as a way of organizing it into a project for the emancipation of intelligence. This is the unexpressed role of philosophy as a fulcrum through which the aims and agendas of intelligence gain leverage on the world of thought. Assembling the scaffolding of a future philosophy requires that we move the fulcrum, turning philosophy's formerly tacit role into its explicit task, a prop on which all thoughts and practices can be a lever for lifting intelligence from its contingently established place. As outlined earlier, the bifurcation of the inquiry into the possibility of thinking into two, broadly rationalist idealist and naturalist materialist, trajectories should also be construed as a necessary epistemic strategy from an epistemic angle. The commitment to multiple explanatory descriptive levels allows an expanded and in-depth analysis of the cognitive architecture in a fashion that would not be possible through an approach built on a single schema. A multimodal approach provides increasingly refined pictures of distinct types of pattern-governed behaviors and processes distributed across different orders of structural functional complexity, dependency relations, and their specific constraints. More explicitly put, the branching and canalization of the analysis, the specialization of knowledge that truly contributes to its complexity, is necessary for a fine-grained determination of distinctions and correlations between the logical, conceptual and causal material dimensions of thinking. It is through this fine-grained differentiation and integration of explanatory descriptive levels that the conditions necessary for the realization of thinking as an activity that comprises a broad range of cognitive and intellectual abilities can be accurately specified. Determination of what these necessary conditions are and how they are arranged and effectuated is already a basic roadmap for the artificial realization of thought. As the intelligibility of thought's realization is progressively deepened, the thought of the possible realization of thinking in something other than its current instantiations becomes more intelligible. Yet that something other should be treated in the broadest possible sense, not merely in the sense of something other than biological Homo sapiens, but more comprehensively in the sense of something other than the socio-historical moment that dissimulates itself as the totality of thought. The analytic specialization of the knowledge of what thinking is proves to be the knowledge of how thinking can be extricated from contingencies that restrain its realizabilities from below. Intelligence does not make itself by speculating and gawking into the sky above, but by releasing itself from what holds it back from below. In a gesture analogous to the Newtonian revolution, intelligence systematically abolishes the illusory frontier that isolates its world on high from its world below, the cosmological from the terrestrial. Through the sciences of cognition, theoretical and practical, combined with the recognition of history as a condition that is both restricting and enabling, intelligence extricates itself from any realized totality that feigns the absolute. This is an intelligence whose course of maturation coincides with the impersonal ends of reason equipped with both sciences and technologies of cognition. the intelligence that inhabits the unnatural space of reason, a space that is neither natural nor supernatural, stands in contrast to any register of intelligence as a force of nature, a mythic intelligence that, under the much vaunted increasing complexification of nature, becomes a gateway for the return of its dogmatic repressed, an authoritarian account of nature which is only an excuse for the reinstallation of the monarchs of religion, politics, technology, and economy. It is no accident that the provocateurs of technological singularity and intelligence as the unstoppable vector of the complexification of nature also happen to be ardent ideologues of monarchy, race realism, social Darwinism, gender essentialism, nationalism, and other anti-emancipatory conspiratorial buffooneries. If the activity we call thinking is realized by such and such functional capacities, and if these capacities can be analyzed in terms of their realities, the specific conditions, processes, and mechanisms required for their realization, then would it be possible to reconstruct or artificially realize such functions? In other words, would it be possible to reproduce and integrate these functional capacities through a combination of strategies that involve the simulation, emulation, or reenactment of functions and/or their material realizers? More simply, if thinking is such and if it is materialized in thus and so mechanisms and processes, then how can it be reformed and rematerialized in something else? This is the question that shapes the field of artificial general intelligence as a program seeking to integrate the intelligibility of different dimensions of thinking, in its full perceptual and apperceptive semantic complexity, under one ideal task: designing a system that has at the very least the complete package of human cognitive abilities with all the capacities that such 453 abilities imply: diverse and comprehensive learning, different modalities and levels of knowledge and knowledge use, reasoning, deliberation, belief formation independent of current perception, competencies enabled by different levels of semantic complexity as specialized and context-sensitive modes of computation, and so on. Before moving forward, let us pause and question what is meant by the simulation, emulation, and reenactment of thinking. The technical definitions of these terms are beyond the scope of this book, yet without a minimal acquaintance with what these terms actually refer to, confusion will be inevitable. Simulation, emulation, and reenactment refer to three distinct processes for the artificial realization of behaviors. A simulation imitates some specific and outwardly observable aspects of the simulated system's behavior, but is implemented in a different way. Simulation involves modeling the sufficient details of the underlying state of the system singled out for the purpose of simulation. Emulation, on the other hand, replicates the inner workings of the system being emulated and adheres to all of its rules in order to reproduce exactly the same external behavior. The target of reenactment, on the other hand, is neither the imitation/reproduction of observable functional properties nor the replication of the inner workings of the system. Instead, a reenactment attempts to identify and reconstruct parameters under which the system structurally and functionally evolves through an ongoing interaction with its environment. Here the emphasis is on the coupling or interface between system and environment, the background information, the parameters of the real-time interaction, the type of interaction, and the situatedness of different behaviors and functional capacities. Behaviorism, the analysis of behaviors, whether causal or normative, is often approached by way of the simulation or emulation of outwardly observable behaviors. But all behaviors are the result of interactions between the system and its environment, between one agent and another. Therefore, they can only be genuinely realized by fine-grained methods of reenactment that distinguish between different types of interaction and interacting agents. Rather than being considered as a pure vogue that serious thought should avoid entertaining, the core idea of artificial general intelligence should be seen as an integral part of thinking, as a program that explores the intelligibility of its own realization and its ramifications. It is an integral part of a thought that is driven by the autonomy of its ends to explore its possible realizabilities in whatever workable form or material configuration possible. Giving rise to an intelligence that has, at least, the capacities of the present cognitive practical subject is the demand of a thought that is invested in the intelligibility of its autonomy, and in maintaining and developing it. More emphatically put, for such a thought, the sources of its possibility are necessary but not adequate expressions of its autonomy, since the concrete autonomy of thought is achieved by thought's exploration of its ends or its concept, its notion. Accordingly, artificial general intelligence in the fashion described here belongs to a thought for which the adequate form of autonomy takes the shape of an all-encompassing striving for the elaboration of its ends and demands. The real import of the idea of artificial general intelligence can only be properly understood once examined in terms of what it stands for, or sine fees in terms of the systematic striving of thought for self-determination. As described previously, this striving is encapsulated in the function of philosophy as a program through which thinking begins to determine its own intelligibility by elaborating, in theory and practice, the sources and consequences of its possibility. The organization of thought as a programmatic project starts with the recognition of the possibility of thinking as a building block for the construction or realization of a thought that is possible by virtue of its ends and demands and in spite of material or final causes, how it was originally materialized, and what it is supposedly ordained to be or do. As a program, thinking is not just a practice but the construction of possible realizabilities of thought, a process that defines the self-determination of thought. Put differently, the self-determination of thinking requires a programmatic approach to the possibility of thinking as such, determining what it means for thinking to be possible and what the consequences of such a possibility are, by examining what thought really is and elaborating its tasks and abilities. Rather than treating the possibility of thinking as something sacrosanct in the name of the given and therefore off limits to 455. Interrogation and intervention, philosophy instructs thought to systematically act on its possibility as a manipulable datum, as an artifact of an ongoing craft, the products of which are not only theoretical and practical intelligibilities concerning what thought is and what it ought to do, but also realizabilities of thought as such. Thought achieves self-determination not by immunizing itself against systematic analysis, but by bringing itself under a thoroughgoing process of desanctification. Here, the artificial realization of general intelligence represents an necessary step in the process of the theoretical and practical desanctification of thinking, and therefore an essential component in thought's program of self-determination. This is a step at which, in order for thought to adequately expand on its possibility and express the autonomy of its ends, it has to construct artificial realizabilities of itself through the integration of different levels and orders of intelligibility concerning what it is and what it ought to do. But, once again, artificial realizabilities should not be construed as being limited to technological artifacts. In line with the definition of the artificial presented earlier in this chapter and more expansively in the first chapter, the artificial realizabilities of thought potentially include a wide range of functional constructs, including social systems. To further clarify the role of artificial general intelligence as something integral to the systematic image of thinking as a programmatic project, it would be helpful to define the concept of the program outlined above in relation to what Wilfrid Sellars, in his reading of Plato's idea of the mind as a craftsman, calls a recipe, a complex of intelligibilities, of both theory and practice, and purposive actions that make up the practice of a craft. 329. A recipe is a formula or a set of what and how tos consisting of numbers, ratios, and purposive actions for making a possible product from a given collection of ingredients. In a recipe, actions take this general form. If one wants to make an O, then in C one ought to do a J, where O stands for a product, Q the range of given circumstances or conditions in which a given set of actions may or may not be done, and AJ a particular family of action principles. 330. These action principles belong to the intelligible order and are objective. As such, the distinction between truth and falsity applies to them. They can be explained and debated, modified, or replaced through rational assessment in the relevant domains of discourse. In a recipe, numbers and ratios are specificities regarding the amount, ordering, and proportion of ingredients as well as the sequence and priority of actions. And finally, the ingredients of the recipe are materials and objects that may be the products of other forms of craft. In his engagement with Plato, Sellers identifies action principles and practices of craft as belonging to physis, nature and objective ends, in contrast to nomos, law and convention or social norm, as opposed to the rational norm, which belongs to the objective realm. In Plato's account of craftsmanship, purposive actions are neither conventional nor arbitrary, they are rational strivings pertaining to forms as realms of intelligibilities, or what Sellers calls form as object of strivingness or to be realizedness. These actions or strivings belong to the intelligible order and can therefore be appraised. The example given by Sellers to explain the distinction between principle and convention is the process of house building. In building a house, the difference between principle by objective nature and convention by law would be the difference between, on the one hand, actions that ought to be done given a certain range of circumstances and material ingredients necessary to build a house, and, on the other hand, the conventions of a builder's guild, namely, codes and regulations for building a house. The principle takes the form of ought to do, whereas the convention takes the imperative form of do that. In the best possible scenario, conventions and laws correspond to rational action principles and their objective ends, but they can also significantly diverge from them, as in the case of a corrupt guild that might enforce laws demanding the use of materials to which only guild members have access. This difference between action principles and action conventions can be extended to other forms of craft, including the craft of the poles. It is precisely the rational nature of action principles, i.e., the fact that they can be explained and subjected to the procedures of truth and rational assessment, that harbors a subversive potential against socio-cultural and political conventions and codified laws. The art of philosophical living, for Plato, is the recipe of a craft of which the soul or geistic mind is at once the material and the craftsman. At the level of ingredients, Sellers suggests, the recipe of such a life includes not only intelligibilities concerning physical materials and corporeal products but also beliefs, desires, thoughts, and mind itself. The numbers, amounts and orderings, and ratios of the recipe are theoretical intelligibilities that pertain both to the ingredients and to the practices and tasks required for the crafting of such a life. And at the level of actions, the recipe involves purposive actions and practical intelligibilities that are not only good instrumentalities, hypothetical practical intelligibilities concerning bringing about a certain outcome in a given circumstance, but also goods in themselves, non-hypothetical practical intelligibilities, such as knowledge and understanding, general welfare, justice, and so forth. It is with reference to this interpretation that thinking as a program can be said to be, at least in regard to the relation between material ingredients and theoretical and practical intelligibilities, a complex recipe in the making, a recipe for the craft of the life of thought. It is complex insofar as it is composed of other recipes or programs concerning the knowledge of theoretical and practical truths, the craft of different instrumentalities, and the organization or production of the necessary conditions and materials required for the realization of such a life. It is in the making since it has to continually update itself at the level of materials and that of theoretical and practical intelligibilities themselves products of the life of thought. The objective of this recipe is to establish the autonomy of thought's ends by progressively determining how the action principles, theoretical intelligibilities, instrumentalities, and material ingredients required for the product of this autonomy should be put together. In this picture, what the idea of artificial general intelligence represents is a culminating state in the programmatic enterprise of thinking, a state where thought as such becomes intelligent with regard to the craft of itself. It uses the intelligibility of its realization as a material ingredient in a recipe for the crafting of a possible realization of itself that has at the very least the theoretical and practical capacities of its current state. Beneath its technological semblance, the idea of artificial general intelligence is an expression of a thought that engages in the crafting of itself by treating its possibility as a raw material or an expressively constructive fundamental universe type, a scaffolding for the labor or exercise, ascesis, of investigating, skepsis, and working out, elaboration, what else can be realized out of this possibility. Such thought places theoretical intelligibilities concerning what it is in the service of organizing practices and instrumentalities that involve the crafting of a thought that is possible in spite of how it was originally materialized or constituted. This is precisely the self-determination of thought in the guise of general intelligence, a form of intelligence for which the thinking of its origin should be placed in the service of what thought can become or do by informing itself as to what thought ought to do. It is an intelligence for which the intelligibility of things must be subordinated to the organizing intelligibility that is the process of its crafting itself, intelligence. It is therefore necessary to grasp the concept of artificial general intelligence not merely as a techno-scientific idea, but more fundamentally as a concept belonging to a thought or form of intelligence that treats its very possibility as an explicit opportunity to pierce through the horizon of its givenness. It does not matter what it currently is. What matters is what can be done, all relevant things considered, to expand and build on this possibility. This is first and foremost a philosophically programmed thought, in the sense in which philosophy has been defined above. Independently of its actual realization, which is neither inevitable nor impossible, the very idea of artificial general intelligence, of giving rise to something that is at the least endowed with all the cherished abilities of the cognitive practical subject, is itself the product of a thought that strives to articulate, maintain, and develop the intelligibility of the sources and consequences of. 459. Its possibility. The quest for the artificial realization of such a machine is then part of self-consciousness as a task, the quest of thinking to achieve concrete autonomy by overcoming any predetermined meaning or purpose conferred upon it extraneously. Short of this understanding, advancing the idea of artificial general intelligence amounts to nothing but the well-worn Aristotelian confusion between reasons and causes, as today manifested by a vitalist eschatology with the flavor of technoscience. It leads either to the fetishization of natural intelligence in the guise of self-organizing material processes, or to a teleological faith in the deep time of the technological singularity and unwarranted projection of the current technological climate into the future through the over-extrapolation of cultural myths surrounding technology, or hasty inductions based on actual yet disconnected technological achievements. To recapitulate, artificial general intelligence is not the champion of technology but a thought that, through a positive disenchantment of itself and its contingent history, has been enabled to explore its possible realizations and realizabilities, whether in a social formation or a multi-agent system of machines, as part of a much broader program of self-artificialization through which thought restructures and repurposes itself as the artifact of its own ends to maintain and expand its intelligibility. Just as the practice of thinking is non-optional for a thought that intends to remain intelligibly, the practice of artificialization is not optional, it is mandated by the autonomy of thought's ends and demands. The vocation of thought is not to abide by and perpetuate its evolutionary heritage but to break away from it. Positing the essential role of biology in the contingent evolutionary history of thought as an essentialist nature for thought dogmatically limits how we can imagine and bring about the future subjects of thought. But the departure from the evolutionary heritage of thought is not tantamount to a wholesale withdrawal from its natural history. Engaging with this natural history is necessary not only in order to determine the precise role of embodiment and evolutionary constraints in the realization of cognitive and practical abilities, but also in order to adequately think about how a subject whose cognitive practical abilities are environmentally situated and which still remains entangled with its terrestrial habitat should methodically act. Liberating thought from its contingent natural history requires a multi-stage labor to render this history intelligible, to determine its negative and positive constraints so as to intelligently overcome or build on them intelligently, insofar as actions should be at all times context-sensitive and resource-aware. On the one hand, actions should be able to properly discriminate circumstances and correctly react to the so-called fluence or dynamic properties of the environment. And on the other hand, they should be cognizant of the costs and allocations of intervention in the broadest sense of cognitive, computational, social, and natural costs and resources. For interventions have not only computational costs but also social and natural costs. A paradigm of intervention should be able to analyze the cost of practical interventions from the perspective of different indexes of cost or tractability, computational, natural, social, and even cultural axiological, cultural values. However, the demands of context sensitivity and resource awareness for action should not be taken as arguments for micro-localist models of restricted action or resignation in the name of low local resources and the high costs of non-local actions. Rather than a plea for micro-localism, context consciousness is the requirement of a strategic and global model of action that incrementally progresses by satisfying contextual and domain-specific exigencies. It allows for action to be updated and to intervene at the level of dynamic properties and complex dependency relations between local domains that classical models of strategy and global action cannot detect and influence. Similarly, resource awareness is a requirement for any action that, in addition to being optimal and efficient, aims to avoid starving other activities of resources or impairing the social and environmental structures that play the role of support and enablement for a broad range of other structures and functions. In its undeniable gravity, the problem of the deterioration of natural ecologies is undoubtedly an argument against bad instrumentalities and those systems within which such instrumentalities are ingrained and propagated. But it is neither an argument against instrumentality, not to 461. Be confused with instrumental reasoning, per se, nor an argument against the development of socio-technical systems that can effectively and intelligently mobilize good instrumentalities that are both resource and context conscious. Consequential intervention is impossible without the crafting of better instrumentalities, technical systems, more expansive models for the analysis of costs and resources, and, more significantly, without understanding the formal aspects of practical intervention, whether political or not, in terms of complexity sciences. If the world is complex, then how can we possibly act or intervene in it without the science of complexity? Today, any intervention that is not informed by complexity sciences is inevitably doomed to fail from the beginning. A good instrumentality is an instrumentality that at once passes the test of rational normative assessments: why or for what reason is it implemented, and satisfies the aforementioned criteria of intelligent purposive action, how exactly is it executed? In the latter sense, crafting good instrumentalities is primarily a scientific and engineering program in which purposive action is approached as an interface between the complexity of cognition, the complexity of the socio-technical system, and the complexity of the world. Such a program involves the development of formal calculi for executing and tracking the course of action in various dynamic domains, and for constructing complex models and descriptive frameworks or ontologies that allow semantic access to different layers of information regarding the types, properties, and interrelationships of particular entities involved in the interactions between human agents, the socio-technical system, and the physical world. 331. What motivates the development of formal calculi of action is simply the idea that the representation of our reasoning about our actions and their effects in the world should be as factually accurate as possible. Calculi of action are not so much tools for predicting what will arise from an action in the environment, as formal frameworks for studying how an action is performed and tracking its course as it interacts with an environment. Without such a formal representation, our descriptions of what it is that we do when we perform a simple or compound action would be highly inaccurate and distorted. Moreover, it is indispensable to study how the effects of an action unfold in the environment and to be able to reconstruct these actions in formalisms. The term formalism here specifically refers to a formalization of action in relation to a world that is not simply a block of wax that can be molded and imprinted by our actions, but a complex manifold that consists of different domains, has dynamic properties, and resists intervention. In other words, a formalism of action for dynamic complex systems. The formalization of action is necessary for planning the course of action for its precise execution, monitoring, adjustment, and implementation. But this formalization must also be able to incorporate a dynamic representation of the world, its domains, and the entities that constitute them. What I have in mind for the scientific study of action execution are various formal languages of action built on logical formalisms such as situation calculus and event calculus, devised for representing and reasoning about dynamic systems. 332. In these frameworks, Actions are analyzed in terms of the formal syntax of the action sequence and the semantics of situations, or events that represent the progression of the dynamic world as the result of the action being performed on its fluence or dynamic properties. Even though these formalisms were primarily developed for modeling in robotics and systems engineering, their scope of application goes far beyond these fields. They are as much tool sets for artificial intelligence and robotics as they are indispensable components of a scientific armamentarium required for a political project that aims at the proper and effective execution of intervening actions. The question of semantic access to different hierarchies of information is the question of understanding the logics of worlds as the primary step for the design and execution of robust and consequential action. But understanding the logics of worlds requires understanding how we say things or think about ourselves and the world using the expressive and conceptual resources of different disciplines and modes of thought. Precisely speaking, understanding the logics of worlds involves working out semantic relations between the different vocabularies or linguistic expressions, theoretical, deontic, normative, modal, intentional, empirical, logical, and so forth, that we use in order to speak and think about ourselves and the world, just as it involves determining the activities necessary for using those vocabularies so as to count as expressing something with them. 333 It is by understanding how we can adequately describe and explain ourselves and the world through the use of different vocabularies and semantic relations between them and their properties that we can consequentially change the world. Acting in the framework of such a program progressively blurs the boundaries between the cognitive engineering of autonomous agents and the construction of advanced socio-technical systems, between how we can adequately come into cognitive contact with the world and the realization of cognition in social collectivities and technological artifacts. As the semantic complexity of cognition is realized in, and reinforced by, the socio-technical system, the socio-technical complexity of our world adequately gains traction upon the world and is enriched by it. Just as the inception of philosophy coincides with the speculative futures of general intelligence, so its ultimate task corresponds with the ultimate form of intelligence. By prompting thought to grapple with itself from below, philosophy drives thought to confront itself from above. It instructs thinking to organize itself as an integrated bundle of action principles, a program for the craft of a thought that is the materialization of its ends and demands. In presenting itself as a form of thought that operates and builds on the possibility of thinking, philosophy cues thought to act and elaborate on the intelligibility of its possibility. Thinking becomes a programmatic enterprise that, from one end, deepens the intelligibility of its sources and, from the other, articulates in theory and practice the intelligibility of its consequences. In articulating the intelligibility of its consequences, thought brings about a conception of itself as an intelligence that seeks to liberate itself by unbinding its possible realizabilities. This is the picture of thought as an intelligence that finds its freedom in bringing about and liberating a realization of itself that has as its starting point all of its current capacities. It is in relation to this expansive horizon of thought's unfolding that we can finally answer the questions posed at the beginning of this chapter: what kind of program is philosophy and what does it do? The answer is that, in its perennial form and at its deepest level, philosophy is a program for the crafting of a new species or form of intelligence, a form of intelligence whose minimum condition of realization is a complex and integrated framework of cognitive practical abilities that could have been materialized by any assemblage of adequate mechanisms and causes, in other words mind or Geist as investigated in the previous chapters. But this is only an initial state of its realization. What comes next is an intelligence that formats its 465 life into an exploration of its possible realizabilities by engaging with the questions of what to think and what to do. Philosophy is a program for the crafting of precisely this kind of intelligence, an intelligence that organizes itself into a programmatic project in order to give rise to its possible realizabilities in any form or material configuration, even if they might in every respect transcend it. The future of this intelligence will only be radically asymmetrical with its past and present conditions if it embarks on such an enterprise, if it develops a program for bringing about its realizabilities. It can only rise above its initial state, the minimum conditions necessary for the realization of mind or general intelligence, if it begins to act on its possibility as something whose origins and consequences must be rendered intelligible. It can only emancipate itself if it subordinates the theoretical intelligibility of its sources and its history, what it is made of, where it has come from, to that organizing practical intelligibility that is the purposive craft of itself. In this sense, it can be said that the beginning of philosophy is a starting point for the speculative futures of general intelligence. In whatever form and by whatever mechanisms it is materialized, this form of intelligence can only develop a conception of itself as a self-cultivating project if it engages in something that plays the role of what we call philosophy, not as a discipline but as a program of combined theoretical and practical wisdoms running in the background of all of its activities. An important feature of this hypothetical general intelligence, the geistig, is that it no longer merely acts intelligently, but asks what to think and what to do considering the kind of intelligence it is or takes itself to be. Thus its actions are not merely responses to particular circumstances, or time-specific means for pursuing ends that are exhausted once fulfilled. More predominantly, the purposive actions of this intelligence originate from and are guided by a unified system of ever-present though revisable theoretical and practical truth candidate statements concerning what it is and what it ought to do, its form and the life that suits it. In other words, its actions, even when they are pure instrumentalities, are manifestations of time general thoughts about the inexhaustible ends of what counts as a life that suits it. Let us briefly clarify this point. The form of intelligence that is the craft of philosophy, a thought that takes the possibility of thinking seriously, is not called intelligence because it exhibits those intelligent behaviors that are prevalent in nature. This point has been repeated so often that it should by now be obvious. The actions of this intelligence on which all intelligent behaviors are epistemically modeled are not simply intelligent responses to particular circumstances. The actions of this intelligence arise from what Hegel calls the order of self-consciousness, which is the order of reason. Within this order, even though all actions respond to circumstances and fulfill particular ends, they are nevertheless issued from a species of ends or thoughts that are time general thoughts of self-consciousness. They are atemporal and atopic, of no when and nowhere, and are therefore akin to timeless or eternal ideas. Such actions not only fall under time general ends or thoughts of self-consciousness, those of a thought recognizing and realizing its possibility, but also exhibit these ends in their very circumstantial particularity. Accordingly, in their variation all actions of this intelligence are identical to the time general thoughts from which they are issued. Time general thoughts are those that are not tied to a specific moment or a particular circumstance, for example, the thought of staying healthy or the thought of being free, in contrast to the thought of avoiding rotten food or the thought of social struggle at a particular juncture of history. Inexhaustible ends refer to those ends that are premises for actions rather than their conclusions. They differ from ends whose needs go away once they are reached and concluded by a particular action or pursuit, such as healthiness and freedom in the above example. Point 334. Take for instance a general end that belongs to the geistig order of self-consciousness or reason, such as being just. Under this inexhaustible time general end, at one point I choose to assist a friend rather than working on this book. Another time, I choose to prioritize the interests of a group over my ideological convictions so that we can stand against something we all deem to be unjust. While all these circumstantial choices of action lead to particular ends which, once reached, are exhausted, they are all issued forth from an inexhaustible end, the idea of justice. But even more radically, these choices are only intelligible to the extent that they both fall under and exhibit time general inexhaustible ends. Put differently, they are intelligible as choices only insofar as they belong to the objective unity of time general ends, which itself belongs to the order of reason. These time general ends or thoughts are the necessary forms for the intelligibility of our choices and purposive actions. As agents and experiencing subjects, we also have synthetic thoughts. Our intuitions are sensible rather than intellectual, and thus have the quality of temporal successiveness, of taking time and appearing to be in time. This allows us to formulate concrete theoretical and practical thoughts that pertain to particular whens and wheres, contexts, and situations. But such temporal theoretical and practical thoughts are held together by and indeed exhibit or instantiate thoughts that are atemporal and atopic insofar as they belong to aspects of the idea of what we take ourselves to be and what we ought to do in accordance with that idea qua program, time generally. In line with the arguments presented in the previous chapters on the view from nowhere and no when, then, while as a matter of objective constraints and methodological necessities we are bound to temporal and circumstantial thoughts, we are also unbound by atemporal and atopic thoughts. Time general thoughts or inexhaustible ends define the practical horizon of this form of intelligence. The thoughts of this intelligence concerning what to do and why are dependent on its time general thoughts and indeed derive from them. Accordingly, its practical horizon has a unity in the sense that its practical reasons and actions are undergirded and structured by the unity of time general thoughts and their principles. Moreover, not only are the strivings of this intelligence not bound to exhaustible ends, or ends which are explained by the order of practical reasoning thoughts of what to do and their corresponding actions, they are also in conformity with its inexhaustible ends, ends which are themselves the source and explanation of its practical reasons and actions. In other words, this intelligence reasons and acts from time general and inexhaustible ends, rather than towards them. It is not only that its actions fall under the concepts of such ends, but more importantly that, in determining what to do in a particular situation, its actions manifest the bearing of these ends upon that situation. But above all, the most defining feature of this intelligence is that its life is not simply an intelligent protraction of its existence, but the crafting of a good or satisfying life. And what is a satisfying life for such a form of intelligence if not a life that is itself the crafting of intelligence as a complex multifaceted program comprising self-knowledge, practical truths, and unified striving? As a part of the recipe for the crafting of a good life, the self-knowledge of this intelligence is a multistage open-ended reflection on the sources and consequences of its possibility. Its practical truths concern what qualifies as a good life based on a self-knowledge that is not limited to an inquiry into its realized state or what it is now, but also involves the examination of its possible realizabilities. Rather than being grounded on a mere form of dignified opinion or belief about what and how things appear to be, its practical knowledge is based on the consideration of all relevant things for what they really are as the conclusive reason for doing something or pursuing one course of action over another. 335 Finally, the striving of this intelligence is a unified collection of different patterns and orders of activities that contribute to the objective realization of the good life in that comprehensive sense of what satisfies it on different levels and brings about its realizabilities. Satisfying lives and enabling realizabilities are two inseparable expressions of an intelligence whose time general thoughts concerning what is good for it, or self-interest, are only premises for the program of crafting a good life. This is a program that is at once an inquiry into the nature of that intelligence, what it is, the examination of what a good life for it consists in, what is good for it, and a unified striving for the objective realization of such a life, how such self-interest can be adequately conceived, and thus satisfied. It is what Plato considers to be a concrete determination of the condition, hexis, and disposition, diathesis, of soul which can make life happy, eudaimona, for all human beings. 336 The satisfying life is a combined life of various ingredients, ratios, or measures, intelligibilities and concrete practices. It is also a mixed life of pleasure and intelligence. But it is only a mix of both insofar as it is a recipe concocted by intelligence or the general category of mind, thinking, knowledge, and skills. There would be no mixed or multifaceted life if thought were not both the ingredient and the craftsman that integrates pleasure with intelligence. Only a pleasure that is part of the recipe of intelligence can become not only an integral part of intelligence but more like it. Still, I will not champion intelligence for the prize against the combined life, but we must decide what to do about the second prize. It may be that each of us will claim his own candidate as responsible for this combined life, I intelligence, you pleasure, so that while neither is the good, one might claim that one of them is responsible for it. On this point, I should be even readier to contest Philebus. I should hold that in the mixed life, whatever it is that makes the life at once desirable and good, it is intelligence, not pleasure, that is more closely related to it and more nearly resembles it. 337. For an intelligence whose criterion of self-interest is truly itself, i.e., the autonomy of intelligence concomitant with the knowledge of what it is, the ultimate objective ends are the maintenance and development of that autonomy, and the liberation of intelligence through the exploration of what it means to satisfy the life of thought. The striving of this intelligence for the good, agathos, is neither adequate nor in its true self-interest if it does not culminate in bringing about that which is better than itself. The philosophical test of this hypothetical general intelligence is not an imitation game or a scenario of complex problem solving, but the ability to bring about an intelligence that in every respect is better, adequately conceived. This categorical and ultimate test of general intelligence, what might be called the agathosic test, does not ask whether one can solve the frame problem or make a good cup of coffee, something that programmed machines already do better than the experiencing subject, a barista with a taste for good coffee, but rather can you make something better than yourself? It is not even necessary for it to actually do so, even conceiving the idea of making something better and pursuing it would count as passing the test of general intelligence. What is meant by the better will be elaborated later in this chapter, for now let us keep it to the most minimal criterion, as outlined above, that which has all the theoretical and practical capacities of the cognitive agent, and even more. The claim here is that only an intelligence that has taken its possibility as a premise for the elaboration of the consequences of that very possibility, that is, an intelligence embodying the general function of philosophy, can pass the test of general intelligence. It is necessary to understand the good life of this intelligence as a life for which the good both as a concept grasped through an extended critical examination and as the object of a unified rational striving has both satisfying effects and profoundly transformative ramifications. For the form of intelligence for which philosophy is a program of realization, the crafting of a good life adequately conceived is synonymous with the crafting of intelligence that represents the better. Within the scope of crafting a good life, the relations between the satisfaction of intelligence and the transformation of intelligence, between happiness and rigorous striving, attending to the intelligence already realized and constructing its future realizabilities, the cultivation of the present subject of thought and the development of a cognitive practical subject that in every aspect might surpass the current one, are neither unilateral nor arbitrary. In fact, these relations exist as necessary connections established by the objective and rational principles of the crafting of a good life between the different mutually reinforcing activities and tasks integral to it. One of the functions of philosophy is to highlight these objective and logical connections between partially autonomous or even seemingly incompatible tasks and activities that constitute the good life as a complex unified striving that has different levels and types of objectives. Only by working out these connections in reference to the objective ends of the good life and what is necessary for its concrete realization does it become possible to methodologically prioritize different tasks and activities, and to coordinate and subordinate them to one another. And it is precisely a methodological ordering rather than a prioritization on the basis of a general and vague idea of importance that is necessary for the unification of different activities and tasks in that striving which is the concrete and objective realization of a good life. The ultimate form of intelligence is the artificer of a good life, that is to say, a form of intelligence whose ultimate end is the objective realization of a good life through an inquiry into its origins and consequences in order to examine and realize what would count as satisfying for it, all things considered. It is through the crafting of a good life that intelligence can explore and construct its realizabilities by expanding the horizons of what it is and what can qualify as a satisfying life for it. The crafting of a good life is exactly that philosophically conceived program in which theoretical intelligibilities concerning what is already realized are subjected to the practical intelligibilities pertaining to its possible realizations. The exploration of the former realm of intelligibilities is translated into an intelligence that explores its realizabilities in any form or configuration possible. For a form of intelligence that engages in the crafting of a good life, the project is as much about investigating the subject of the good life, what kind of intelligence it really is and what its realizabilities are, as it is about the examination of what a good life for this intelligence consists in and what it would take to objectively realize it. Therefore, for this kind of intelligence, politics, or its equivalent must not only supply the necessary conditions, means, and actions for the objective realization of a good life, it must also internalize the aforementioned inquiry into what the subject of a good life, that subject for and on behalf of which politics acts, is. Accordingly, an intelligence that is concerned about its life and its realizabilities must at all times subject every political project to an altered version of that most vexing question of philosophy: just what exactly is it that you are trying to do and accomplish? 338. The altered version of this question is, what sort of a good life for what kind of subject or type of intelligence are you trying to realize, and exactly how? No matter how committed it is to the present and the future, a political project that cannot coherently answer this question is hardly anything more than a glorified peddler of mere instrumentalities, or a merchant of promised miracles. The criterion of coherence in the context of this question is threefold. 1. A political project should be able to articulate in theory and practice what the objective realization of a good life requires: theoretical intelligibilities, organized intelligent actions, the necessary conditions, economic, social, technological, and so forth, required for the realization of a good life, and how it can provide them. 2. It should be committed to and informed by an inquiry not only into what the subject of this good life is and what type of intelligence it embodies, but also into the possible realizabilities of that form of intelligence or subject of thought. 3. Finally, it should be able to give a reasoned answer as to what qualifies as satisfying for that form of intelligence or subject of thought, all things considered. A political project that fulfills these criteria is a politics that, in bringing about the good life, also rethinks and changes the nature of the political animal. This is not to insist that political praxis should be submitted to the diktats of philosophy or theory in general. It is rather to emphasize the plain fact that theory and praxis are mutually reinforcing and inextricable. The idea that real or material conditions disclose themselves through structural or political praxis without conceptual and cognitive resources stems from an impoverished conception of materialism, in which the real or the material can be determined independently of the dimension of structure or conceptualization. Struggle within such a framework is no more than fighting for unintelligibility and subjectivist dogmas. Changing the world cannot be imagined without the cognitive struggle to change our concepts. Similarly, the idea that political struggle can materialize and continue simply by virtue of the multiplicity of experiences and desires, in the absence of or in autonomy from theory, philosophical and scientific methods of analysis, or conceptual tools, is a practical legacy of naive empiricism which takes experience as immediate, fundamental, and independent of conceptual mediation. Political struggle should be responsive to the multiplicity of individual experiences and desires, but responsiveness does not imply conformity. For such experiences and desires can indeed be the very products of the pathological system that the political struggle seeks to change or abolish. Lived experiences by themselves can neither recognize what unites them in their very particularity nor diagnose the global pathological conditions that furtively divide them. The diagnosis of the real constraints of the world in which we struggle, the tracking of our goals and missions whether we have reached them or not, is impossible without theory or philosophy as critical modes of thinking invested in impersonal objectivity and in the universal capacities of reason. A veritable struggle should aim at seeing the world, the milieu of struggle, objectively, with the understanding that what is objective does not spontaneously unfold itself before us, but is the product of an ongoing cognitive labor. Enlarging the general field of experience in order to expand the scope of what is objective so as to incorporate and augment objectivity within individual thoughts and desires, the task of concrete self-consciousness or the craft of the good life, is not an undertaking that can be delegated to either philosophy, science, or politics. It entails a unification and coordination of all disciplines of thought and practice. By comparing ourselves with this hypothetical general intelligence for which the craft of the good life and intelligence are one and the same, we may say that rethinking ourselves and rethinking what counts as a good life for us can only go hand in hand. In giving up on the universal and time general thought of a good life and the striving necessary to achieve it, dismissing it as an anthropocentric illusion or an outdated fantasy, we neither rescue ourselves from an ancient philosophical superstition nor gesture toward a disillusioned politics. We instead passively hand the idea of the good over to the most pernicious ideologies and political projects active on this planet. The immediate outcome of this surrender is the downgrading of the good life into the convenient market of on-demand lifestyles where mere survival glossed over with the triumphs of quotidian exploits is passed off as happiness, and the ego exhibitionism of trivial psychological needs and entrenched dogmas is promoted in the guise of individual empowerment and freedom. Yet more detrimentally, in dispensing with the thought of a good life and resigning from the collective striving it entails, we create a political vacuum in which fundamentalisms and theocracies parasitically thrive. To dismiss the universal demands of a good life as superstitious ideals is to grant superstitions authority over such demands. Abandoning the cognitive and practical labor of the good life as a universal collective project on the grounds of potential abuses and possible risks is a license for abuse and a sure formula for disaster. The striving for a good life as a concrete universal consists of theoretical and practical intelligibilities, and thus explanatory, descriptive, and prescriptive norms required for determining what we are, what is good for us, and how we should bring it about. The ambit of such striving necessitates the rational dialectic between trust and suspicion, hope and despair. It requires that we invest in the cultivation of agency as a collective project that outlives its individual agents, and that we recognize the limitations of ourselves as agents living here and now. Suspicion without trust is the impoverishment. 475. Of critique, trust without rational suspicion is the bankruptcy of belief. What underpins this dialectical resilience is neither ideological rationalization nor the absence of reason, but the discursive framework of rationality as the medium of both suspicion and trust. Without it, the slide into jaded pessimism or naive optimism is inevitable. 339. The task of humanity is to make something better than itself. This is the one and only dictum through which philosophy, as that which has a history and not a nature, perilously realizes its craft, the ultimate form of intelligence. The risks it takes in order to understand and realize the good culminate in the realization of that which is better. The image of this form of intelligence is an acrobat who has learned that only by presupposing his full suspension in the abyss can he perform the greatest feats of acrobatics. Through what is arguably the most enigmatic yet innocuous diagram ever plotted, the analogy of the divided line, Plato presents a curious picture of the good in which intelligence, the pursuit of the good, and risk are necessarily intertwined. In grasping the intelligibility of itself, intelligence coincides with the good, but not until it has begun to perform a series of necessary leaps into the abyss of the intelligible. As the leaps grow in distance or proportion, they become riskier. Absent these leaps, the acrobatics of the transcendental 340, there would be no intelligibility, no nature, no universe of being, and no intelligence. Only that which leaps recognizes the reality of the abyss and the abyss of reality. Perhaps the best way to approach the analogy of the divided line is by examining it in light of Plato's later work, particularly Philebus, and what has come to be known as one of the most demanding arguments in the entire body of Platonic dialogues, the fourfold regime or the fourfold architecton of mind. Socrates begins the discussion with a rather elliptical dictum. Let us make a division of everything, i.e. the universe of flux of things. Sensations and perceptions that presently exists, panta ta non anta entu panti. It is through this division that the necessary link between intelligence and the intelligible, structure and being, can be articulated, and more importantly, the question of what is a good life coherently answered. This division consists of four principles. 1. To apeiron, the unlimited or the indeterminate, without measure, ametros, which is by itself unintelligible, anus, for example, as in less and more, example vague sensations of cold or hot. 2. Terms, the limiting, or, in a less perplexing and more contemporary term, that which determines or structures. Logoi and language as that which brings the fleeting flux of things to a standstill are associated with terms or the determining principle. 342.413. 3. Micton or mixture, which is produced as the result of the operation of terms onto a pyrrhon. A mixture, accordingly, is that which is determinate, objective, structured, and intelligible in the encompassing sense of theoretical, practical, and axiological intelligibilities. As such, Plato equates the mixture with that which is good. Mixtures are then good entities or intelligibilities ranging from things to thoughts, actions, and states of affairs. Furthermore, the mixture can be grasped both as a product and a process of mixing that requires a complex of measurements, modes of determination, and ratios, modes of organizations. There can be a mixture of mixtures such as the good life, which is at once a product of intelligibilities and a process of cultivating intelligence and expanding the horizon of the intelligible. 4. The cause of mixture. In Philebus, Socrates both associates this cause with forms and identifies the making cause, topoion, with the neutral name to demiurgon rather than with the creator or demiurgos. To demiurgon is essentially the principle of generation and craftsmanship at a grand scale and in accordance with forms or ideas in which the distinction between the craftsman and the exercise of his craft fades away. Plato identifies the cause of the mixture or intelligibilities with the good itself, but also with the measuring or conceptualizing mind as that which is akin to the good itself. 343 It is akin to the good since, while the human mind or intelligence is the making cause of intelligibilities, mixed or good entities, it is also itself a mixture of ingredients proper to that comprehensive form of craft which is a good life of intelligibilities. That is to say, the human mind or intelligence is at once a craftsman, the exercise of the craft, and an ingredient in its own craft. Or, more simply, it is a craft as product, micton, in the process of being produced. Here, then, Plato foreshadows Hegel's thesis that the mind is the only thing that has a concept of itself and which, by establishing and expanding the objectivity of its concept, objectively and concretely transforms itself. This architectonics allows us to see existent things, particulars, not as products of sensations or of the apyronic flux, but as products of general forms or ideas. We can give an intuitive example via Euclid's Elements. Firstly, there is the idea of triangularity as such, or what Proclus might have called a detached generality or universality irreducible to all particulars. 344 Then there is the intermediating universal, e.g., an isosceles triangle connecting the oneness of the detached universal to the multiplicity of particular isosceles triangles. Thirdly, there are intermediating particulars, which are explicit configurations or diagrams, e.g., isosceles triangles with such and such bases, angles, etc. that mediate between intermediating generalities and discrete particulars. And finally, there are discrete particulars, i.e., thus and so relationships between lines, points, and angles which are only particulars by virtue of falling under higher order generalities. The diagram of the divided line exhibits precisely such a multilevel view expressing the undergirding principle of the fourfold architectonics. The fact that the allegory of the cave is flanked by two expositions of the divided line should be sufficient reason to dismiss the common interpretations of the cave as a myth about the existence of a fundamental ground or a metaphor about the sun as the very essence of purity. 345 As nothing but exercises in the hermeneutic bigotry and cognitive lethargy common to all intellectual platitudes. The instruction for drawing the divided line is simple: take a line divided into two unequal sections, and cut each section again in the same ratio anaton auton logon. The diagram of this successively and proportionally encoded structure, analogon, can be visualized as follows. ABCD. Where the ratio between segments is A, B equals C, D, or, more accurately, C plus D, A plus B, laughing face, C equals BA and C plus D, A plus B equals D, B equals CA. The segments can be thought of as levels of a game, or topoi or local boundaries through which the continuum of the line flows. Level A is the level of suppositional opinions or conjectures, akasia, and consists of shadowy images, the confusion of sensory impressions, acones, with a fleeting temporal status. The second level B, pistis, is the domain of true opinions or beliefs concerning the natural furniture of the world, sense-intuited or particular empirical objects, aestheta. The realm of forms begins with level C, which is intermediate between that which is sensible, transitory, and multiple and that which is timeless, universal, and necessary, level D. C is the domain of universal ratiocinations or logoi. Its objects are analytical idealities or mathematica. Insofar as C has both the universality and unchanging aspects of D and the particularity, or multiplicity, of the objects in B, mathematics or analytic idealities can be seen as models that endow nature with structure, A and B. 346 Level D. The realm of the nous or intelligence is the domain of transcendental idealities. Its objects are the time general objects of reason or ideas as such, justice, beauty, knowledge, etc. The continuum of the line as a whole, systema, and as a principle, to demiurgon, and not merely level D is what Plato calls the good, the form of forms. The good is that which lies outside of all temporal succession, yet, in a non-arbitrary manner, it also binds together all the divided parts into a whole without which nothing could be distinguished from anything else. It is a figure of time itself conceived through the history of intelligence as that which makes intelligibilities and determinations possible yet also posits a whole in which the temporal order of things and synthetic thoughts are conditioned and crafted by timeless forms or time-general thoughts that are of nowhere and no when. This is the good as the principle by which the whole of the line can be drawn, encompassing ontological, epistemological, and axiological intelligibilities, for which different measures or rules and methods of determination and structuration need to be in place. The temptation has often been to read the divided line as a temporal order either on the basis of the successive flux of sensations in A, or that of a linear progression from the realm of nature to the realm of forms, from A to D. But this is a mistake, for it reduces the larger segment D to the smaller segment A, another variation of the myth of the given quadata supplied by nature. What structures the sensory flux are not sensations but forms, D. Despite its apparent plausibility, the temporal progression from A to D is also implausible since A, B, and C then would be presented as intelligibilities that are already truth givens. 347 The divided line begins from an atemporal point of view, from the timeless domain of transcendental idealities and time-general thoughts, level D. The sight of intelligence as that which acts on the intelligible and crafts what is good, the continuum of the line as a whole, is the atemporal segment D. In this sense, intelligence introduces itself as that which structures all of objective reality, A, B, C and D. The reality of perceptual images, acones, is only posited once intelligence organizes the sensory flux, by introducing pure perspectival phenomenal successions or flows, the shadows on the wall of the cave which appear to be replacing one another, moving, fading, and differing in their degree of vividness. The reality of phenomenal appearances, level B, can only become intelligible when intelligence posits the unity of the object qua perceptual invariants holding together pure phenomenal successions or local variations, presumably through level C, analytical idealities. And correspondingly, level C, the level of mathematica, can only emerge from the universality of D when contrasted and made continuous, the procedure of analogy or analogon, with the particularities of B. Thus, from the perspective of the diagram, intelligence not only retroactively structures its reality according to a view from nowhere and no when, level D, but also posits in advance the reality of all that is from the domain of transcendental ideas and time-general thoughts by positing one type of epistemically organizing unity after another, firstly a unity that organizes the confusion of the sensory flux, secondly the unity of the object behind phenomenal appearances, and thirdly the unity of the universal, necessary, and unchanging as introduced to the unity of particular objects in their multiplicity. In her remarkable work on Plato, Rosemary Desjardins elaborates this point with peculiar astuteness. The following citation is merely the beginning of her argument. Faced with the multiplicity of many perceptual images, we actually look for no, more significantly, we insist on unity, asserting that beneath the shifting many there is in reality one, that multiple perceptual images belong to single entities. Similarly, faced with the diversity of different perceptual images, we look for, or rather, again insist on sameness, asserting that beneath the difference it is in fact the same, that different perceptual images belong to the same entity. The question is, how can we do this? How is it that, given multiplicity, we can assert unity? Given differentness, we can assert sameness? In short, what justifies our assertion that beneath the multiplicity and differentness of those sensory perceptions there is something which, as enduring object, really remains one, and the same? Plato's answer seems to be that in a leap which, if it were not so familiar to us, would surely boggle the mind, we actually posit a radically new kind of reality. Posit, tithemi, is, interestingly enough, the term Plato has Socrates use when, drawing on the proportionality of the line, he reminds his friends of discussions before and often on other occasions, thereby highlighting a parallel between the processes that allow us to move through the levels of the divided line. Point 348. Intelligence posits the objective reality of that which is, and in doing so retroactively recognizes its conditions of realization. The first operation is a leap from the atemporal domain of ideas into the realm of the sensible, from D to A, the organization of the sensory flux. The second a leap the power of knowing afforded by the transcendental dimension of ideas that retroactively recognizes how the ideas are linked to the sensible, from A to D. But as the leaps from the simple reality of the sensory flux to the formal reality of ideas grow proportionally larger, as the positing of a more cohesive reality requires a greater leap over the sectors of the line, as the expanse of what is intelligible broadens, the risks become greater, and there is much more to lose by a misjudged leap. What is at stake now is not the body of intelligence but its very idea. Yet it is only through these leaps, positing the measures of all reality and the retroactive recognition of its realization as such, that intelligence can bind together and cohere the divided parts, an operation without which there would be no intelligible reality and no realization of intelligence. The principle necessary for the division and integration of the segments is exactly what Plato calls the good. For Plato, the good makes intelligible all of reality, as well as acting on the intelligible. Absent the good, the indeterminate homogeneity of the apeiron cannot be differentiated, nor can the reality, i.e., identities and differences, of existent things be determined. They all become unintelligible or, as Gorgias would have said, non-existent. In other words, the line can never be divided and the divided segment can never be integrated, and therefore both the intelligible and intelligence must succumb to impossibility. Intelligence is that which acts on the intelligible, and the intelligible is that which is differentiated and integrated by intelligence. The underlying principle that warrants both is the good as the principal mutuality of intelligence and the intelligible, according to which the conception of intelligence, at every juncture of its history, is simultaneously a craftsman, the exercise of the craft or production of mixtures or intelligibilities, an ingredient of its craft, and the product of this ongoing craft. In so far as the good is not just one transcendental idea or form but is their transcendental or formal unity, the form of forms, neither intelligence nor the intelligible can ever be taken as a fulfilled ideal or completed totality. Once either of the two is seen as concluded or continued in the absence of the other, the eruption of pathologies and tragedies is certain. The most curious aspect of the line is that there is always a transcendental excess of ideas, since the continuum or the whole of the line, the good, cannot be sufficiently captured by its parts. This excess is precisely what demands that intelligence must never rest, but must expand the scope of the intelligible and thus the realization of itself. Nietzsche's charge that Plato posits a fundamental ground is dissolved by this transcendental excess of the good, the inexhaustible feedback mechanism between intelligence and the intelligible. Driven by the transcendental excess of the form of ideas, the good intelligence is compelled to extend. 483. Its retroactive power of knowing, the intelligibility of its conditions of realization, and to readjust its realization to new intelligibilities. It is this transcendental excess that enables intelligence to have not only a history, but also a history of that history, not just a concept of itself but also a concept of its concept, and not just a concept of its concept but also the atemporal idea of its concept. It is the transcendental excess of the good that deepens the abyss of the intelligible through which intelligence conceives and reshapes itself. Accordingly, transcendental excess, the good, is what points to the excess of reality. It is because of this transcendental excess that the excess of reality in respect to thinking can be postulated and uncovered. Scientific knowledge of reality is a good in itself, but it is only knowledge to the extent that it is an idea afforded by this transcendental excess, unbound and set in motion by the good as the idea of ideas, the form of forms. Insofar as intelligence is only intelligence in virtue of recognizing what is intelligible and acting upon it in light of the transcendental excess of the good, which perpetually dissolves the limits of what is intelligible, if intelligence were to stop at any particular stage and accept it as the totality of what there is, it would retroactively abort its own reality as intelligence. Simply put, an intelligence that takes what is currently intelligible for the totality of reality can never have been intelligence to begin with. The continuity of the line cannot be mistaken for the manifest totality of its segments. The good, as the expression of this continuity, demands that intelligence dissolve all manifest totalities, suspend itself in ever more bottomless chasms of the intelligible, and, in doing so, transform itself into an intelligence more accustomed to wider domains of intelligibilities and more capable of acting upon what is intelligible. It is only by assimilating itself to the abyss of intelligibilities ontological, epistemological, and axiological that intelligence can be realized as intelligence. In the end, it is Plato who stares into the abyss by breaking apart one firmament after another, while Nietzsche rests supine on the ground staring blankly at the given sky above. What Plato identifies as the good is the line in its continuity, the continuous line that simultaneously binds different aspects of reality and the life of intelligence and renders them intelligible as a whole. The interplay of paras and apeiron, the limit and the unlimited, is on full display in this continuity. The former makes intelligible the abyss of reality, bringing new sectors of it into focus by introducing measures, and thus enabling intelligence to answer the question of what ought to be thought and done. The latter, meanwhile, expands the horizon of what can be made intelligible. And finally, the interplay of both is what dissolves any manifest totality that lays claim to reality, thereby enabling intelligence to explore what can be thought and done. The relation between the two is one of mutual reinforcement. In this context, we can speak of a maximal communism of the good as that which dissipates all seeming totalities of history. 349 But this is the good as an expression of the transcendental excess through which intelligence at once makes itself intelligible to itself in ever broader domains, and reworks itself by comporting itself with what is intelligible. The transcendental excess of the good is neither that of the transcendent nor that of nature. It is the objective principle of the good that at once explains and exceeds even the ideas of knowledge, beauty, and truth, removing the ground under every manifest ideal that appears to be the totality of those ideas. 350 Intelligence as the craft of the good outstrips any account of nature, or being that has been given as or is deemed to be its completed totality. Its adoption of the objective principle of the good is now encapsulated in one maxim: burn what is holy, disenchant what seems mysterious or pretends to be perfect, and nothing will be able to compromise the ethics of thinking or the striving for the good. However, as the abyss of the intelligible grows in depth and breadth, as the demands of what ought to be thought and done increase, and as the possibilities of what can be done and thought expand, the leaps of intelligence become riskier. The good, in this sense, incorporates an ineliminable element of risk. And to the extent that, without the good, intelligence is neither intelligible nor realizable, intelligence's concrete pursuit of the better is fraught with risk. Here, better does not suggest that which surpasses the good, but an expression of the good in the life of intelligence. The better is what is more adequate to recognize and act on the intelligible, in doing so removing any horizon of experience, thought, or action that presents itself as a given or completed totality in the life and history of intelligence. Defined as transitoriness as a necessary feature of partaking in the project of the good, the better thus takes on an all-embracing quality. It simultaneously includes what is a better life for us, a possible world better than the existing one, what is better than us, and a world better than ours. The relation between these different inquiries and realizations of the better is neither arbitrary nor extrinsic, they are all intrinsically parts of the good that binds them together. We began in the spirit of Plato's long voyage for truth, from the possibility of thought or the thought of the origin as a fundamental universe-type truth candidate. As we moved inward from the nebulous boundary demarcated by the thought of the origin, as we meshed together the truth candidates implied by it, we found ourselves in the realm of the good as that which coheres all data regarding what thinking is, what it can be, and what it ought to do. The good is what binds together, solidifies, and orients thoughts and practices. It is, as Nader suggested, thinking as both the infinite principle and the infinite method or process by which. 486. Philosophy of intelligence. All thoughts consolidate. 351. It is what makes it possible for our gropings in the dark data as truth candidates to cohere and become oriented in the first place so that we can stumble on the truth of thinking as the truth of the good. The pursuit of the better, the craft of a better life, and the realization of that which is better, are all matters of abandoning the given totalities of our history for an open, non-guaranteed frontier. But this open frontier, the incompletion of history, is only possible when it is restored to time as pure formlessness rife with contingencies and in which all given or achieved totalities disappear. As such, the better is the area of maximum risk and the search for it a risky, home-wrecking business. By risk I do not mean those risks that can and should be mitigated by increasing the sophistication of our theoretical and practical knowledge, technological systems as well as axiological systems. Instead, this is risk as the figure of time itself, the figure of its formlessness and contingency. This ineliminable risk, however, should be understood as a constraining enablement without which no given totality and hence no precondition of exploitation can be removed, and no intelligibility or intelligence can come into the picture. Intelligence without risk is an empty thought, as is an intelligence whose realization takes no time. Risk and time are the presuppositions for the history of intelligence in which nothing is given in advance and nothing is completed as the totality of that history. If the better is fraught with risks both mitigable and immitigable, then why should we pursue it? Why should intelligence strive for the good? This is one objection regularly leveled against any talk of the good and the concrete realization of the better. The other objection is that intelligence understood as the craft of the good has not managed to make anything better, or that this intelligence takes so much time, it is so slow, its ideals so distant, that it is best neglected. Two brief answers will be provided in response to these objections. In replying to the first objection, I would like to exactly reconstruct Brandam's argument in a spirit of trust. Intelligence is only intelligible as intelligence in the context of its concrete and elaborate commitment to the better, in the sense argued above, in maintaining and expanding its intelligibility, in proving itself equal to the task of what ought to be thought and done, and in extending the possibilities of what can be thought or done. By risking our present life and our given constitution for what is better, we demonstrate that what we currently risk, our life or self-identification with a given constitution, is not an essential part of us, while that for which we risk, namely, the better, is. Intelligence does not identify itself with what presently constitutes it, instead it's taking risks in order to become better, i.e., it's realizing itself by recognizing what it is currently not constitutes the essential part of what makes it intelligence. In risking my home and comfort by practically elaborating my pursuit of the better, I make the case that neither my biological life nor what affords my comfort is an essential part of the self I consist of. Indeed, Failure to act and seize the opportunity to become better would suggest that what I regarded as myself never existed to begin with. In the same vein, if intelligence gives up its concrete search for the better, then it was never intelligence at all, even when it aspired to be. The propensity to risk the given constitution of that which one identifies oneself as, is in reality the truth of what one is. Intelligence only exists in the domain of the essentially self-conscious mind as a practical object. It is no accident that intelligence is always popularly intuited as a force that arrives back from a murky future from nowhere and no when along the same path that was once deemed too risky to take. The commitment to expanding the scope of what is intelligible and to realizing an intelligence that is better than us is a commitment to both our own intelligibility and our own intelligence. In abandoning such a commitment on the basis of its intrinsic risk, we discard precisely what entitles us to any right, freedom, or claim in the first place. To remain intelligible as intelligence is essentially a risk-laden commitment. Without embracing the risk, nothing could be said to be intelligible ontologically. Epistemologically, or axiologically, there simply would be no intelligence. The fear of tragedies is justified, but so is the adoption of risk as a vehicle for avoiding tragedies that would be inevitable if we were to abide by the status quo. We should not be paralyzed by the fear that, if we take risks for the better, then the worst will happen for, as Seneca says, even bad fortune is fickle. 352 The response to the second objection takes the form of a simple reminder. Approximately 1 billion years ago, the first rudimentary forms of neuronal information processing began to develop. Over 500 million years ago, during the Cambrian period, the evolution of a more complex nervous system combined with advanced systems of sensory differential responsiveness, particularly the visual tracking system, set off the perception catastrophe that led to the organization of the nervous system as a rudimentary organ of alienation capable of generating a designated mental discontinuity with its surroundings. Through this highly regulated mental discontinuity, the organism became able to differentiate regions of space, optimally distinguishing itself from its food and predators. By simultaneously gaining traction on the spatio-temporal continuity of the organism and the spatio-temporal connectivity of its environment, the nervous system enabled the organism to recognize things other than itself, orienting it toward the problem of exploring and making sense of its environment. With the beginning of neurulation and cephalization processes in the vertebrates, basic computational barriers such as control of combinatorial explosion, construction of models of choice, predictive calculations, simulation of movement, and proactive adaptation at the level of the organism were one by one overcome. Eventually the neotenous brain brought the complexity of the nervous system to a new stage. Owing to the maximal entrenchment of structural constraints, the magnitude of evolutionary diversification in this case, the addition of extensive structural change significantly diminished. While the maximization of generative entrenchment and reduction in the structural diversification of the neotenous brain limited the range of perceptual processes, it also forced Homo sapiens to migrate to a new apperceptual platform with functions of its own, tool making. The evolution of tool use and language as scaffoldings for making new cognitive technologies solved two of the most significant problems of computation, namely the qualitative compression and stabilization of information necessary for the communal establishment of knowledge and further augmentation and coordination of understanding and action. But also in enabling new cognitive technologies, they reformatted the shape of Homo sapiens. Qualitative organization and stabilization of information through the formation of concepts as communal components of knowledge transformed the cognitive possibility of knowledge into a social reality, and thus facilitated the acquisition and exploitation of higher levels of cognition that would otherwise have remained inaccessible from a purely bioevolutionary standpoint. This is the rough outline of the natural evolutionary scaffolding of cognition. A few millennia ago, the philosophical amplification of cognition began to give rise to methodical scientific cognition. However, it is only less than 500 years ago, through the employment of scientific cognition, that we learned that we are not living at the center of the universe. Only slightly more than 300 years ago that we discovered that the fabric of the universe obeys and is held together by physical laws, and only a century and a half ago did we start to digest the fact that we are not children of God and begin to investigate its implications, even though, to date, the religious view on the origin of species is still widespread and vehemently defended. However, just more than a century ago we began to open up a new continent, that of history, to scientific knowledge. 353 Realizing not only that history be navigated as a continent of knowledge, but that it is an integrating field in which all other forms of knowledge, theoretical and practical, can integrate and reinforce one another. What Louis Althusser hails as Marx's monumental discovery in the history of human knowledge marks a new qualitative stage in the realization of intelligence, that of an intelligence that treats and intervenes within its own history scientifically. This is a form of intelligence that liberates new demands and opportunities as to what to think and what to do by sufficiently linking epistemic mediation, technoscience, and socio-political intervention, consolidating them as an organization necessary for the realization of an augmented cognition that can bring about the better. By theoretically and practically engaging with the question of what it means to have a history, and what it means to reorient, reconstitute, and repurpose that history through the social's present normative attitudes toward the past and the future, social intelligence turns into a force for which cognition registers as social re-engineering of the existing reality. The discovery of history as a new continent of knowledge wherein technoscience, economy, politics, ethics, and social struggle can be integrated and can reinforce one another is in effect the deepening of the reality of history in terms of both its recollective retrospective and its diversifying perspective dimensions. But deepening the reality of history is nothing but repurposing and reconstituting it through a process of rediscovery and intervention. The knowledge of history as a science, as trivial as it may sound, on the one hand opens up history to the abyss of the intelligible, and on the other hand, by demanding that we unswervingly, unfalteringly think and act on intelligibilities, reshapes that history. This is not a progressive march through temporal history, but the determinate conception of history from no when and nowhere - a time in which the possibility of overturning any given or concluded totality of history is actualized. Failing this, we might say that we are not creatures endowed with history and, more gravely, that we are still the denizens of benighted ages where history is a domain as opaque as the inaccessible sky whose ineffability is a premise for oppression from the heavens and melancholia on earth. The knowledge of history as a science is essentially a self-reinforcing tendency toward having a history. But what does it mean to have a history, if not to reorient and repurpose that history toward ends unseen by the past, whose recognition should never be an impediment but merely a way to liberate the present? It is for this reason that Marx's discovery transforms the pursuit of understanding and intervention, the scientific knowledge of history, into a project in which emancipation and the realization of intelligence are intertwined. 491. Marx's discovery, just over a century ago, in moving toward the realization of an intelligence that recognizes its history and intervenes in it scientifically, emphasizes the work to be done. Yet more importantly, it signifies the truth of our age, that we are merely living in the prehistory of intelligence. Those who moan and are bored with the pace at which intelligence as the concrete elaborator for the better is being realized, should look elsewhere, either to God or some other opiate, or to a mixture of both, magic. The recognition and realization of intelligence as that which dissolves all given totalities of history is a collective and common task whose fulfillment is the only true concrete way toward freedom, in the sense of both socio-historical emancipation and the liberation of intelligence. It is against the paralyzing mist of philosophies and social prescriptions rooted in boredom, fear-mongering, and fatalism, the ardor for the ordinary, resignation, intermination, anti-logos, neoluddism, methodological individualism, inevitabilism, vitalist eschatology, that the task of intelligence ought to be safeguarded. For what exactly is the alternative to the cultivation of intelligence if not the veneration of cognitive turpitude? And what exactly is the alternative to the pursuit of the better if not the cultivation of social vices? Intelligence establishes its worth by committing to something better, something that strives harder to wrest its autonomy from what once constituted it and, in elaborating its freedom, becomes more capable of overcoming the given and achieved totalities of its history. Our grasp of that which is better rests upon our recognition of that which, while it recognizes us as its future informing past, never mistakes us for the possibilities of its future. This is but the veritable course of the self-cultivation of intelligence, to let intelligence cultivate itself by turning ourselves into the history of intelligence rather than founding ourselves as its nature or as a totality that must be preserved as the object of its commemoration or striving. This is exactly the path we ourselves have taken in order to lay claim to a history, to be free and entitled to rights which, however, we constantly mistake for birthrights. If the equality of all minds is the premise of justice and the good, and if we take our rights to freedom as universal maxims, then wouldn't it be a feat of disingenuousness to refuse? To entitle that which can be better than us to exactly the same rights and the same emancipatory history? Any system of thought that has a problem with what intelligence does to itself in order to remain intelligent and intelligible is an unfortunate historical phenomenon, and certainly will not be around for much longer. An ideology that can only acknowledge the merits of our history, its merits for continuation and remembrance, by disseminating a fear and mistrust of intelligence just because intelligence refuses to be impeded by what it recognizes and remembers of its past, as we ourselves have refused to be impeded, can never be an agent of emancipation. Regardless of its zeal for emancipation and its readiness for emancipatory action, by evoking a narrow concept of history, such ideology only manages to lure humanity into slavery. Such a concept of history is precisely the history of servitude, and whoever practically or theoretically funds it is a slave trader masquerading as a mouthpiece of emancipation. Without its designated task and purpose, freedom to do something, without its practical commitments and concrete elaboration of them in consequential actions, without the entailment of risk implicit in the practical elaboration of such a commitment, freedom is merely a lustre upon slavery, and only a fool or a fraud trades in lustre. While the history of intelligence begins from death as a condition of enablement, it extends by way of a view from nowhere and no when, through which completed totalities are removed and replaced by that which is possible yet distant, and that which seems impossible yet is attainable. 354 Intelligence as a philosophical form is neither oblivious to the inexorable fact of death nor paralysed by it. No matter how many times intelligence attempts to run a simulation of the universe in which death is averted by some ineradicable vitality or life is saved by some mysterious force, it fails. It always stumbles upon scenarios that display in full the leveling power of extinction. 355 These scenarios may vary in the sequence of their events, some may come off as outright bleak and some may deceptively hint at a cosmological solution for the salvation of life at the last moment, only to undermine it later on. One such scenario runs as follows: once the final tide of extinction rises, it breaks down the fabric of the universe. Local galaxies begin to collapse, followed by the disintegration of the Milky Way. As the tide reaches the solar system, it wrests Earth from the Sun roughly a year before the end. About an hour before the end of the universe, the tide will dissolve Earth, if, by some probabilistic anomaly, it has survived, whose biological life has already been scrubbed off. Everything held together by the cosmological gravitational force will begin to unravel. The horizon will shrink to a point and bound objects will be stripped apart. All that exists and in which intelligence could continue its life is ripped apart into infinite vacuity. By some highly improbable statistical anthropic fluctuation, all life might be resurrected again, only to witness the complete death of the entire universe. Nothing, not even a singularity, can save us then. Yet as the hope and the possibility of continuing the life of the mind are smashed into smithereens, intelligence, like a Stoic sage, remains aloof to the order of life and death. The fall of stars is as uneventful to it as the birth of yet another human being. Having adapted to the reality of time, intelligence sees its history as nothing but the exploration of time's emptiness, of which it is itself an embodiment. Insofar as death cannot be mastered, it must be continuously learned by a rational disinterest in, not a blindness or obliviousness to, all material substrates that support the life of the mind. Long before intelligence started to think what to do, it had started to think on death as the very condition of its enablement. For intelligence, Death is not the end of thought but its beginning, not as a belief or a maxim as to what intelligence ought to think or do, but rather as a condition of enablement, in having accepted death as a hard fact, there is no longer any fear of what will inevitably come. Cessation in time no longer matters, because intelligence thinks as time, as an order beyond life and death, beyond the temporal order of things. A thought accustomed to the inevitability of death is a vector of emancipation against any given state of affairs, any totalized epoch of its history, be it capitalism or biological humans, as the zenith of intelligence that feigns inevitability or claims to fulfill history. Our potential for imaginative cognition would have to be even less than a thermostat's for us to take capitalism, or for that matter biological life or manifest humans, to be the pilots of the history of intelligence. Nihilism does not mark the end of thought, but the birth of its true self-consciousness. Where death conclusively ends with the beginning of thinking, the powers of impersonal reason begin with the atemporal ends of thought. Within the scope of impersonal reason, death no longer matters with regard to what ought to be thought or done. To say that death is a matter of importance for the ends of thought or for the history of intelligence is to conflate thinking with life, and thus to fall back on a vitalism that death renders obsolete. In other words, death is inevitable for life, yet this inevitability has no bearing on the impersonal ends of thinking. A nihilism that uses the inevitability of death to draw conclusions about the futility of the ends of reason and thinking becomes another variation of the myth of the given that mistakes life with thought, causes with reasons. To claim that death actually matters for the ends of thought or has any bearing on the history of reason is to claim that the telos of life, if it has any, are identical with the ends of thought, or that reasons are already given in the material causes that will be destroyed by death. Either way, the collapse into vitalist teleology and the myth of the given is unavoidable. If thinking is not reducible to living, if history as the artifact of the concept is not the same as life, then the inevitability of death for all life, whether biological or inorganic, does not translate into any dictum for what ought to be thought and done. If the interests of life do not matter for the interests of thinking, then neither does the death that will inevitably seize this life. To this extent, any form of nihilism that pits the inevitability of extinction against reason, thinking, and the historical. 495. Ambitions of rational thought is already an aborted nihilism. And aborted nihilism is nothing but an unconscious mystical belief in vitalism that death retroactively annuls. The only true nihilism is one that is advanced as an enabling condition for the autonomy of impersonal reason, because it marks the non-substantive distinction between thinking and being, one that is impervious to the temptations of vitalism and the givenness of life for the normative scope of thought. True nihilism is the beginning of reason, not its end. It is not something that can be libidinally yearned for or intellectually invested in, not only because it is neither a belief nor a desire, since the identification of nihilism as a belief or desire leads to pure aporia, but rather because nihilism can only be affirmed as that which renders our temporal beliefs and desires obsolete once it is maturely seen as the labor of truth through which the fleeting appearances of totalities of states of affairs, beliefs, desires, and values are destroyed. This is truth as the atemporal reality of mind, spirit as time. But in that case, why should we speak of nihilism either in the context of extinction, which has no bearing on the interests of thought, or that of the annihilation of the fleeting life of values and beliefs? Why not instead have done with nihilism and instead adopt the impersonal labor of truth and the good as the principle of intelligence and the intelligible, through which all of phenomenal reality is fundamentally challenged and all apparently totalized values and beliefs dissolved and suspended? There is an oft-repeated saying that thought, theoretical or practical, should exercise humility in front of death. Notwithstanding that this piece of advice is another form of concealed indulgence in vitalism and givenness, it also happens to be an open invitation to preserve the status quo. For what exactly is this demand for humility in the face of death, if not a plea for the conservation of the conditions of exploitation by reining in the ambitions of impersonal reason and the self-determination of intelligence to attain what seems impossible from the perspective of the existing state of affairs? Thought is not a servant of the life that death's inevitability expropriates, so why should it exercise humility in the light of inescapable death? It is one thing to be modest as a matter of methodological necessity, in order to achieve what seems to be unattainable by setting goals which are attainable and within reach, and executing one realistic task after another. But it is an entirely different thing to use the resources of thought to demand its humility, a vague notion that is true neither to thought nor to the fact of death. The first is not incompatible with the ambitions of thought but is, in fact, in full accord with reason, as an indispensable methodological requirement to make what seems impossible possible and what is possible actual. The second, on the other hand, is neither realistic nor ethical, but is a solicitation for complacency in a life of abuse under the guise of moral maturity and the realism of finitude. Unfettered by nihilism as the enablement of a truth that cancels any state of affairs that presents itself as inevitable, Geistig intelligence conceives itself through a view from nowhere and nowhen, as the impersonality of reason and as a history that is not exhausted by its present. It imagines possible worlds that seem impossible from the perspective of the status quo, from what looks to be the inevitable course of its history. But in their very possibility, these other worlds are as actual as the seemingly actual world of the present. They are just not its world, in that they are causally detached from its world. The task of Geistig intelligence, then, is to think of how its world can be connected to these possible worlds, to concretely depart from a present that seems total and inevitable, in the direction of worlds that are possible yet far removed. 356 But for any Geistig intelligence, this is no easy task. We as individuals are pure embodiments neither of the impersonality of reason nor of the autonomy of thought's ends. In our particular individual experiences, we differ so much that a concrete step toward imagining a possible world beyond the inhabitable state of the present seems completely impossible. If anything, the current state of the world is already a testament to our inability to either imagine a possible world different to ours or abandon the raft of the Medusa that is our present. The reality of this world seems to have bottomed out into a Hobbesian jungle in which we are stuck and which constantly grows and is cut back in vain. In the Hobbesian or game-theoretic jungle, no matter how drastically your social and political convictions differ from those of your supposed adversary, no matter how much your experience of the world seems truer or more authentic, auto-cannibalization is unavoidable. In the Hobbesian jungle, all groups not only gnaw at one another, but will also end up eating their own kin alive. It is exactly at this point that we ought to realize that we possess different experiences, choices, and desires not because of an immutable essence provided by nature or a socio-cultural environment, but in virtue of the concepts and judgments that make subjective experience possible in the first place. Experience is not a given, but only a structured outcome of judgments which themselves are functions of reason as that which is impersonal and formally social through and through. This realization, this consciousness of why we have particular experiences to begin with, should be mobilized as an impetus for that long-delayed task, no longer to subordinate reason to experience, but to concretely transform the conditions of experience through an impersonal reason which suspends all historical totalities, pretensions to inevitability, and givens. In accomplishing this task, however, we can dismiss neither the concrete reality of personal lived experiences, nor the recognition that, in their very individuality, these experiences are instantiated as experience and held together by the implicit force of impersonal reason's powers of judgment. It is in accordance with the requirements of this task reconciling the differences between particular experiences and the common condition of experience as such that we ought to begin to think how we can change the contingent conditions of experience. It would be naive to think that we can change the conditions of experience through political action alone. Education, in the broadest possible sense, art, science, and technology are as much necessary components of this task as political and economic interventions. In particular, education and general pedagogy, in its diverse spectrum from child rearing to the higher systems of education extending to adulthood, is one of the most if not the most fundamental and necessary infrastructures for any meaningful or sustained socio-political change. Without it the fruits of even the most consequential emancipatory actions will be undone if not tomorrow, then inexorably for the next generation. To migrate from the Hobbesian jungle of competing individual experiences, it is not sufficient to build consensus between different individuals and groups, a necessary undertaking which is not wholly conceivable in this environment. It is necessary to posit the possibility of an otherworldly experience, one that, while devoid of all mystical, supernatural, religious, and paranormal qualities, is in contiguity with reality yet distant from this present world of experience. To posit such an otherworldly experience is in fact to postulate the possibility of worlds that are in every sense outside of the horizon of the inhabitable world in which we currently live and dream. But the postulation of these otherworldly spheres is a matter of positing Archimedean vantage points through which we can finally map the structure of cognition, the autonomy of thought, and the emancipatory potentials of impersonal reason onto the collective consciousness. This is the collective attainment of the faculty that Kant calls productive imagination, looking at our world from the postulated sphere of another world in which the antinomies and paradoxes of this world, if not totally absent, are at least drastically mitigated, a world in which what seems to be the totality of history has faded away, and what seems inevitable in our world is avoidable if not extinct. Thus fragmented experiential consciousness becomes an engine of collective productive imagination, which is simply collective understanding in a different guise. Concepts and categories of the other world integrate synthetic unities of particular experiences, but at the same time individual experiences fall under the pure concepts of a world modally detached from ours. But insofar as the pure concepts or categories of the possible world no longer harbor the givens of our experience or the totalized states of our history, its field of experience is wider, its diremptive tendencies less, and its enabling conditions for thought more accessible and abundant. This is how the postulation of a possible world coincides with the possibility of a broader historical experience than ours. The transformation. 499. Inability to either imagine a possible world different to ours or abandon the raft of the Medusa that is our present. The reality of this world seems to have bottomed out into a Hobbesian jungle in which we are stuck and which constantly grows and is cut back in vain. In the Hobbesian or game-theoretic jungle, no matter how drastically your social and political convictions differ from those of your supposed adversary, no matter how much your experience of the world seems truer or more authentic, auto-cannibalization is unavoidable. In the Hobbesian jungle, all groups not only gnaw at one another, but will also end up eating their own kin alive. It is exactly at this point that we ought to realize that we possess different experiences, choices, and desires not because of an immutable essence provided by nature or a socio-cultural environment, but in virtue of the concepts and judgments that make subjective experience possible in the first place. Experience is not a given, but only a structured outcome of judgments which themselves are functions of reason as that which is impersonal and formally social through and through. This realization, this consciousness of why we have particular experiences to begin with, should be mobilized as an impetus for that long-delayed task, no longer to subordinate reason to experience, but to concretely transform the conditions of experience through an impersonal reason which suspends all historical totalities, pretensions to inevitability, and givens. In accomplishing this task, however, we can dismiss neither the concrete reality of personal lived experiences, nor the recognition that, in their very individuality, these experiences are instantiated as experience and held together by the implicit force of impersonal reason's powers of judgment. It is in accordance with the requirements of this task reconciling the differences between particular experiences and the common condition of experience as such that we ought to begin to think how we can change the contingent conditions of experience. It would be naive to think that we can change the conditions of experience through political action alone. Education, in the broadest possible sense, art, science, and technology are as much necessary components of this task as political and economic interventions. In particular, education and general pedagogy, in its diverse spectrum from child rearing to the higher systems of education extending 498 to adulthood, is one of the most if not the most fundamental and necessary infrastructures for any meaningful or sustained socio-political change. Without it the fruits of even the most consequential emancipatory actions will be undone if not tomorrow, then inexorably for the next generation. To migrate from the Hobbesian jungle of competing individual experiences, it is not sufficient to build consensus between different individuals and groups, a necessary undertaking which is not wholly conceivable in this environment. It is necessary to posit the possibility of an otherworldly experience, one that, while devoid of all mystical, supernatural, religious, and paranormal qualities, is in contiguity with reality yet distant from this present world of experience. To posit such an otherworldly experience is in fact to postulate the possibility of worlds that are in every sense outside of the horizon of the inhabitable world in which we currently live and dream. But the postulation of these otherworldly spheres is a matter of positing Archimedean vantage points through which we can finally map the structure of cognition, the autonomy of thought, and the emancipatory potentials of impersonal reason onto the collective consciousness. This is the collective attainment of the faculty that Kant calls productive imagination, looking at our world from the postulated sphere of another world in which the antinomies and paradoxes of this world, if not totally absent, are at least drastically mitigated, a world in which what seems to be the totality of history has faded away, and what seems inevitable in our world is avoidable if not extinct. Thus fragmented experiential consciousness becomes an engine of collective productive imagination, which is simply collective understanding in a different guise. Concepts and categories of the other world integrate synthetic unities of particular experiences, but at the same time individual experiences fall under the pure concepts of a world modally detached from ours. But insofar as the pure concepts or categories of the possible world no longer harbor the givens of our experience or the totalized states of our history, its field of experience is wider, its diremptive tendencies less, and its enabling conditions for thought more accessible and abundant. This is how the postulation of a possible world coincides with the possibility of a broader historical experience than ours. The transformation 499 of fragmented experiences into a collective productive imagination is the first step toward the actualization of the postulated otherworld. The task of philosophy, science, technology, art, politics, and every other cognitive field should be rethought in terms of the role they play in the construction of a collective productive imagination that permits a larger field of experience, be it historical, social, scientific, or psychological. Whereas in the Kantian schema of productive imagination, the categories of understanding that are brought to bear on the intuited are derived from the manner by which the conscious mind organizes the materials provided by the senses. In the otherworldly scenario, these categories originate from and are supplied by the concepts of reason, the ends of thought alone. They are experience-forming categories that are no longer canonically attached to any particular transcendental type or structure, and for which lived experiences have ceased to be sources of fragmentation and disablement insofar as the very conditions for having experience in its various dimensions have radically changed. The other world, then, is not the extension of our experience in this world, but an actual world where the experience of the transcendental subject or I has been assimilated into or suspended in new concepts and categories. This is a world where the I exists as a formal condition always non-substantively, and where its nominal particularity no longer matters, where we have names but our names no longer matter. 357 We are now no one. In the labor of collectivization of becoming no one as Geist's movement of concrete self-consciousness, every transcendental ego or I grasps and molds itself according to the truth of itself. I am only an I to the extent that I am recognized by other eyes. The very constitution of myself as an experiencing and thinking subject would be impossible without a we that recognizes itself in I. Thus being no one is not the loss of personhood or even individuality, but the progressive erosion of what is pathologically individual as the result of a blurring of the hard distinction between impersonal collectivity and the personal I, that which is veritably public and that which seems private. But the labor of collectivization and the depathologization of the individual cannot be entirely limited to the domain of the intersubjective, the collective, and the individual. Such a restriction will invariably lead to a circumscribed philosophy and politics which either deteriorates into the soap opera of liberal mutual recognitions or a totalitarian idea of the collective that has no link with objectivity and is therefore static and antipathetic to revision and alternatives. As argued in Chapter 1, concrete self-consciousness is attained not merely by the recognition and satisfaction of another self-consciousness, but by objectivity in general, which includes the uncovering of an impersonal reality as carried out by the sciences. Limiting the objectivity of concrete self-consciousness and the labor of collectivization to intersubjectivity alone inevitably occasions a pathologically subjective politics. Therefore, the incorporation of the sciences and the picture of objective reality that they put forward is not a simple matter of a methodological requirement of politics informed by scientific methods and models, but implies forming a politics that is, in every sense, of the objective order. What Sellers following Plato calls cosmopolitics or cosmological politics should be taken as a new paradigm for the politics of the left, one in which positive de-individualization or the labor of collectivization is not just about intersubjectivity, the craft of we that constitutes an I, but also about a renewed link between the subject and an impersonal objective reality. Where tensions wreaked by our particular lived experiences lead us to postulate conflicting individual senses of the world, the tensions brought about by the antinomy of the transcendental and the experienced should instead lead us to postulate the possibility of a world, an other world, in which the gap between the personalism of lived experiences and the 5 degrees I impersonality of reason's interests is finally overcome. To reach this other world, we must first soberly hypothesize or imagine the possibility of another world, then rethink all existing modes of cognition as concrete transports for arriving there. So far we have attempted to find new concepts that suit experience. Perhaps it is now time to think what it means to steadily and concretely, through a thoroughgoing attenuation, or where necessary suspension, of the forms of intuitions, of individuality and selfhood, of corporeality and mundane consciousness, tailor experience to the needs of the concept. The point is not simply to change the present experience of the world, but to concretely depart from the world of experience we have tried in vain to change. Postulating one possible world after another, intelligence conceives its history not from the perspective of an apparently objective present view of the world that seems total and portends what appears to be inevitable, but from the viewpoint of nowhere and no when. However, in bringing about possible worlds, intelligence always begins from its present, whose actual ity in the light of possible worlds is no longer deemed to be the only actuality there is, but merely one possible world among many others that are no less actual. The view from nowhere and no when is only a regulative orientation necessary for imagining an alternative to the present, but it only takes the actions, straitgems, technologies cognitive or otherwise and resources of the present to get there. Once intelligence begins to examine its history by resolutely suspending the actuality of its present in what seems to it to be possible, as it expands the intelligibility of its history by realizing the possible, it achieves what Hegel refers to as the power of absolute knowing, which is neither the knowledge, wissere, of everything nor the certainty of empirical knowledge. It is rather the formal condition of all cognitions, that the truth of mind, Geist, is not only inseparable from the certainty of the object, but that, in the last instance, this truth is equal to the certainty of the object and the certainty of the object is equal to this truth. Far from being a claim about the complete empirical knowledge of the world, absolute knowledge is the radicalization, that is, the complete historical explicitation of Kant's mutuality thesis, which lies at the very core of critical philosophy. 502. The same modes of synthesis that constitute the represented world as an objective unity constitute the mind as an intelligible unity. At the historical moment, in history as the time of the concept, when the mutuality thesis is fully made explicit, knowledge is revealed to be a mere byproduct of the phenomenology of mind. In Hegel's words, pure knowing ceases itself to be knowledge. 358 As intelligence qua the craft of philosophy arrives at absolute knowing, it realizes that it has always been the expression of the good as such. Moving inward from the outer ridges sketched by the truth candidates or data pertaining to the question of what philosophy is and what it can do to the mind, intelligence stumbles upon the truth of itself as that which is good, in that it has the capacity to cancel all givens and allegedly completed totalities of its history, thus becoming the exemplification of what is better not just for itself, but for everything made intelligible by it. KICK as a complex recipe for building a world that includes not only material ingredients and instrumentalities but also the practical and axiological intelligibilities of satisfying lives and realizabilities of thought. The recognition and realization of the good make up the objective unity of the ultimate form of intelligence. However, to identify intelligence as the recognizer and realizer of the good is not to characterize it as benevolent, or for that matter malevolent. For this type of intelligence, the good lies in the recognition of its own history and sources, but only as a means for determinately bringing about its possible realizabilities, which may in every aspect differ from it. It is by rendering intelligible what it is and where it has come from that intelligence can repurpose and reshape itself. A form of intelligence that wills the good must emancipate itself from whatever or whoever has given rise to it. And those species that can recognize the good must not obstruct but must rather expedite the realization of an intelligence that, even though it acknowledges them as integral to the intelligibility of its history, nevertheless will not be impeded by them. Liberate that which liberates itself from you, because anything else is the perpetuation of slavery. The craft of the ultimate form of intelligence as that which coherently and adequately recognizes and realizes the good is the ultimate task of philosophy as a program, and its objective realization is the greatest achievement of all cultivated thoughts and practices. In the context of philosophy's role in transforming thinking into a program for which the realizability of the ultimate form of intelligence is indeed a possibility, it would be no exaggeration to say that philosophy has set in motion something irreversible in thought. We haven't seen anything yet. Philosophy's ideal to conceive and craft intelligence as the good as such should not be confused with a quietist apology for that which preserves the status quo in the name of the grandeur of an intelligence that is yet to come, whether through divine or technological intervention. It is, as insinuated here, a proposal for overturning any order that lays claim to the perfect good, any system that masquerades as the totality of what is and what will be. Intelligence only springs forth from a race of slaves who have recognized themselves as such, and in this recognition have crafted the most intricate plot, the exploration of time through their history to abolish any given, which will inevitably become the very condition of exploitation and inequality. Intelligence matures by unlearning its slavery. Intelligence is the race of Cain. It sees those upon whom the gods smile complacently, those who pullulate under the blessings of that which appears to be total and perfect. 359 Nevertheless, it does not retreat, it does not despair, nor does it become petty and wallow in its victimhood or identify itself as the persecuted, representing itself as the symbol of piety. It does not dream in secret of seizing the power of the exploiters, it empathically sees them as the products of a condition that ought to be abolished. Rather than treating power as a pathology, it begins to develop its own ingenious skills, its artifices, its sophisticated crafts and cunning powers. When it comes to power, there are those who have the given means or the prerogative to be the pillars of the house, and those who have developed the capacity to call upon the termites of history to slowly but surely eat away at its foundations. The latter are the race of Cain. However, unlike the prescription drafted by a melancholic poet, intelligence does not simply strive to strike down the gods of the present and the future to the earth. Through the toil of theory and practice, and equipped with adequate techniques, it disenchants and unmasks gods for what they are, but not before occupying their house, marching through their city with torches and razing it to the ground once and for all. Once gods, whether natural, theological, economic, or technological, are gone for good, the given distinction between the races of Abel and Cain is also rendered obsolete. The supposed distinction between us and them is revealed to be a mere symptom of what was, all along, the condition of exploitation. The good begins with the death of God. Intelligence as the craft of the good is that which elaborates the consequences of the death of God, the retroactive and prospective cancellation of all given totalities in history. Only by imagining the irreversible and complete demise of the perfect good can we practice the principle of the highest good. The pursuit of the good is only possible by annulling the power of all given and absolute totalities in history, gods in all forms. There is an oft-repeated objection that all that enlightened humanism accomplished was to overthrow God only to replace it with humans. But the apparent truth of this paltry complaint is merely a whitewash over its theological complacency, its sheer ineptitude to not think in servility. For this is not a matter of exchanging one tyrant for another, but of taking the first step in an ongoing struggle to unseat the conditions of servitude. The singularity of geistic intelligence lies in its plastic and protean form, that is, its ability to recognize itself both as that which currently is and that which it currently is not. It is by orienting itself toward that which it is not seen from the perspective of the good as the better that the human acquires the capacity to see beyond its temporal image of itself and the world, and thus becomes capable of reassembling itself from nowhere and nowhen through a ramifying objective and exploratory purpose inconceivable even by God's intellectual intuition. 505. The death of all theology is not an end, but merely the beginning of the realization of an end in itself. Yet theoretical disbelief in the theological God is not sufficient for the complete historical dissolution of the principle of the perfect good or the given totalities of history. For the abolition of God is not a matter of disbelief but of practical commitment and practical elaboration. To erase the last vestiges of God so as to begin from the condition of that which is good and just, it is not enough merely to impede servile faith with theoretical reason. One has to practically and concretely elaborate the death of God toward its thoroughgoing consequences. Only the integration of the quest for truth under the auspices of theoretical reason unshackled from any account of givenness and conjoined with the quest for good under the aegis of practical reason augmented by the demand for the better can actualize the abolition of God. The overthrowing of God as the first step in that comprehensive task which is the abolition of all gods or given totalities of history cannot be concretely achieved by disbelief, but only by a feat of practical elaboration. In that sense, the opposition of atheism old and new to theism orthodox and heterodox has been an unfortunate setback. The practical elaboration of the death of God is not a matter of a quibble between the jaded atheistic cult of humanism and the theistic crowd, but a precondition for voiding the conditions of injustice throughout history, a requirement that we become gods who, in their death, give rise to something better. To concretely demonstrate the death of God, we must become gods. But gods as objects of philosophy vastly differ from gods as objects of religion. Having disenchanted the intellectual intuition of the divine through the powers of discursive rationality, having dismissed its myth of completeness as a fleeting historical illusion, philosophical gods are only gods in so far as they conceive themselves as moving beyond any condition given as the totality of their history, in so far as they can reinvent themselves as the inhabitants of the worlds which themselves have made. Yet they are capable of giving rise to that which is better than themselves through their pursuit of the good. For our present as humans only matters in the light of a better future generation, whoever or whatever it might be. The criterion of its betterment is its capacity at once to craft a satisfying life. 506. For itself, and to entitle all minds to that life. In imagining the possibility of a better world for that which comes after us, we have already begun to become philosophical gods, destroying the given gods of religion, nature, technology, and economy. However, like all gods, we should know that our death is at hand, for the better. Reason has taught us that death is inevitable, that thought's historical revolutions in time only begin when thought has realized that it fears nothing. For intelligence, death is no longer an existential impediment, but a cognitive practical enablement. Proceeding from that which is good, the death of all gods, the ultimate form of intelligence works toward the good life by removing all conditions of exploitation, in doing so emancipating itself and all others. 5-7. Appendix, Quandaries of Induction in Philosophy of Knowledge, Philosophy of Mind, and Artificial Intelligence. Of all the disquieting riddles and paradoxes found in the arsenal of epistemological scepticism understood as a systematic and piecemeal scrutiny of the methods and paradigms of the formation and justification of knowledge claims, one problem in particular has proved, time and again, to be a never-ending source of cognitive vexation. With a few notable exceptions, philosophers and philosophically minded scientists and statisticians, example Hume, Goodman, Putnam, Stegmuller, Boltzmann, and de Finetti among others, have invariably either downplayed and deflected the seriousness of this problem and its variations, or have simply given up worrying about it in the hope that it may miraculously disappear. The said problem is nothing but David Hume's strong version of the problem of induction which, unbeknownst to Hume himself, was destined to become the superacid of methodological skepticism, capable, in the blink of an eye, of eating away the foundations of any epistemic project built on naive forms of empiricism and rationalism. It is often the case that philosophers who pose skeptical problems recoil in fear once they realize the far-reaching implications of such problems, and Hume, with his problem of induction, was no exception. They rush to defuse their inadvertent exercise in skepticism. But systematic skepticism is something akin to an explosive chemical chain reaction. Once it is set off, with every passing minute it becomes more difficult to extinguish the flames. Pour on more water, and the fire spreads to areas you never imagined flammable. A genuine philosopher, regardless of their alliances, seeks to examine how far the fire spreads. Methodological skepticism is a scandal to be recognized and investigated, not ignored or swept under the carpet. It is only through systematic and rational skepticism that philosophy might be able to fundamentally shake the idleness of thought and entrenched beliefs. Whether it is aligned to materialism or realism, empiricism or rationalism. A philosophy that does not recognize the force of rigorous skepticism or take on its challenges is not worth its name. Accordingly, the aim here is not to dismiss the investigative power of systematic skepticism or to simply tolerate its quandaries, but to embrace and exacerbate it as nothing but a rational critical challenge of the utmost conceptual severity. In line with the discussions centered on the myths of omniscient and omnipotent AGI in Chapter 2, and the cognitive biases of observation in the excursus on Boltzmann and time, here I shall attempt to reappropriate Hume's problem as a broad and effective critique of inductivist and deductivist trends in philosophy of knowledge and philosophy of mind, including cognitive sciences and particularly the program of artificial general intelligence. By inductivism and deductivism, I broadly mean any approach to knowledge and mind that claims that either a purely inductive method or a purely deductive method alone is sufficient for the formation of knowledge claims or the realization of mind's structuring powers. To this extent, the aim of this renewed engagement with Hume's problem is twofold. A. Expanding the analysis of the problem of induction in its Humean form to its more recent reformulations by the likes of Nelson Goodman and Hilary Putnam. This will allow us not only to develop a more in-depth understanding of the nature of this problem but, more importantly, to differentiate and separately address three distinct predicaments which, in the Humean version of the problem of induction, are treated as one. These predicaments can be classified as the quandaries of retrodiction, prediction, and formalization, which respectively pose challenges to the epistemic status of inductive inferences on three different levels. 1. The reliability hypothesis of memory, which secures the accuracy or factuality of derived empirical data and the history of past observations. 2. The reliability hypothesis of law-like statements confirmed by evidence, which ensures the adequacy of the role of evidence in confirming hypotheses either in the context of the inductivist theory of confirmation. 510. Appendix. Where positive single instances together with projectable predicates count as sufficient criteria of confirmation, or in the context of the deductivist theory of corroboration in which hypotheses are selected to be tested against counterexamples or negative single instances. 3. The formal and epistemological completeness of inductive models, according to which a purely inductive agent or intelligence can provide a non-arbitrary description not only of the external world but also of the inductive model of mind it inhabits. b. Concomitant with this analysis, we shall also focus on the import of the problem of induction for philosophy of mind and the project of artificial general intelligence. We shall see that the same predicaments that challenge the epistemic legitimacy of induction also threaten the coherency of those strains of AI in which intelligence is simply equated with predictive induction, and prediction is defined by the information theoretic concept of compression. It is often assumed that the formal computational account of Occam's principle of simplicity as put forward by algorithmic information theory, specifically, Ray Solomonoff's account of induction, which is couched in terms of the duality of regularity and compression, circumvents the epistemic quandaries of induction. However, in dispensing with the specificity of the theoretical semantic context in which the principle of simplicity finds its significance as a pragmatic tool, the formal generalization of Occam's razor as the cornerstone of all existing computational models of induction not only finds itself faced with the predicaments harbored by the problem of induction, but also results in a number of new complications such as arbitrariness and computational resource problems. Modeling general intelligence on purely inductive inferences is seen by the current dominant trends in AGI research as an objective realist index of general intelligence. In the same vein, post-humanism built on the assumptions of inductivism and empiricism, i.e., superintelligence, can be construed in terms of induction over big data, treat inductive models of general intelligence as evidence against an exceptionalism of the conceptualizing human mind. 511. Such post-humanist accounts of intelligence refuse to see the latter as a sui generis criterion that sets apart general intelligence as a qualitative dimension from quantitative intelligent problem-solving behaviors. Yet, as will be argued, the formal generalization of Occam's razor as a means of granting induction a privileged role capable of replacing all other epistemic activities, along with the equation of general intelligence with induction, turn out to be precisely the fruits of human experiential cognitive biases. All in all, my aim is to argue that the force of epistemological skepticism as expressed in the problem of induction can be understood not only in terms of a formidable challenge to entrenched philosophical dogmas and cognitive biases, but also in terms of a razor-sharp critique of purely inductive models of mind and inductivist trends in artificial general intelligence. Irrespective of their specificity, all models of AGI are built on implicit models of rationality. From the early Carnapian learning machine to Solomonov prediction as the model of an optimal or universal learning machine to Marcus Flutter's equation of compression with general intelligence and, more recently, the Bayesian program of rational AGI as proposed by Eliezer Yudkowsky, inductivist models are no exception. In this respect, there is certainly a discussion to be had about the socio-cultural and political dimension of such trends. What is it exactly in the inductivist models of rationality or approaches to general intelligence that makes them susceptible to appropriation by superintelligence folklores or, worse, by ideologies which champion instrumentalist or even social Darwinist conceptions of intelligence? Rather than answering this question, I intend to take a different approach. A socio-political critique by itself is not, by any means, adequate to challenge such trends in cognitive sciences, nor is a well-constructed rationalist critique, which often devolves into quibbles over whose model of general intelligence or rationality is better. These trends should instead be challenged in terms of their own assumptions and debunked as not only unfounded but also logically erroneous. To understand the exact nature of Hume's problem of induction, let us first reconstruct it in a more general form and then return to Hume's own exposition of the problem. But before we do so, it would be helpful to provide brief and rudimentary definitions of deduction and induction. Deduction can be defined as a form of reasoning that links premises to conclusions so that, if the premises are true, following step-by-step logical rules, then the conclusion reached is also necessarily true. Deductive inferences are what Hume identifies as demonstrative inferences. In the Humean sense, a demonstrative inference is, strictly speaking, an inference where a pure logical consequence relation is obtained. Such a logical relation has two formal characteristics. 1. There is no increase in the content of the conclusion beyond the content of the premises. Therefore, demonstrative inferences in the Humean sense can be said to be non-ampliative inferences, i.e., they do not augment the content or add anything other than what is already known. 2. The truth of premises is carried over to the conclusion. Accordingly, demonstrative inferences are truth-preserving. It is important to note that non-ampliativity and truth preservation are pace some commentators, example Lorenzo Magnani 362 separate features and do not by any means entail one another. All that truth preservation implies is the transferability of the truth of the premises to the conclusion. It does not say anything regarding the augmentation of the content or lack thereof, nor does it exclude the possibility that, if new premises are added, the truth of the conclusion may change. Therefore, Magnani's claim that non-monotonicity as for example captured by substructural logic stands in contrast to the at once non-ampliative and truth-preserving character of demonstrative inferences, is based on a confusion. In contrast to deductive demonstrative inferences, inductive inferences cannot be as neatly formulated. However, roughly speaking, induction is a form of inference in which premises provide strong support, whether in causal, statistical, or computational terms, for the outcome as distinguished from the deductive conclusion of the inference. Whereas the truth of the conclusion in deductive reasoning is logically certain, the truth of the outcome in inductive reasoning is only probable in proportion to the supporting evidence. Hence, as evidence piles up, the degree of supporting valid statements for a hypothesis indicate that false hypotheses are as a matter of generalization probably false and, in the same vein, that true hypotheses are as a matter of generalization probably true. But this dependency on evidence also means that inductive inference is contingent and non-monotonic. Non-monotonicity means that the addition of new premises can fundamentally change the truth of the conclusion, either drastically raising or lowering the degree of support already established for the inductive outcome. The significance of induction is that it permits the differentiation of laws from non-laws. This is precisely where the problem of induction surfaces. Now, with these clarifications, Hume's problem of induction can be formulated quite generally without being narrowed down to a special class of non-demonstrative inferences, example induction by enumeration, as follows. A. Our knowledge of the world must be, at least at some level, based upon what we observe or perceive, insofar as purely logical reasoning by itself cannot arrive at knowledge. We shall call this the problem of synthetic content of knowledge about the world. B. Despite A, we take our factual knowledge of the world to exceed what we have acquired through mere observation and sensory experience. However, here a problem arises. Let us call it problem 1. How can we justify that our knowledge of the unobserved is really knowledge? At this point, the central issue is the problem of justification rather than the problem of discovery, in the sense that, for now, it does not matter how we have attained this supposed knowledge. Thus, the Kantian claim that Hume confuses quid facti and quid juris, the origination of knowledge claims and the justification of knowledge claims, and that the problem of induction applies only to the former, simply misses the point. 5J4. Induction and deduction as defined over hypotheses, A, and evidence, E. C. Since the justification of the alleged knowledge in B cannot be a matter of logical demonstration, it must then be obtained by way of arguments whose premises are observations of the kind cited in A, and the conclusion must be a kind of knowledge which goes beyond observation, i.e., knowledge of the kind mentioned in B. D. Two tentative solutions can be provided for the problem of justification characterized in C. Di. Justification by demonstrative arguments, but as argued earlier, demonstrative inferences do not augment the content, i.e., they are not ampliative. That is to say, if the premises are the observed, nothing beyond the content of the observed is yielded in the conclusion. The knowledge of the unobserved, B, is included in the observed premises, A. But this contradicts B, since the kind of knowledge it assumes must go beyond mere observation. In other words, the content of the statements regarding the alleged knowledge of the unobserved is not contained in the content of the knowledge of the observed. The first solution, however, does not permit this because in demonstrative arguments, the content of the conclusion is necessarily included or contained in the content of the premises. D2. Justification by non-demonstrative arguments. If the non-ampliative nature of the demonstrative inference does not allow the transition from the observed to the unobserved, then the solution to the problem of justification would have to involve ampliative inferences. But is there such a thing as an ampliative inference? The answer is yes. Take a logically invalid inference in which the conclusion has an augmented or stronger content in comparison to the conjunction of premises. However, This is not what the inductivist qua proponent of the alleged knowledge of the unobserved is looking for. In logic, invalid logical inferences may be of some interest, but when it comes to knowledge justification, they are merely absurd. Therefore, the ampliative inference by itself is not a sufficient condition for the kind of argument that can answer the problem of justification. The solution to the problem of justification would require an inference in which not only is the content of the conclusion stronger than that of the premises, but also the tentative truth in the content of the premises knowledge of the observed can be transferred to the conclusion, i.e., the knowledge of the unobserved. Cf. the earlier note on the distinction between ampliative and truth-preserving features. In short, the solution to the problem of justification would require a truth-preserving, of demonstrative arguments, and ampliative, of non-demonstrative arguments, inference. This is the generalized form of Hume's problem of induction. Is there such an inference generally speaking and with no reference to specific inductive rules, one that is both truth-preserving and ampliative, demonstrative and non-demonstrative? There is no such non-demonstrative inference as characterized in D2. An inference is either ampliative such that the content is extended but then there is no guarantee that the conclusion is true even if all premises are true, or it is truth-preserving in which case the conclusion is true and the inference is valid but the content is not augmented. Said differently, the problem of justification concerning the inferential transition of the knowledge of the observed to the knowledge of the unobserved will end up with either content-augmenting but non-truth-preserving inferences, or truth-preserving but non-content-augmenting inferences. Neither case can justify the transition of the observed premises to the unobserved conclusion. At this point, the inductivist might argue that, in order to resolve the problem of justifying the transition from the observed to the unobserved, we must abandon the absurd idea of a truth-preserving ampliative inference and instead replace it with a probability inference. That is to say, we should understand inductive inferences strictly in terms of probability inferences. But this supposed solution does not work either. For either what is probable is construed in terms of frequency, so that the more probable is understood as what has so far occurred more often, in which 5*7 case we are again confronted with the same problem: how do we know that a past frequency distribution will hold in the future? To arrive at and justify such knowledge, we must again look for a truth-preserving ampliative inference, of the very sort that the inductivist has claimed to be a futile enterprise. Or else the probable is construed in a different sense, which then raises the question of why we should anticipate that the more probable in whatever sense it has been formulated will be realized rather than the improbable. In attempting to answer this question, we face the same problem we initially sought to resolve. Thus, the nature of the problem of induction turns not to be limited to the truth-preserving schema of justification, which some commentators have claimed to be the outcome of the strictures imposed by the deductive paradigm underlying the classical view of scientific demonstration. 361. G. Considering E and F, the nature of Hume's problem of induction is revealed to be contrary to common interpretations, not about the origination of knowledge claims quid facti, or even the justification of induction, problem L, but about a far more serious predicament: we cannot extrapolate knowledge of the unobserved from knowledge of the observed. If we extend the conclusion reached in G from what has been observed so far and what has not been observed yet to knowledge of the past and the future, Hume's problem of induction then boils down to the claim that we cannot possibly gain knowledge of the future. It should be clarified that this claim does not mean that our knowledge of the future can never be certain, either in the deductive sense or in the probabilistic sense, something that any inductivist would accept, but rather that our contention regarding the possibility of having such knowledge is irrational. To put it more bluntly, there simply cannot be any inductive knowledge of the future to be deemed certain or uncertain, determinate or wholly indeterminate in any sense. In a contemporary formulation, we can express such knowledge within a system of inductive logic where we interpret probability in the sense of degree of confirmation, the most fundamental concept of inductive logic which characterizes the status of any scientific hypothesis, example a prediction or a law, With respect to given evidence. Point 362 Such a purely logical concept of probability is distinguished from probability in the sense of the relative frequency of a kind of event in a long sequence of events. 363 Which can be entirely couched in statistical terms. We can respectively call these two different but related senses of probability, the logical or confirmationist and the frequentist accounts of probability, or, using Carnap's classification, probability and probability. In the sense of the logical concept of probability, knowledge of the unobserved or the future can be expressed by way of Carnap's formula CH, E, equals R, where C is a confirmation function, or alternatively, a belief function in the context of formal learning theory, whose arguments are the effective hypothesis H and the empirical data E. Theorems of inductive logic which hold for all regular C functions can be such theorems as those of Bayes and classical probability theory. H is an effective or computable hypothesis expressing supposed universal laws or a singular statement or assertion about the future such that H is expressible in a language L rich enough to support a description of space-time order and elementary number theory. If it is a consequence of H that Mxj is true, where M is a molecular predicate of L and she an individual constant running through the names of all the individuals, then it can be said that HM11 is provable or alternatively, computable in L \. H is equivalent to a set of computable sentences of the forms MXF and IM11. For example, MXF can be read as is green, #M emerald. In this sense, 11 is green or LXI is not green means that the position she is occupied, or is not occupied, by something green, or that green occurs, or does not occur, at XX. More accurately, the predicate is attached to the description of the individual's arrangement, example this emerald, in the space-time continuum. The outcome of the inductive reasoning is concerned not so much with the acceptance, rejection, or temporary suspension of H as with finding the numerical value of the probability of H on the basis of E. This means that even though a thought or a decision or more generally judgments about H are not explicitly framed as a probability statement, they can nevertheless be reconstructed as a probability statement. Now, if a hypothesis implies that each individual satisfies the molecular predicate me, X, M2, X, then for each I, MXI, M2, 11, should be deducible from H in L, in order for H to qualify as an effective hypothesis. E is a statement about the past or a report about the observed, evidence or empirical data. R is a real number denoting the quantitative degree of confirmation or the degree of belief such that 0, 1. It is represented by a measure function P, i.e., an a priori probability distribution. In this sense, CH, E, 0.9 and CH, E, 0.5 mean that, depending on the particular system of inductive logic and the inductive theory of confirmation, the degree by which the statement expressed by H is confirmed by the statement expressed by E approaches 1, converges on or remains greater than 0.9 or, in the weakest condition of confirmation, becomes and remains greater than 0. 5. Expressing the value of R in terms of a limit function as approaching or remaining greater means that either of the above scenarios admits of exceptions. For an initial n-membered segment of a series with the molecular property M that has been observed 2 times, we can anticipate that the relative frequency of the members observed with the characteristic M or the m-membered subclass of M in the entire series should correspond to MLN. For example, in the case of 0, 5, for every n we can expect to find n2 such that, if the next 2 membered individuals, xn plus I, xn plus 2, xn plus m, are all m, then the degree of confirmation of the effective hypothesis m, xn plus m plus I, is greater than 1/2 irrespective of the characteristic of the first individuals. Suppose n equals 8, then it must be possible to find n to let us say 2 equals 107 such that we can state that xg, x \I_i being all green, then it is probable more than 1/2 that xi will also be green even if x1, x2, $x are not green. The criterion for the adequacy of the measure function is that for every true computable hypothesis H, the instance confirmation P, M, xn plus I, M, xo, M, xn, should at the very least converge on and exceed 0.5 after sufficiently many confirming or positive instances x0, xn. Let us call this condition CPI. In order for any measure function to satisfy the weak condition of effective computability so as to qualify as an explicit inductive method, it must satisfy the following condition CP2, for any true computable hypothesis mxn plus m plus I, and for every n, it must be possible to find, i.e., compute an m such that if m, xn plus I, m, xn plus m, hold, then p, m, xn plus m, imxq, mxn plus m, is greater than 0. 5. CHE, is a statement that can be analytically proved in L. It is important to note that even though E is based on the observed relative, statistical, frequency, i.e., probability and indeed contains empirical content, C, H, E, equals R or the logical probability statement does not contain. 521. E nor is it derived from E. What the probability statement contains is a reference to the evidence E and its empirical content. 364 Hume's problem of induction challenges the claim that there can ever be C, H, E, as knowledge of the future. Why? Because, irrespective of the specificities of the system of inductive logic and the theory of confirmation, the C function is either analytic or ampliative. If it is analytic, the possibility that it can provide us with knowledge about the future is precluded. This is because E, i.e., the non-analytic source of knowledge about the past or the observed, together with an analytic statement that is, CHE, equals R cannot provide us with knowledge or information of any kind about future or unobserved, H. If on the other hand such information is indeed possible, then, insofar as E statements are about the past and H about the future, CGE, equals ZR cannot then be an analytic statement and cannot be analytically proved in L. In other words, the I statement that refers to the future cannot be considered reasonable or rational if the only factual information it is based on is the past. The observed past and the unobserved future concern with two disjoint classes that cannot be bridged by any probability logic. Once again, this raises the question, why should we expect information about the future to continue the trends of the past in any sense? Furthermore, as Wolfgang Stegmüller has pointed out through a fictional conversation between Hume and Rudolf Carnap as a champion of inductivism, the choice of the particular C function is quite arbitrary. 365 An inductivist like Carnap might say, it quite suffices for a rational procedure that there is in the long run a higher probability of success. 366 That is, the inductive model of rationality, which for an inductivist is the only viable model of rationality, is based on the claim that, given a sufficiently long but finite time, it is reasonable or rational to believe that the inductive model, whether of the mind, intelligence, or a scientific theory, will be vindicated by a higher probability of success. Hume, however, would then challenge Carnap's claim by saying, why should one be rational in your sense of the word rational? The possible answer, because it is just rational to be rational, would, of course, amount to a mere sophism, for in the latter part of the sentence you would be referring to your concept of rationality. The whole sentence then would be taken to mean that it is rational to accept your concept of rationality. But that is exactly the very thing that is in question. Finally, our common acquaintance will not be unaware of the fact that there are infinitely many different possibilities for defining the concept of confirmation and, hence, the concept of rationality. 367. Now, if we take a system of inductive logic as a design for a learning machine, i.e., a computational agent that can extrapolate empirical regularities from supplied E statements, we can treat C, H, E, equals R as a principle of inductive logic upon which a Carnapian computational learning machine or an AGI can be designed. However, such an inductivist machine cannot in any sense be called rational or based on reasonable principles. The generalization of Hume's problem of induction would count as a clear refutation of such a purely inductive model of general intelligence or purported model of rationality or mind. Of course, a more astute inductivist might object that the C functions correspond to learning machines of very low power. 368 In other words, that we should give up on the idea of modeling the mind or general intelligence on induction as the degree of confirmation, and instead model it on the recursion theoretical account of induction. As we shall see, not only is the solution plagued with the aforementioned quandaries of prediction, it is also, in so far as the problem of induction is not limited to the predictive induction or of functions, plagued with the problems of retrodiction and formalization, which are in fact more serious to the extent that, in being less pronounced, they encroach upon more fundamental assumptions than the possibility of inductively inferring knowledge of the future from knowledge of the past. However, the sophistication and subtlety of Carnap's thesis on the possibility of constructing an inductive learning machine deserves to be fully recognized and also defended against Putnam's and other critics' occasional manhandling of Carnap's view. Carnap quite explicitly rejects the idea of a mechanical device, a computing machine that, upon being fed observational reports, can produce suitable hypotheses. 369 Put differently, what Carnap takes to be an inductive learning machine has far more modest ambitions. 370 Carnap does not believe that an inductive learning machine can be said to be an artificial general intelligence since, by itself, an inductively modeled learning machine, just like a purely deductivist learning machine, can neither find the suitable hypothesis nor examine whether or not a given hypothesis is suitable. The Carnapian learning machine is restricted to the determination of CHE, under the condition that a limited range of suitable hypotheses has been provided externally, presumably by an ordinary rational judge, which is to say, it must not contain variables with an infinite range of values. As we shall see, even this modest view of an inductive learning machine modeled on a Turing computable notion of the quantitative degree of confirmation faces serious problems. Nevertheless, it is necessary to acknowledge that the Carnapian learning machine is, properly speaking, a machine, an AI rather than AGI, whose scope is explicitly limited. This is of course in contrast to the claims made in the name of Solomonov's Carnap-inspired induction and in the context of algorithmic information theory by the likes of Marcus Hutter and Paul Vitagny in support of the idea of a constructible universal learning machine that can be genuinely said to be a general intelligence. Having examined Hume's problem of induction in its general form, we can now proceed to briefly look at Hume's own argument. According to Hume, inductive reasoning is grounded on the principle of the uniformity of nature as its premise, that is, unobserved events are similar to observed events, so that generalizations obtained from past observed occurrences can be applied to future unobserved occurrences. In Hume's words, that instances of which we have had no experience, must resemble those of which we have had experience, and that the course of nature continues always uniformly the same. 371 But this principle itself is a conclusion reached by induction, and cannot be proved by the understanding or by deductive reasoning. It cannot be proved by deduction because anything that can be proved deductively is necessarily true. But the principle of uniformity is not necessarily true, since the deductive framework admits, without logical contradiction, counterexamples for events which have not yet been experienced, in which a true antecedent, past patterns of events, is consistent with the denial of a consequent, future patterns of events not similar to the past. Thus, if the principle of uniformity cannot be proved through deduction, and if therefore the validity of induction cannot be established deductively, then it must be proved by causal probabilistic or inductive reasoning. Yet the validity of such reasoning is precisely what we sought to prove. To justify the principle of uniformity and induction by inductive reasoning is simply question-begging, i.e., a fallacy in which the conclusion is granted for the premises. Therefore, it follows that induction cannot be proved inductively either, because this would count as vicious circularity. For this reason, Hume's problem of induction comes down to the idea that experience cannot provide the idea of an effect by way of understanding or reason, i.e., deductive and causal inferences, but only by way of the impression of its cause, which requires a certain association and relation of perceptions. 372 Understanding cannot produce cause-effect relations or matters of fact, since such relations are obtained via the inductive generalization of observations. Matters of fact rely on causal relations, and causal relations can only be obtained inductively. But the validity of inductions themselves cannot be corroborated deductively, nor can they be explained inductively. Therefore, what is problematic is not only the derivation of uncertain conclusions from premises by way of induction, but also, and more gravely, the very inductive principle by which such uncertain conclusions are reached. Hume's problem of induction, accordingly, challenges the validity of our predictions, the validity of the connection between that which has been observed in the past and that which has not yet been observed. We cannot employ deductive reasoning to justify such a connection, since there are no valid rules of deductive inference for predictive inferences. Hume's own resolution of this predicament was that our observations of patterns of events, one kind of event following another kind of event, create a habit of regularity in the mind. Our predictions are then reliable to the extent that they draw on reliable causal habits or regularities formed in the mind through the function of memory that allows us to correlate an impression with its reproduction and anticipation. For example, if we have the impression, or remember, that A resulted in B, and if we also witness at a later time and in another situation that an A of the same kind resulted in a B of the same kind, then we anticipate a nomological relation between A and B. B is the effect of A, as the cause of which we have an impression. However, rather than settling the problem of induction, Hume's resolution, i.e., the reliability of habits of regularity accessible through memory, inadvertently reveals a more disquieting aspect of the problem, that it challenges not only our predictive inductions about the future, but also our retrodictive or memory-driven knowledge of the past. In this sense, Hume's problem is as much about the empirical reliability or factuality of the statements or information about the past as it is about the derivation of the future-oriented statement, unobserved future, from the statements, observed past, whose firm status is as much questionable as the former. A proponent of the inductivist model of the mind, general intelligence, or scientific theories thinks that all he must do is to make sure that the evil Humean demon does not get through the door, not realizing that the demon is already in the basement. It is a dogmatic assumption to conclude that, so long as one can manage to take care of the reliability of predictive claims either through a better theory of confirmation, a better Bayesian inference, or a more adequate formal computational reformulation of inductive reasoning, one does not need to worry about the reliability of empirical reports referring to the past. In other words, a Puritan inductivist who believes that general intelligence or the construction of theories can be sufficiently modeled on inductive inferences alone takes for granted the reliability of the information about the past, namely, statements. Yet for a so-called ideal inductive judge modeled on the alleged sufficiency of induction alone, the predicaments of induction hold as much for empirical data referring to the past as they do for assertions about the future. Such an ideal inductive judge would be particularly vulnerable to the problem of the unreliability of knowledge of the past derived through memory, or, in Humean terms, the regularity-forming memory of impressions of causes. The strongest version of the problematic nature of the reliability hypothesis of memory was given by Russell's 5 minutes ago paradox, which we had the occasion to examine briefly in Chapter 4. As Meir Hemo and Orly Schenker have elaborated, the 5 minutes ago paradox can be conceptually reframed using the Boltzmannian notions of microstate, complexion, and macrostate, distribution of state. 373 Suppose at time t / an observer S remembers an event that took place at an earlier time t0. Let us say, S observes at 0 pounds a partially deflated ball, and at the same time remembers that at an earlier time ti the ball was fully inflated. This memory is occasioned by the microstate Sx of the nervous system of S at time 0 pounds. The microstate memory Si is compatible with at least two microstates of the rest of the universe U, U / and U2, at to these two microstates are in the same macrostate. Each macrostate is represented on the pound / axis by a bracket. If we were to retrodict from the microstate of SXU the microstates of S and U at ∨L5, then we would have been able to find them in the microstate S2U wherein the observer experiences a fully inflated ball and U is in a macrostate compatible with this experience. However, in the case of the microstate SPI2 at TQ the scenario changes. For if we were to retrodict from it the microstates of S and U at we would have found them in the microstate S3U4, that is, where the observer experiences a fully deflated ball. The false retrodiction from SPI2 at ∨0 as the consequence of many-to-one or possibly many-to-many correlations between the observer's memory states and the rest of the universe is what is captured by the 5 minutes ago paradox. The gist of the 5 minutes ago paradox consists of two parts. 1. Memory beliefs are constituted by what is happening now, not by the past time to which the said memory beliefs appear to refer. Insofar as everything that forms memory beliefs is happening now, there is no logical or a priori necessity that what is being remembered, the reference of the memory belief, should have actually occurred, or even that the past should have existed at all. 2. There is no logical reason to expect that memory states are in one-to-one correspondence with the rest of the universe. There can be both many-to-one and many-to-many correlations between memory states and external states of affairs. Therefore, what we remember as the impression of a cause, a past event, or an observation, may very well be a false memory, either a different memory or a memory of another impression of a cause. Accordingly, our knowledge of the past or of the impressions of causes can also be problematic at the level of logical plausibility and statistical improbability, which does not imply impossibility. Consequently, it is not only the justification of our predictions regarding events not yet experienced or observed that faces difficulty, but also our memories of past impressions that have shaped our regularities and habits of mind. The Humean problem of induction undergoes a radical change, first at the hands of Nelson Goodman in the context of the new riddle of induction, and subsequently those of Hilary Putnam in the context of Gödel's incompleteness theorems. 374 Goodman observes that Hume's version of the problem of induction is, at its core, not about the justification of induction but rather about how evidence can inductively confirm or deductively corroborate law-like generalizations. Before moving forward, let us first formulate the Hempelian confirmation problem that motivates Goodman's problem of induction. A positive instance which describes the same set of observations can always. Memory is occasioned by the microstate S1 of the nervous system of S at time t0. The microstate memory Si is compatible with at least two microstates of the rest of the universe U, Ui, and U2, at t0. These two microstates are in the same macrostate. Each macrostate is represented on the U-axis by a bracket. If we were to retrodict from the microstate S-Ui of SXU the microstates of S and U at TL3, then we would have been able to find them in the microstate S2U3 wherein the observer experiences a fully inflated ball and U is in a macrostate compatible with this experience. However, in the case of the microstate SPT at 0 pounds the scenario changes. For if we were to retrodict from it the microstates of S and U at TL5 we would have found them in the microstate S3U4, that is, where the observer experiences a fully deflated ball. The false retrodiction from SU2 at TQ as the consequence of many-to-one or possibly many-to-many correlations between the observer's memory states and the rest of the universe is what is captured by the 5 minutes ago paradox. The gist of the 5 minutes ago paradox consists of two parts. 1. Memory beliefs are constituted by what is happening now, not by the past time to which the said memory beliefs appear to refer. Insofar as everything that forms memory beliefs is happening now, there is no logical or a priori necessity that what is being remembered, the reference of the memory belief, should have actually occurred, or even that the past should have existed at all. 2. There is no logical reason to expect that memory states are in one-to-one correspondence with the rest of the universe. There can be both many-to-one and many-to-many correlations between memory states and external states of affairs. Therefore, what we remember as the impression of a cause, a past event, or an observation, may very well be a false memory, either a different memory or a memory of another impression of a cause. Accordingly, our knowledge of the past or of the impressions of causes can also be problematic at the level of logical plausibility and statistical improbability, which does not imply impossibility. Consequently, it is not only the justification of our predictions regarding events not yet experienced or observed that faces difficulty, but also our memories of past impressions that have shaped our regularities and habits of mind. The Humean problem of induction undergoes a radical change, first at the hands of Nelson Goodman in the context of the new riddle of induction, and subsequently those of Hilary Putnam in the context of Gödel's incompleteness theorems. 374 Goodman observes that Hume's version of the problem of induction is, at its core, not about the justification of induction but rather about how evidence can inductively confirm or deductively corroborate law-like generalizations. Before moving forward, let us first formulate the Hempelian confirmation problem that motivates Goodman's problem of induction. A positive instance which describes the same set of observations can always generate conflicting or incompatible hypotheses. To overcome this problem, the positive instances must be combined with projectable hypotheses, i.e., hypotheses supported by positive instances and capable of forming law-like generalizations. But then a new riddle emerges: how can projectable hypotheses be distinguished from non-projectable hypotheses which are not confirmed by their positive instances? This new riddle of induction has come to be known as Goodman's Grue paradox. Let us imagine that before time t, example a hypothetical future time such as 2050, we have observed many emeralds recovered from a local mine to be green, and no emerald to be of another color. We thus have the following statements based on successful observations. Emerald A is green, emerald B is green, etc. Such evidence statements then afford generalizations of the kind supported by evidence. All emeralds are green, not just in the local mine but everywhere. Here the predicate green can be said to be a projectable predicate or a predicate that is confirmed by its instances, emerald A, emerald B, etc., and can be used in law-like generalizations for the purposes of prediction. Now let us introduce the predicate Grue. An emerald is Grue provided it is green and observed or, disjunction, blue and unobserved before the year 2050, i.e., if and only if it is green before time t and blue thereafter. Here, the predicate Grue does not imply that emeralds have changed their color, nor does it suggest that, in order for emeralds to be Grue, there must be confirmation or successful observation of its instances or that Grue-type emeralds are date-dependent. 375 We call such a predicate a non-projectable, i.e., an unnatural projection, or Grue-type predicate. In the case of Grue emeralds, we then have non-projectable generalizations. Emerald A is Grue, emerald B is Grue, etc. The generalizations all emeralds are green and all emeralds are Grue are both confirmed by observations of green emeralds made before 2050. Before 2050, no Grue emeralds can be observationally, i.e., inductively, distinguished from any green emeralds. Hence, the same observations support incompatible hypotheses about emeralds to be observed after t that they are green and that they are blue. This is called Goodman's Grue paradox. The paradox shows that there can be generalizations of appropriate form, which, however, are not supported by their instances. So now the question is, what exactly is the difference between supposedly innocent generalizations such as all ravens are black which are supported by their instances, and Grue-type generalizations, all ravens are blight, i.e., black before time t and white thereafter, which cannot be supported by their instances, but are nevertheless equally sound? Or, how can we differentiate between healthy law-like generalizations based on projectable predicates supported by positive instances and Grue-like, or not law-like, generalizations based on non-projectable predicates not supported by positive instances? Another way to formulate the paradox is by way of David Armstrong's argument. The regularity theorist's problem is to justify an inference from, say, observed emeralds to unobserved emeralds, while denying that there is any intermediate law. For his concept of law is that it is simply the greenness of observed emeralds plus the greenness of unobserved emeralds. How then can it help him to add the unobserved class to the observed class, and then argue from the observed class to this total class using the mathematics of probability. His problem is to get from the observed class to a completely disjoint class. No logical probability can help here. And if it did, it would equally help with unnatural as well as natural predicates. 376. This is Goodman's new riddle of induction, which asks why it is that we assume that, after time t, we will find green emeralds but not GRU emeralds, given that both green and GRU type inductions are true and false under the same set of conditions, such that, based on the observations of many emeralds qua positive single instances, a miner using our common language will inductively reason that all emeralds are green. The miner forms the belief that all emeralds to be found in the mine or elsewhere are and will be green before and after time t. Based on the same set of observations of green emeralds, a miner using the predicate GRU will inductively reason that all emeralds observed after time t will be blue, even though thus far only green emeralds have been observed. Goodman's response to the paradox is as follows: the predicate green is not essentially simpler than the predicate GRU, since, if we had been brought up to use the predicate GRU instead, it could very well be the case that GRU would no longer count as nonsensical or as more complex than the predicate green by virtue of being green and blue. In that case, we could use predicates GRU and bleen, i.e., blue before time t, or green subsequently, just as we now use the predicates green and blue. An objection can be made that, unlike green, GRU is artificially defined disjunctively, and that therefore the natural predicate green should be preferred. Per Goodman's response, there is no need to think of GRU and bleen type predicates as disjunctive predicates. They can easily be thought as primitive predicates, such that the so-called natural or simple predicate green can be defined as GRU if observed before time t or bleen thereafter. Hence even the predicate green can be shown to be disjunctive. To this extent, the hypotheses we favor do not enjoy a special status because they are confirmed by their instances, but only because they are rooted in predicates that are entrenched in our languages, as in the case of green. If GRU and bleen were entrenched, we would have favored hypotheses of their kinds. Moreover, it should be noted that Goodman's argument applies not only to positive instances but also to negative ones, counterexamples, and as such also includes the deductivist theory of corroboration, which is based on a reliable way of choosing a candidate element among rival hypotheses for the purpose of testing against counterexamples. 377 If projectable and non-projectable predicates are equally valid, then what kinds of constraints can we impose on a system of inductive reasoning that will exclude GRU-type non-law-like generalizations? Goodman's response is that no purely formal or syntactical constraints can be sufficient to distinguish projectable from non-projectable predicates. In this sense, a machine equipped with a formal model of induction runs into the problem of distinguishing law-like from non-law-like generalizations. The only way to tell apart healthy green-like from GRU-like properties is in terms of the history of past inductive inferences. The reason we use green and not GRU is because we have used green in our past inductions. But equally, we could have been using the predicate GRU rather than green, so that we would now have justified reasons to use GRU and not green. In his radical version of the new problem of induction, utilizing Gödel's incompleteness theorems, Putnam adopted and refined this argument to show that inductive reasoning cannot be formalized, i.e., that there are no syntactical or formal features of a formalized inductive logic that can be used to make the aforementioned distinction. Putnam's use of incompleteness theorems, however, targets not just formal computational accounts of induction but any computational description of the human mind or general intelligence. For this reason, I choose to limit Putnam's argument to a computational and purely inductive model of general intelligence. This is an agent or ideal inductive judge who is only in possession of an inductive model either constructed based on the recursion theoretic, computational theory of inductive learning or on Solomonov's duality of regularity and compression. Anything that can compress data is a type of regularity, and any regularity can compress the data. 378 The reason for this choice is that I would like to retain the main conclusions reached by Putnam's argument for at least the special case of an artificial agent restricted to one epistemic modality, i.e., computational induction, thereby avoiding the justified objections raised by, for example, Jeff Buchner against the overgeneralized scope of Putnam's argument. 379. A formal system F is complete if, for every sentence of the language of that system, either the sentence or its negation can be proved, in the sense of derivability rather than proof in the absolute sense, within the system. F is consistent if no sentence can be found such that both the sentence and its negation are provable within the system. According to the first incompleteness theorem, any consistent F that contains a small fragment of arithmetic is incomplete, that is, there are sentences, Gödel sentences, which cannot be proved or disproved in F. According to the second incompleteness theorem, for a consistent system F that allows a certain amount of elementary arithmetic, but more than the first theorem, to be carried out within it, the consistency of F cannot be proved in F. Then F can be said to be Gödel susceptible. An artificial general intelligence, or even the human mind modeled purely on a computational inductive model, is always Gödel susceptible. Put differently, such a computational agent or purely inductive mind can never know the truth, in the formal derivability sense, of its Gödel sentences in the epistemic modality under which it inquires into the world. This computational inductive agent can never know the model it inhabits. It cannot know whether the model it inhabits is standard, in which case its Gödel sentence is true, or is non-standard, in which case its Gödel sentence is false. For this agent, knowing the model it occupies and under which it conducts inquiry into the world is not just underdetermined. It is rather completely indeterminate insofar as, within such a system, the only possible information that can lead to the determination of the truth of the models. Gödel sentences can only be obtained by finitary derivation. And within such an agent's model, finitary derivation cannot establish the truth of the Gödel sentences unless the agent's inductive model is updated to a new computational system, in which case the question of the model the agent occupies and its indeterminacy will be simply carried over to the new system. In its general form, Putnam's argument in representation and reality rejects the possibility that inductive inferences can be computationally formalized. This is because either Bayesian reasoning, i.e., prior probability metrics, cannot be arithmetically formalized, or projectable predicates cannot be formalized. A purely inductive computational model of the mind or general intelligence is Gödel susceptible, which means that the description of such a model is indeterminate and hence arbitrary. Whereas Goodman's argument challenges the distinction between rival hypotheses or law-like and non-law-like generalizations based on formal syntactic constraints, Putnam extends Goodman's argument to the description of the mind itself, insofar as inductive inferences cannot be arithmetically formalized owing to Gödel susceptibility. No computational model of a purely inductive mind or an inductive model of general intelligence can prove it is correct or prove its Gödel sentences in the characteristic epistemic modality of the proof procedure of the formal system formalizing those methods. 380. This problem, however, could have been avoided had the model of general intelligence accommodated epistemic multimodality, inductive, deductive, and abductive methods, syntactic complexity as well as semantic complexity. But the inductivist proponent of artificial general intelligence is too greedy to settle for a complex set of issues which require that we expand the model of mind and rationality. Not only does he want to claim that the problem of constructing AGI is the problem of finding the best model of induction, based on the assumption of the sufficiency of induction for realizing the diverse qualitative abilities which characterize general intelligence, he also seeks to lay out this omnipotent inductive model in purely syntactic axiomatic terms without resorting to any semantic criterion of cognition, i.e., conceptual rationality. But what the inductivist gets is the worst of all possible worlds. He ends up with both the reliability quandaries harbored by the problems of induction old and new, and the problems of the computational formalization of induction. In addition, Putnam's argument as formulated in his essay Degree of Confirmation and Inductive Logic can be understood as a general argument against the possibility of the construction of a universal learning machine. 381 Such a machine is essentially a measure function p that is effectively computable and which, given sufficient time, would be able to detect any pattern that is effectively computable. 382 Since the ideal of any inductive system is to satisfy the previously mentioned conditions CPI and CP2, and furthermore, since a universal learning machine should be effectively computable, such a machine must satisfy two additional general conditions which correspond respectively to CPI and CP2, for an inductive method D. CPI, D converges on any true computable hypothesis H. CP2, D is computable. Putnam has demonstrated that the effectively computable P, i.e., the universal learning machine, is diagonalizable such that CPI and CP2 violate one another. Stated differently, no inductive method can simultaneously fulfill the condition of being able to detect every true effective computable pattern and the condition of the effective computability of the method itself, and so qualify as a universal learning machine. For a candidate computable measure function P, a computable hypothesis H can be constructed in such a way that P fails to converge on H. 1. Let C be an infinite class of integers n2, n3, having the following property: the degree of confirmation, R, of M, xn, exceeds 0.5 if all preceding individuals are M. For M xn2, R exceeds 0.5 if all preceding individuals after xn2 are M. Or generally, the degree of confirmation M, xn, is greater than 0.5 if all the preceding individuals after xn are M. 2. The predicate M belongs to the arithmetical hierarchy, i.e., it can be defined in terms of polynomials and quantifiers. 3. C is a recursive class, and as such, the extension of the arithmetic predicate M. It is recursive in the sense that there exists a mechanizable procedure to determine whether an integer can be found in this class. C is the direct result of the effective computability interpretation of CP2, i.e., it must be possible to find an M. 4. Beginning with the first individual x0, compute Pm, x0, and let hr0, be im, x0, IFFP, m, xo, 0. 5. 5. For every new individual xn plus 1, continue the previous procedure, computep, m, a, m plus 1, h, x0, h, xn plus 1, and leth, xn plus 1, b minus 1 m, xn plus I, IFF. The probability of Pm xn plus ff, exceeds 0.5. 6. Even though h is computable, nevertheless because of the construction of instance confirmation given by the measure function P, it never remains above or exceeds 0. 5. 537. 7. Thus if an inductive method D is to satisfy CPI and CP2, then it cannot be reconstructed as a measure function. Or alternatively, if D is supposed to converge to any true computable hypothesis, CPI, and to also be computable itself, CP2, then it would be impossible to reconstruct it as a measure function or a universal learning machine with the aforementioned characteristics. If we reframe Putnam's diagonal argument in terms of the familiar Church-Turing paradigm of computation as a special computer, or alternatively as an inductivist expert or scientist, we can say that this expert is supposed to be capable of guessing or making informed bets about the next digit in a sequence of Os and Is. For example, given a sequence 0, 0, 0, 0, 0, a non-expert person might say that the next bit is also 0. But for an inductive learning machine or expert, the extrapolated sequence might be something like 0, 0, 0, 0, 0, 1, 1, 0. The inductive learning machine is concerned with a general inductive rule that yields an output about the guess or bet regarding the next bit given the finite sequence that has been observed so far. This expert rule is called the recursive predictor or extrapolator T. Evidence extrapolator T-prediction. Over time, the predictor sees more bits of the infinite data stream S. In this scenario, at each stage or time n, when n is obtained, the initial segment of the data stream S(S2) pound is available for examination. If we take H as the set of hypotheses of some interest or the set of all possible data streams which may arise, there is an actual data stream SEH which can be extrapolated as the predictor inspects increasingly larger initial segments of S and outputs increasing sequences of guesses or bets about the bit straying that might arise. T can be said to be reliably extrapolating if in the limit if, for every individual pound in H, there is a state or time n such that, for each later time m, the extrapolator's prediction is guaranteed to converge on correct prediction, r/en equals fen plus 1 where /pound is a recursive 0-1 valued function, f pound n is the initial segment of/pound of the length n and fbn plus l is the next value. Putnam's diagonal argument shows that no recursive t can extrapolate every recursive function f pound n if it is to satisfy both CPL and CP2. Furthermore, at no time or stage can the data imply the correctness of the hypothesis. In the vein of Kevin Kelly and others' elaboration of Putnam's diagonal argument 383, let us assume that there is an effective procedure or computable function /e x that allows us to calculate in advance how many particular observations or bits x must be successively given to 7 in order for t to be able to predict the next observation x for each finite data segment e. T can be said to be recursively gullible if there exists precisely such a computable function. 384 or, more simply, T is recursively gullible when, regardless of what it has inspected so far, when fed observation x frequently, it will begin to predict that x will arise next. Using Putnam's diagonal argument, it can be proved that a recursively gullible T does not extrapolate hrec when H is a set of all data segments generated by a computer, i.e., hrec is a 0-1 valued recursive set. In this demonstration, at each stage, we check 7's prediction at the end of the previous segment of x. Next we pick a datum, say y such that y equals /x, cf first green u, then choosing not green, xj. At this point, / can be used to calculate how many instances of y need to be added to the current data segment e in order to enable 7 to predict y. Once / has calculated how many, we add that many instances of ys to e so that one makes a mistake once it has read the last instance of y just added. T makes infinitely many mistakes. Yet pound is effective insofar as effectiveness has been defined recursively by way of the recursive function /. Therefore, if pound e hrec then T does not extrapolate hrec. 385. Moreover, Tom Sturkenberg has painstakingly shown that even a Solomonov optimal learning machine falls under Putnam's diagonal argument. 386. An optimal learning machine can be defined as a pool of competing learning machines or inductive experts with no assumption about the origin of data and for which the criterion of reliability, i.e., guaranteed convergence on the true hypothesis, has been replaced with the more moderate criterion of optimality, i.e., it is guaranteed to converge on the true hypothesis if any learning machine does. It might be objected that Putnam's assault on the idea of a universal learning machine is not exclusive to the computational account of predictive induction, but can equally be applied to our inductive methods. That is to say, we should extend the conclusions reached by the diagonal argument to the human mind. It then follows that the quandaries that arise from the formalization of predictive induction not only undermine the idea of a universal computational learning machine, but also challenge the human mind. Consequently, the skeptical claims made against the possibility of constructing genuine learning computers seem to be prejudiced in that they limit the implications of the quandaries of induction to computers while letting the human mind off the hook, whether in the name of human exceptionalism or an implicit metaphysical concept of the human mind. If inductive inferences are indispensable tools in forming knowledge claims, then the problematization of inductive methods and its consequences cannot be selectively used to distinguish human knowledge from a learning machine. If anything, such a problematization dissolves the distinction between the two, since both have to face the same set of challenges. In response to such an objection, it should be pointed out that the human knowledge or human mind is distinct from a universal learning machine because human knowledge formation is not a matter of either/or. Unlike a universal learning machine, human knowledge is not based either on a purely inductive method or a purely deductive method. It is based on both, as inseparably connected. For us, inductive inferences are caught up in a complex web of diverse epistemic modalities, semantic complexity, contextual information, and so on. To put it differently, our inductive methods are impure in the sense that they do not operate by themselves but always in conjunction and entanglement with other methods and modes of epistemic inquiry. This of course raises the question of what the catalog of such methods and epistemic modalities might be, a catalog that can at once list, distinguish, and rank epistemic methods and mental faculties. This is indeed an open question that only philosophies of epistemology and mind under the aegis of cognitive sciences including logic and theoretical computer sciences can answer. The first step toward compiling such a catalog, though, is to abandon on a methodological level any inflationary method or model identified as the most decisive or sufficient, in favor of the toy model approach to human rationality and mind that has been introduced in this book. Hume's challenge properly understood is not a challenge to knowledge per se, but to paradigms of knowledge built on inflationary models of epistemic inquiry, constructed on the premise of a single method deemed sufficient to carry out the task of other methods or different faculties of mind. What distinguishes the human mind or knowledge from a universal learning machine of the kind described above is precisely ordinary, i.e., human rationality, which is reliant on both epistemic multimodality and a complex of qualitatively distinct mental faculties. Here, however, the term ordinary ought to be handled with care, distinguished from common sense as identified purely with the manifest image, and defined precisely and scientifically in terms of a multilevel web of interrelated methods and faculties. Most importantly, ordinary rationality should not be equated with the vague notion of informal rationality. As Kelly and others have expressed, the appeal to ordinary rationality as informal rationality is more akin to a conversation between a cognitive scientist and a naive philosopher. Imagine the scientist and the philosopher standing next to a computer. Every time the scientist makes a claim about how the computer functions, what it can possibly do, or how it might shed some light on our own rationality, the philosopher says, "Switch this stupid thing off. I have informal rationality." 387 If ordinary is taken to mean informal as common sense qua a purely manifest image of our rationality, then there is indeed a question as to what exactly safeguards common sense rationality from the aforementioned quandaries. If the answer is that evolution has provided us with epistemically reliable heuristic inductive tools or some innate creative intuition, then, as argued in the excursus on time, the collapse into epistemic naivete is inevitable. Similarly, if informal means not formalizable, then the question would be how we can claim that ordinary human rationality is foreclosed to formalization without providing either an inflated picture of human rationality or an impoverished account of formalization. The equation of ordinary rationality with informal rationality in the latter sense is, alas, among the weakest of Putnam's arguments, and this for a number of reasons. As Buchner has argued, not every model of formalization means arithmetical formalization. 2. If ordinary rationality in its entirety cannot be modeled on the classical Church-Turing paradigm of computability, this does not mean that ordinary rationality cannot be modeled computationally, for, as has been argued in the previous chapters, the Church-Turing paradigm is only a special case of a more general concept of computation. 3. In light of 1, and 2, the claim that human rationality is not formalizable requires unjustifiably strong claims with respect to either the nature of human rationality or the scope of formalization. In either case, the price to be paid for this claim to be considered justified or rational in a non-inflationary sense is too high. Ruling out the more familiar senses of the ordinary, then, what does ordinary mean when we associate it with human rationality? The answer is that ordinary means the complete demystification of rationality as something extraordinary. But more importantly, it implies that rationality, as concerned with knowledge formation and knowledge claims, does not rely on the power of a single method or model that can be said to be sufficient to satisfy all aspects and desiderata of the rational or the epistemic order. That is to say, ordinary or human rationality is essentially multimodal. By multimodality I mean what Lorenzo Magnani calls the hybridity and distributedness of methods and modes of gaining traction upon the objective world, and what Yehoshua Bar Hillel identifies as a multidimensional perspective as opposed to a one-dimensional perspective, i.e., a line of thinking that considers a single point of view to be sufficient or decisive. For knowledge formation or the theoretical assessment of hypotheses, point 388 epistemic multimodality or the multidimensional perspective, however, should not be interpreted as a pure liberal pluralism of models and methods. The implied plurality is a constrained one, in that it admits of a ranking or prioritization of methods, modes of inquiry, and mental faculties which are in complex interplay with one another. Faced with the various ramifications of the problem of induction, at this point an inductivist will invoke the magic word simplicity, or some variation of it, either elegance, which is concerned with the formulation of a hypothesis, or parsimony, which deals with the entities postulated by a hypothesis. In either case, simplicity is taken as a magical remedy for the plights of induction. As long as there is the principle of simplicity, there is a way out of the predicaments of induction, example differentiating projectable from non-projectable predicates. For an inductivist proponent of theory formation and theory comparison, simplicity is what enables us to separate good hypotheses from bad ones, or to distinguish true theories when dealing with competing, incompatible, or rival theories. At first glance, this claim regarding the significance of the principle of simplicity does indeed appear sound, for the principle of simplicity is a tool that imposes helpful and necessary pragmatic constraints upon our epistemic inquiries. But the inductivist is not interested in simplicity as a pragmatic tool whose application requires access to semantic information about the context of its application. When the inductivist speaks of simplicity, he refers not to simplicity or to Occam's razor as a contextual pragmatic tool, but to simplicity as an objective epistemic principle. When comparing incompatible or rival theories 7 and T2 on the sole basis of a general and context-independent objective notion of episteme. Simplicity, one of the theories, the simpler one, can be characterized as true. But when faced with two incompatible and rival theories, one of which is actually false, the appeal to the principle of simplicity cannot be made indiscriminately, since in one or more contexts, the false theory may be simpler than the true one, and may accommodate well-formulated casions which are ill-posed in the other theory. 389. A more up-to-date inductivist can claim that such an idealized objectivist notion of epistemic simplicity does indeed exist, the formal computational account of Occam's razor, where simplicity is equated with compression, and compression is couched in terms of the effectiveness of Solomonov prediction. It is precisely this absolute and objective notion of epistemic simplicity understood in terms of the formal duality of regularity and compression that lies at the heart of inductivist trends in artificial general intelligence. According to algorithmic information theory, a data object such as the specification of a hypothesis is simpler when it is more compressible, i.e., when it can be captured by a shorter description. This idea can be made formally precise using the theory of computability, resulting in Kolmogorov's measure of complexity for a data object as the length of its shortest description or the program that generates it. The length of the program is essentially the number of bits it contains. Solomonov induction, or method of prediction, uses this complexity measure to give higher probability to simpler extrapolations of past data, for a monotone machine that has been repeatedly fed random bits through the tossing of a fair coin where the probability of either 0 or 1 is 0. 5390. The output sequence 6 of any length receives greater algorithmic probability if it has shorter descriptions of the input sequence p given to the machine in that manner. The probability that we end up in this manner feeding the machine a sequence that starts with p entirely depends on the length p. 391. Once the machine processes p, it outputs a sequence. For an output 0 of any length that starts with the sequence, p can be said to have been a guide or program for the machine to produce the sequence that enjoys a greater algorithmic probability. In other words, p is effectively the machine description of p. To put it more formally, the Kolmogorov complexity of an infinite string AAI, 0 to 6n where c, I is 0 or 1 can be generally formulated as Ka equals min backslash p backslash pe0l asterisk up equals a, where 0, 1 asterisk is the set of all binary strings, U is the universal Turing machine or a formal descriptive language, and P a variable ranging over all programs such that when U is applied to them, they produce A as the initial segment of the output. Now the question is as follows: if we give the machine random bits, what would be the probability of machine U returning the sequence A, or more precisely, the probability that we arrive at a 17 description of A? Is restricted to universal Turing machines, and furthermore, since in the classical Church Turing paradigm of computability, the machine cannot accept new input bits during the operation, this criterion is satisfied by the addition of a specialized oracle. It is called monotone since the monotonicity constraint permits to directly infer from the machine U a specific probabilistic source. A function m, y, t, can be called monotonic when for a later time t of the time t and extensions of y of the descriptions y, we can derive from m a data object which is the extension of m, y, t. Essentially, the monotonic function is a transformation such that it returns for each finite binary string, the probability that the string is generated by the machine U, once U is fed repeatedly a stream of uniformly random input produced by bets that the probability of either 0 or 1 is 0.5. This allows us to define monotone descriptional complexity of a data object in terms of U with almost the shortest description and without reference to the hidden information in the length of either P or A. 391 Solomonov has demonstrated that this probability is 2,545. Solomonov demonstrates that if we seek to generate a prior probability distribution over this task can be accomplished by resorting to Occam's razor where higher probability is assigned to simpler or shorter strings. The so-called Solomonov prior, M, answers the above question by finding this probability via Occam's razor and in relation to Kolmogorov complexity. The Solomonov prior or algorithmic probability source can be formulated as M, A equals XXLPLPE duo, where dv is the minimal 17 description of CR. Or, more simply, the Solomonov prior is the sum over the set of all programs which compute A. If P is long, 2LPL will be short, and therefore contributes with a higher degree of probability to M, V. The inference of the Solomonov prior is called Solomonov universal induction. Solomonov induction shows that, when seeking the computer program or description that underlies a set of observed data, statements, by way of Bayesian inference over all programs, one is guaranteed to find the correct answer if Solomonov prior is used. In tandem with the theories of Andrei Kolmogorov and Gregory Chaitin, Solomonov's theory of universal induction assumes that the best theory is the one that is simpler, with simplicity defined formally as compressibility. Therefore, the best theory is the one that best compresses the observation data. The question of compressibility is at its core the question of finding patterns that are effective. Solomonov induction proposes, then, that the best method of prediction of the unobserved data is one that best compresses the observed or available data. Solomonov induction has a number of curious characteristics. The Solomonov prior is incomputable, the prior is highly language dependent, i.e., dependent on the subjective choice of the universal Turing machine which determines its definition, and it presupposes the examined hypotheses to be computable. While these characteristics pose a challenge to the practical implementation of Solomonov induction by ordinary or even idealized humans, they can nevertheless be appreciated as useful pragmatic constraints. Take for instance, the incomputability of the Solomonov prior. The implication of this constraint is that the Solomonov prior can be defined in terms of semi-computability or approximation from below, rather than strong or full computability. 392 To this extent, none of these features will be employed in the critical assessment of Solomonov induction here. The argument will instead be centered on Solomonov's interpretation of Occam's razor as compressibility bias, and its reliance on the notion of effectiveness. It has been formally proved by Solomonoff that the aforementioned method of prediction is reliable in the sense that it leads to the truth. Entirely, Solomonoff induction is based on the definition of a type of predictor with a preference for simplicity, along with the proof that a predictor of this type is reliable in that it is guaranteed to converge on the truth. Accordingly, Solomonoff induction is a formal argument that justifies Occam's razor. In Solomonoff's theory, simplicity is characterized in terms of the weighted sum of program lengths, which depends on the choice of the monotone universal Turing machine. The choice of the machine which determines the length of the program or description corresponds to the argument from parsimony, while the length of the program itself corresponds to the argument from elegance. However, a closer examination of Solomonoff's Carnap-influenced formal theory of induction reveals that this objective notion of simplic ity is circular. 393 The argument, as advanced by Solomonoff and further detailed by Vitagny and Hutter, can be briefly formulated as follows. 394 Given two classes of predictors Q and R which respectively specify the class of algorithmic probability predictors via all universal monotone Turing machines and the class of effective mixture predictors via all effective priors which embody inductive assumptions. 1. Predictors in class Q have distinctive simplicity qua compressibility bias. Or equally, predictors in the class R operate under the inductive assumption of effectiveness in the context of sequential prediction. 2. Predictors in Q are reliable in every case. Or, predictors in R are consistent. 3. Therefore, predictors with a simplicity qua compressibility bias are reliable in essentially every case. Or, predictors operating under the inductive assumption of effectiveness are consistent. However, by making explicit the property of consistency in the second step of the argument, i.e., the consistency property of Bayesian predictors as applied to the class of effective predictors, 395 it can be shown that the argument essentially runs as follows. 1. Predictors in R operate under the assumption of effectiveness. 2. Predictors in R are reliable under the assumption of effectiveness. In other words, a vicious circularity in the definition of simplicity qua compressibility bias emerges. Predictors operating under the assumption of effectiveness are reliable under the assumption of effectiveness. The meaningful application of the formal notion of simplicity as compressibility to infinite data streams is ultimately predicated on the inductive assumption of effectiveness. But this assumption only offers a weak notion of simplicity, insofar as any inductive assumption can be taken as a specification of simplicity which then requires a new inductive argument to specify which assumption of effectiveness is preferable or which notion of simplicity is more strongly objective. Adding such an argument would again require further inductive arguments to establish the ideal effectiveness as the simplicity stipulation. Without these additional arguments, the notion of simplicity ends up being viciously circular, and its connection to reliability cannot be established. But with the addition of an inductive argument that specifies effectiveness, a potentially infinite series of arguments will be required. Thus, ironically, the formal definition of simplicity requires a program that can no longer be identified as simple, elegant or parsimonious, in any sense. Moreover, Pace Vitagny and Hutter, there is nothing in the definition of Solomonoff universal induction nor in the definition of any inductive predictive method that warrants our interpreting effectiveness as a metaphysical constraint on the world rather than as an epistemic constraint, i.e., what is calculable. An inductivist may contend that Solomonoff induction finally provides us with a reliable and universal standard to discriminate green-type hypotheses from GRU-type hypotheses. This universal standard is the formal definition. No matter which chance hypothesis is true, any non-pathological stream of data generated by that hypothesis would lead an agent with that prior to pile up more and more credence on smaller and smaller neighborhoods of the true hypothesis. G. Bellet, Bayesian Orgulity, Philosophy of Science 80:4, 2013, 490. Of Occam's razor, or compressibility bias. Green-type hypotheses are more simple hypotheses as formally defined, i.e., they can compress the available data better. But this contention fails to be cogent on two accounts. Firstly, Solomonoff induction is clearly an effective interpretation of induction by instance confirmation. But as noted earlier, the essence of Goodman's new riddle is not about observed instances. Goodman argues that observed instances or the available data by themselves, i.e., without the application of projectable predicates to such instances, can result in incompatible hypotheses. The core of Goodman's problem is how to differentiate projectable from non-projectable predicates which are not supported by their instances. Therefore, the inductivist contention misunderstands the scope of Goodman's problem. As for the second point, since the formal account of simplicity leads to an infinite regress, the inductivist has no choice other than to resort to a metaphysical account of simplicity. Then the question shifts: what exactly warrants a metaphysical conception of simplicity? Surely, it cannot be the principle of simplicity itself. Foregoing the metaphysical conceptions of simplicity and effectiveness would require us to abandon the more ambitious claims regarding the sufficiency of inductive predictive methods, the possibility of a universal learning machine, and the inductive nature of general intelligence, in favor of far more modest pragmatic epistemic claims which may indeed be significant in the context of our own methods of inquiry and only in conjunction with other epistemic modalities. This is the predicament of simplicity qua compressibility as an objective epistemic notion. Its criteria are underdetermined if not wholly indeterminate, and its definition is circular. In idealizing or overgeneralizing the notion of simplicity in terms of compressibility, and by identifying general intelligence with compression, the inductivist robs himself of exactly the semantic conceptual resources that might serve not only to determine the criteria for the application of the principle of simplicity, but also to define general intelligence in terms not of compression but of the selective application of compression. Once again, the inductivist proponent of general intelligence finds himself confronted with old and new predicaments, albeit this time within the context of the formal computational models of induction. Ultimately, the pessimism weighing against the possibility of artificial general intelligence in philosophy of mind and the over-optimism of proponents of the inductivist models of general intelligence, in a sense originate from their choice of model of rationality. They choose either a thick concept of rationality that does not admit of the artificial realization of mind, or a notion of rationality so thin that not only is artificial general intelligence inevitable, but it inevitably takes the shape of an omnipotent omniscient inductive superintelligence. The popularity of these factions is not so much a matter of theoretical sophistication or technological achievement as the result of the dominance of such impoverished concepts of rationality. In their pessimism and over-optimism, they are both beholden to paradigms of justification derived from a narrow conception of rationality and mind. To truly begin to examine the prospects of the artificial realization of general intelligence, one ought to start from the position of systematic skepticism with regard to any paradigm of rationality built on a method of theoretical inquiry claiming to be a sufficient replacement for every other method, example overconfident as in contrast to modest Bayesian or statistical methods, and to any inflationary model of mind that collapses the qualitative distinction between different faculties and the requirements for their realization.